thanks for the invitation to come here and do a presentation of our results in front of JLab users meeting. And I will talk about a few selected results we have obtained recently within the Compass collaboration, but I will only talk about the results connected with a hadron beam. If I were to give you an overview of everything, I would have to give several talks, and I think I would like to spare you from that. So what I'm going to talk to you today is, I'll mention the results from the reaction we have obtained scattering pions on a heavy nucleus, but basically using the photon field around the nucleus as a target, and this way addressing questions like the pion polarizability or radiative excitation of mesons. And then I will turn into pi proton scattering measurements, and there we deal with the spectroscopy, and I will give you some results of what we have obtained here. In particular, I will outline a few new analysis methods which we had developed recently, which we're still in the course of continuing to develop. And then at the end, I'll give you a brief summary. Now, of course, you know the constituent quark model, and you know this, let's say, the way how we get quantum numbers, or how we assume that we get quantum numbers for mesons. And just to remind you, of course, we have the total spin J of meson composed from the spin and the orbital angular momentum, and connected to a spin, orbital angular momentum, and to the isospin, we have the basic quantum numbers which characterize our system. We have the parity, we have the charge conjugation, and we have the G parity. We start with the pion beam. Everything we produce is G parity conserving, so we always end up with the same G parity for, let's say, yes, for all the pions we do. Sorry, and the charge conjugation. So if you want to do mesospectroscopy, of course you hunt for the various quantum numbers, not because each individual state is of any particular importance. There are some of them which are particularly important, but normally it's just a picture, it's a pattern which you want to get, and you would like to see whether you understand the pattern, the excitation spectrum for the various quantum numbers in order to compare to a variant nowadays with lattice calculations. There are some peculiar quantum numbers which people are after, and they're always happy if they find at least one or two. They're not really yet interested in the full spectrum. Of course, this will come. And those are a combination of quantum numbers which are forbidden for the normal QQ system. And in particular, I want to point out the 1 minus plus, also the 3 minus plus states which people are hunting for. And those cannot be at least explained easily in this very simple constituent quark model, but you must have other constituents which add to the quantum numbers, which are typically thought of being the duals. And of course you have, and that's important for the interpretation, that different quantum numbers can same quantum numbers mix. Now before I go to investigate the different quantum numbers, I would like to start with our beam particle, which is a pion. And let's say, what do we know about it? And well, it's the lightest composite system, and it has a lifetime of 10 to the minus 8 seconds, which in our experiment at CERN, which has a beam of pions of 190 GeV, means that you don't have to worry about its decay. It has a typical flight path of 10 kilometers. One also notes it has a finite size. The square root of the mean square charge radius is 0.67 centimeters. And now, of course, the question you may ask, what is this macroscopic structure beside of having this charge radius? And for this, we can investigate a property which is a classical property, namely the polarizability. And one knows about the polarizability of atoms. If you have, well, atoms normally is very symmetric. If you have an external charge, then the charge cloud of the electron with respect to the proton deforms, and it's also changes its position. And this way the charges are separated in an atom, and you get polarizability. You have a plus and a minus. These polarizabilities are at the heart of everything we know about light scattering in matter. Refractive index comes from this. And these polarizabilities are typically frequency dependent, and because they're directly related also to the refractive index, which is frequency dependent. Now, typical size of these polarizabilities is 9/2 of the cube of the Bohr radius. So it is the displacement of your hat, which is sort of the order of magnitude of the size of the atom you're looking at. And the polarizability, and this is for the helium, it is 9.3 angstrom cube. So it's a rather large effect. Now, if we go to a fundamental system, or not fundamental, a composite system, but small system, bound by the strong interaction and not anymore by the electromagnetic interaction, things work at different scales. And we have two types of polarizabilities. We have the electric polarizability and we have the magnetic polarizability, which means we can separate charges by means of an electric field, and we can sort of also have induced currents by means of a magnetic field. And what you get if you expose an ion to an electric field, you get an induced dipole moment, which is thus alpha times the electric field. Now, the polarizabilities for a pion are in the order of course, femtometer squared, because that's what you expect, that's the base scale you have. However, they're not at the same level as the size of a pion, but they're only of the order of 10 to the minus 4 femtometers cubed, which in a way is understandable because strong interaction is much stronger than electromagnetic, so it takes you much more force to change anything in the shape of the pion. Now, what makes a pion polarizability interesting for an experimental is that it's a rather fundamental constant which the theorists have calculated, and they use various methods. The most modern ones, let's say in language we like to speak, is canal perturbation theory, and people have done calculation up to 2 loops, and it turns out that the electric and magnetic polarizability are very similar, but opposite in sign, so the sum is almost 0, and then what causes the difference of these two, which is 5.7 in these units. Whatever I say is always units 10 to the minus 4 femtometer squared. And if you only want to address the electric polarizability, then it is basically just half the value, just divide that two. Now, the experiments who measure alpha minus beta, but always assuming that the sum of both of them is 0, because to the accuracy measurements are done today, that I think works. They lie in the range between 4 and 14. So they certainly include this value here somehow, but it's everything but precisely determined. And so many experiments, either planned or are now done, which determine the polarizability of the pion. Now, the question, of course, first of all, is how do you measure polarizability? And what you do, for example, in atoms, is you deflect an atom in a laser field. So you have a dipole which is induced by the electric field, and then you have a field gradient, and then there's a force which is exerted to this dipole by the field gradient. And this force is F, and this is the induced dipole moment, electric dipole moment, and this is the field gradient, and then you look for the reflection of an atomic beam in a laser field. And this way, you can measure the polarizability. The typical fields which you have in atomic physics are the order of a megavolt per centimeter and field gradients up to 10 to the 11 volts per centimeter squares. These are used laser cavities. Now, and the accuracies you get for atomic polarizabilities are the order of 10%, rather poor in principle. Now, let's assume we do this for the pion. So we would like to scatter a high energy pion from a photon source as you scatter an atom from a laser. And as a photon source, you use a high cell nucleus. And well, the question is, of course, you get a strong electric field close to this. How do you get a field gradient? Well, of course, we have a fast particle which approaches the center of the nucleus. So you see during the path a very strongly varying electric field. And so you get very large field gradients by this, which is enhanced by relativistic effects. And you get 10 to the 5 volts per femtometer electric field comparable. So that's how you do the measurements. And then the particle is deflected. Well, it is deflected, and it's just deflected a little bit more. It's deflected because it's charged, other than the atoms, which are typically neutral, but you add a deflection which comes from the electric dipole moment which you induce. Now this is shown in a way here in this cartoon. So you have a heavy nucleus and you have electric field lines, which are sort of showing out here. And what you like to do is you scatter the particle here at a reasonably large distance, like a couple of radii of a nucleus. A nucleus you take lead, actually simpler is you take nickel for various reasons. And of course you cannot aim at moving at hitting at a distance of 5 radii, but you have all distances from the nucleus, so you also get effects from the strong interaction here. And how you distinguish is that the momentum transfer will be different if you get very close to here. They will be much larger than here. So you separate out the interactions of a pion with the electric field by looking at very, very small momentum transfer, which is called the Coulomb peak, or because the method is called after the Russian physicist Primakov, it's called the Primakov peak. And so these are the field strengths here. Now, the momentum transfers are very small, in principle in the order of 10 to the minus 5 MeV squared. And so if you have such fields, what effect do you expect on a pion? How does it interact with the charges? Well, the equivalent charge separation of 10 to the minus 5 centimeter charge. So it's a rather small and subtle effect which you have to measure. And of course, if you measure, since you measure everything, this is sort of the Q spectrum, momentum transfer, not momentum transfer squared, but the transfer of momentum you will see. And the spectrum is composed of part which belongs to the strong direction, and this is sort of the diffraction pattern you see here. And then we have the electromagnetic interaction, which then takes up at various momentum squares. And so what you have to do is you basically look at all the reactions which happen here at various small Q's. And this is theory, and this is the data which you have here, and you see the Primakov peak in the strong direction. And so, and the red curve depicts here the simulation only taking into account Primakov interaction or electromagnetic interaction. Now, of course, normally we speak with pion scattering in different terms. Namely, we say we do Compton scattering of a pion. That's a particle physics language. And so you have an incoming pion which scatters off a quasi-virtual photon here, and then in the outcoming channel you have the photon and you have the pion which you detect at rather high momentum. So you start with 190 GeV and you get photon energies between 40 and whatever, 180 GeV. And now you analyze the scattering process in the center of mass of the outgoing photon and the pion, and you write down the angular distribution. And the angular distribution of the pi photon system here is, gives you two parts, one which is purely related to the Compton scattering, and one which is a correction which comes to the finite size effect of the pion, with which there is a polarizability connected, and this is shown here. P is the effect of the polarizability. And then, of course, you have a certain center of mass between the photon and the pion, and we typically try to be elastic, so this is what we have as a condition. And so now you only have to analyze the angular distribution, and you fit this to basically this formula, not quite to this formula, but something like this. Now these experiments are done at the COMPASS experiment at CERN. It sits at the SPS, and we have pions and we have also kaons. We have 2 to 3% fraction of kaons, which are extremely helpful. And we also have, in addition, whenever we can switch rather easily between hadron beams and muon beams. Of course, that's very nice. This way you can repeat the experiment with the muon, which has no internal structure. You can see whether you can also reproduce this in your experiment. And so the experiment is, well, 50 meters long. It's composed of two magnetic spectrometers. The first magnetic spectrometer is this one here, and the second spectrometer is here. And that's the standard setup for COMPASS. One part of the setup, which depends very much on the type of measurement you want to do, is the target region here. And so this is shown in exploded view on the lower right. The beam and the incoming beam and the scattered beam particles are detected in a series of silicon microstrip detectors or telescopes, which gives you an excellent angular resolution for this scale of pion. And then, depending on which experiment you run, you either put in a liquid hydrogen target, that is this picture shown here. It's a 40 centimeter liquid hydrogen target, important for the measurements that will come to in the context of spectroscopy, or you place this by a thin sheet of nickel on which is scatter, and those are the measurements related to the polarizability. And then you have detectors surrounding it, 2 layers of scintillators. So they are used either to see whether you have fragments produced, or in case of scattering on the proton, they detect the recall proton. And then everything which is on the right side is actually the spectrometer here. We also have particle ID at least up to something like 50 and 60 GeV here in the first stage of the search spectrometer. Now, it's always difficult with such a spectrometer to show a single picture, so that's why I started to just show the movie. And you see here, this is the first spectrometer. This is a big imaging Cherenkov detector. These are big calorimeters. This is a second big magnet, and then downstream of the magnet, you have large size tracking detectors. Then you have an electromagnetic calorimeter, a hadron calorimeter. You have a muon absorber, and you have particle detectors passing the muon absorber, and some very small angular trigger detectors at the very end. So that is basically compass in a very short movie. Now, what concerns the polarizability measurement, in principle the measurement is relatively easy, because you only have to measure the cross-section as expected, and you divide the measured cross-section by the expected cross-section for a point-blank particle, and this you do as a function of the photon energy. So high photon energies basically means you have a big effect on the charge separation of the pions, and this way, that's where sensitivity is for the polarizability effect. Now, X is basically the fraction of the photon energy as respect to the beam energy, so 0.9 basically means 170 GeV. And we do this measurement for muons, and for muons, since you divide by the expected cross-section for point-blank particles, should basically stay constant. And so that's what it is. You analyze it with a function which includes the polarizability as a free parameter, and you get out a polarizability which is consistent with 0. And you do the same thing for the pions, and you see a big effect here, and you get a polarizability for the pion out, and this is not alpha minus beta, but it's just alpha. So it's 2 as a value. It's a statistic error of 0.6 and the systematic error of 0.7. So you see our systematic error is still larger than the statistical error. What does it mean in terms for the experiment and for the physics? Now, the polarizability is shown in this graph here. I'm sorry, it's hard to read. It's alpha minus beta. And so what you see here is the different measurements which had been done before. They lie like here, here, here. There's a whole group of reanalysis of experiments done at SLAC. In gamma, gamma goes to pi, pi. And then you see the theory curves here as this line, and you see compass is here. So that is the, we basically sit then right on the calculation of chi Vt. Now, why is this interesting? What does it actually mean in terms of particle physics? Well, of course, the pion itself, you can either consider it as a QQ bar system, or you can consider it as a Goldstone boson of the spontaneous breaking of ground symmetry. And in this case, it's a massless excitation of the ground state. And so the long wavelength description of QCD, there is nothing else but quarks. There are always only pions around. And then the polarizability of the pion basically means diagrams like this here. And the wavy diagrams are the photon, and the other lines are the pion. On particular, look at things here. So you do basically photon scattering on the pion cloud of a pion. And this has been calculated to high accuracy, two-loop calculation, and they are now nicely confirmed by this measurement done in compass. Now, Pi photon scattering, looking for the polarizability, is elastic scattering. Just like you have light passing through a gas, so you just, it comes out at the other side, just get a phase shift, nothing else. But you may also get into the resonance region of the excitation, then you basically become inelastic, because you can excite it with a photon, and then if you have the resonance typically decays strongly, for example, into 3 pions. And now if you measure the cross-section for this, then you can measure the radiative width of the system. And so this is something we use. If you have a high-energy pion beam entering the Coulomb field of a high Z nucleus, then you have all sorts of transitions. You do not only have dipole transitions, you have electric and magnetic dipole, quadrupole, and so on transitions. So there are all sorts of pionic excitations which you can get. And you find out which transition you had by identifying the quantum number of the particle which you see in the final state. And this quantum numbers you obtain by doing a partial wave analysis of the final state. So what you do actually is the following reaction. You have a pion which again interacts with the photon around the heavy nucleus, and then it forms a system X, and you see the final system decaying into 3 pions. And now what you have to do is you have to analyze the system of 3 pions in an isobar model, which involves these 2 pions building an isobar, having an angular momentum L with a spectator pion. And the only thing you have to do in order to distinguish the production of these guys here from the exchange of the Pomeron is you have to go not only to value of Q squared, but you also have to see that the spin projection of these particles, M, is 1, because that is a photon interaction. It would be 0 for the strong interaction, and a very, very small Q square, M equals 1 for the strong interaction, is suppressed by the power T to the power M. So a very small Q square, M equals 1 for the final state, spin projection 1 basically reflects electromagnetic interaction, and that's what we have done. And so you look at the photo cross-section for the system, and the photo cross-section for very small momentum transfer square, 10 to the minus 3 is the upper limit. It's simple exponential for the photo production, and for the diffractor, it's T to the power M times the simple exponential. And it's this T to the power M, which just cuts down the strong interaction at very small Q squared. So this way you can single out photo production of resonances, and this works very nicely. This is shown here for the A2. This is a mass, this is the A2 here, and you see here the Q square spectrum. You take the Q square spectrum here, you correct for interference with surrounding electromagnetic interaction, and you get the radiative width of the A2, which is, in our case, 358 keV. But you also get it for higher resonances, namely, for example, for pi 2 1670. Now, higher masses typically means you have a broader Primakov peak, and this is the Primakov peak for the pi 2. You have a little bit more background coming from the strong interaction, but again, you can extract the radiative width of the pi 2 of about 180 keV, and this is now an electric, it's an E2 transition, it's an electric quadrupole transition in order to get it, and basically the first electric quadrupole transitions seen in strong interacting system. So that's very nice, and this method can, with higher statistics, be extended to other measurements as well. So if I give you more, just a summary of what Bohr Compass is doing or will be doing in the framework of chiral perturbation theory. We have, for example, studied pion scattering, including a real photon, pi gamma, having 3 pi in the final state, and then you look much below the resonances. You look at masses between threshold and, let's say, the rho or 1 GeV, and these processes can be calculated by chiral perturbation theory, including loops. And so they calculate the 5-dimensional phase space. And you compare this 5-dimensional phase space coming from chi-pt with the observations. And you should then compare the cross-section for this process as a function of the mass in absolute terms. And that is what's shown here. This is a cross-section for 3 pi production with the photon in microbarns. And you see the data points here and the theory curve. They're right bang on top of each other. And there are many other processes which are studied here as well, like the chiral anomaly or eta production, or you can try to measure the polarizability for cables. Now let's turn to the spectroscopy, And I will be brief in the introduction because this is done here extensively. So what you hunt for are not only the normal quark systems, but everything which looks sort of surprising or at least stimulates your fantasy in interpreting the system which you see. So in Compass, we can address, if you look at the landscape of mesons, and this is the orbital angular momentum involved in QQ bar, and this is the principal quantum number of nodes plus orbital angular momentum. And you see the well-known states. You have the normal mesons pi and rho, and the excited mesons, and everything encircled in blue is accessible in Compass if we only study 3 pions. And then, of course, the 3 pions, they can decay into 2 pion systems, and then you also have access to all of the red circled mesons, in particular the scalar sector, which you see here. And you see everything, this is everything else but clear. If you just look at the pi 1800, it's a mess. And also if you look at the pi to 8080, there are various numbers for mass and width, so it's everything but settled, although it is known it's such a long time. And of course, at the very end, you would like to go to very high masses in order to understand the spectrum even up to 2.5 GeV, which is more difficult because with many resonances, overlying resonances, and you have to find a method how to single them out reliably. Sorry. Now, that is the Compass kinematics. We have the pi and the proton exchange. Well, you also Bragg exchange, but you have also Pomeroy exchange. Those are the 3 pi in the final state. And this is the isobark, and it forms an angular momentum L with respect to the pi. And so you look at the mass spectrum as a function of the format transfer, which is a very important variable in this game. And this is a mass, and this is a format spectrum. You see that the mass spectrum depends on the format in the reaction. This is shown here, where we see the mass spectrum at low and high format transfer looking very different. And you also look at the format transfer spectrum at low masses and at high masses. So you see there's an additional variable which will help you to separate out different components which you produce. And you analyze everything in terms of the isobar model. And I'm sorry, if you go to the mass of about 1.3 GeV, and you look at the Dardis plot, it's dominated by the rho. If you go point around 1.6, 1.7 GeV, then the Dardis plot looks already more interesting, and you see the rho, the F2, F0, 980. And so that is the underlying reason why we analyze these things in terms of the isobar model. And we basically analyze the Dardis plot for every bin of 20 MeV mass in the 3 pion system. Every time you basically make the Dardis plot analysis. So what is the results? I think it's just the way we do it, it's a 2-step process. We start with a model where we have a number of waves. And what is a wave? A wave basically defines the JPC of the 3 pion system, and then you have different possibilities and how you come to your 3 pi final state via various intermediate isomers. And every pathway from every JPC gives you a predetermined population of your 5-dimensional phase space, and so you have a whole library of those. And we have started out with a library containing 155 chapters, if you like. And then we boiled down this to about 88 chapters, and we just try to fit the contribution or determine the contribution from each individual chapter, which means a wave, to the spectrum. And this for individual bins of 20 MeV mass. There's no physics in here, other than this assumption here. And then in the second step, you try to get the physics. You have the spin density matrix, and from the spin density matrix, you have the mass dependence, and you try to fit the mass dependence in terms of resonances and non-resonant backgrounds. And the result is at first very boring, because you see the normal resonances which you know. This is 1++, this is 2++, 2-, and 4++. And this is at low high formatting transfer, high formatting transfer. And the interesting thing is that the spectra do not overlay. So there is a certain dependence on the spectra, on the formatting transfer, which if these peaks would only represent resonances, should not be the case. So some of these peaks certainly are a mixture of resonances and non-resonant backgrounds. Now let's go to a system which contains an F0 as an intermediate isobar, and then we do this for the case of 1++, 0-+, and 2-+. The 1++ shows a surprising maximum here is around 1.4 GeV, which was not observed before. Here you see the 0 minus plus the pi 1800, and here you see some very funny pattern, which is a complicated interference with a non-resonant background. And you look at this with the charge ions, and you compare this with pi minus, pi 0, and this looks exactly the same. So it's not an artifact of the experiment, it's really physics. Now the question is, what happens if you do not restrict your pions to be in the S wave with the short mass band around the F0, but you just allow the broad pi S wave, which is taken from pi scattering, and then you see the whole thing looks much more complicated, and it's a mess, and I will come back to this mess again. So this is restriction to the pi S wave being around the F0, and this is the complete pi S wave, and so you see there's a challenge to understand this. Now, if you try to analyze the spectrum, fit them in terms of resonance and non-resonance, then you have two contributions, resonance and a deck-like, which is parameterized in our case. It was just an analytic function. And so if you do that, then you come to the following picture for the 1++. There is a non-resonant part, there is a resonant part in blue, and the resulting fit is in red here. And you do the same thing for A2 and the A4, and it fits very nicely, but the key is that you get interference effects between the different waves, and now you look at the relative phases of these different contributions. And then you know if you have a phase with resonance and you compare this to another wave which does not resonate, then you should see a phase variation of 180 degrees. And we do this. This is the phase between the 1++ F0980 and the 1++ rho pi S wave. And you see here as a function of mass, you see large phase variation. And if you analyze now this, including the phase variation, which is always done, you get a resonance mass of 1.42 GeV and the width of 150 MeV. And this is the same phase variation now with respect to the A4, which certainly is not resonating at 1.4 GeV, but has its proper resonance at 2.0 GeV. Now the question, of course, if you see something like this, what is it? And immediately people jump on it, and there are many different explanations on the market already. One deals with saying this is nothing else but interference effect of the ordinary A11260, whatever this really is, and deck amplitude, and they can actually, with this Berger et al., they can actually produce a very nice phase variation, however not at the right place. And then there are colleagues at Bonn, Bernard Ketzer, for example, and he calculated triangular anomalies, again using the A11260, but then you have this one coupling to KK star, this going to KK pi, and the KK coupling to S0980, and there's some funny, nice triangular diagrams, and they come up with a rather nice shape which looks very similar to what we observe, and the phase variation which is at least part of what we observe. However, whenever you relate this to the A11260, you should see the same production dependence of the new state and the 1260 state, because they are linked immediately. And that is not quite the case. This, the A11260 seems to fall off much steeper with T prime than the new state. And then there are also other explanations in terms of molecular structure being a partner of the F1 1420. Okay, so now what we do, we want to get much more out, and so what we do is we just fit the spin density matrix. And this is such a fit of the spin density matrix. You in principle have 88 times 88 matrix. So this is difficult to fit. First, I show results here from 6 times 6. We're now doing 18 times 18, which is already quite a challenge. And just to see, we do not only have one spin density matrix, but we have 11, which means 11 bits of T prime. So you have this, everything is fit to the same time. So this is a challenge for the fits, but it tells you quite some interesting physics about this. And I think I will not have the time to go into the details here. There are beautiful interference effects, very classical quantum-mechanical interferences which you see, which I will spare. But I will tell you one thing, because I'm running out of time. Namely, we assume that we know the isobars which go in the analysis. So that is a very daring assumption, because you know the isobar which are created basically in a lonely way, let it be plus and minus, you have rho and then it decays freely. But here you have the isobar in decay, and there's always another particle. And this particle could have orbital angular momentum 0, 1, 2 with the other two pion system. So this could change by final state interaction the shape of your isobar spectrum. And let's see whether we can determine the shape of the isobar spectrum from the data. So basically reflects is the shape which of the isobars we put in like this as we assume, or is it odd like this? So we have had effects which come in the spectrum, which come from the resonances. We have final state interaction, and we have what we call deck effect. Deck effect, I just call everything which is not resonant production of three pions. And you would like to separate these three effects out from the data. And so what we do is the following. We make our fits, but now we do not assume, let's say you take the Piper S wave as an example. We do not assume a fixed shape of the Piper S wave, but you divide, you say I have only one Piper S wave, but I have, let's say, 40. And each one is only defined over a very small bin in the mass spectrum of the two pions. Let's say 40 MeV mass spectrum. So you have a histogram of the 40 MeV width of the 2 pi spectrum, and then from the data, you try to see what are the entries in your histogram. And so you determine the 2 pi spectrum from the data, and you do this for individual JPC of the mother, and for individual JPC of the pions. So they can be 0 plus plus and 1 minus minus and so on and so on. So you can get the isobar shape for all quantum numbers of the initial and of the intermediate state. And I just show you here the results if we have the 2 pions in the final state forming an S-wave system. And so this almost looks like a data spot, but it's not a data spot. It is the mass of the 3 pion system being in the quantum number 0 minus plus versus the mass of the 2 pion system having quantum number 0 plus plus. So it's really a tomography of the rather complex, strongly interacting system of 3 pions which you have. And you look at this as a high momentum transfer and low momentum transfer and high momentum transfer. So what you see here, let's go first to this picture here. You see intensity around 1.2, 1.3 GeV. You may say that's a pi 1300. And then you see about 1.8 GeV, that's a pi 1800. And at least on this color scale on this screen, it is not visible, but there's also an enhancement here. This enhancement corresponds to the mass of the F0 and the 2 pion. This corresponds to the mass of the F0 1500 with the 2 pions. And now if you increase momentum transfer, everything connected to resonances should stay the same, except for interference effects. But purely non-resonant stuff should disappear. It turns out that non-resonant drops off much steeper with momentum transfer than resonance production. And indeed it does. All this block basically disappears. And should not be taken as a pi 1300. That's purely deck. And you do this for different JPC of the mother wave. This is a 2 minus plus, and again you see here the pi 1880, and you see some stuff here which is far below the pi 21670, and also basically disappears if you go to high momentum transfer. And this is the 1 plus plus, and so the 1 plus plus, this is 1420, the new one, and you see that this big block is not the 1260, because if you increase T prime, then this block just moves to higher masses. It just continues moving. So it's again non-resonant production of something. The only thing which stays constant is the new A1 fracking. So that's the way how you get information out of the system, and we're going to continue this in 1 minus minus and so on. So it's great fun doing this. So that's really tomography, which is very nice. Now the question, of course, is, does it have any meaning what you get out of this? How do you interpret this? And let's just take this part here. So this is basically a 0 minus plus, and you have the mass of the 0 minus plus got in the mass of the 2 pions being in the S wave. And what you see here, and this is a reasonably high momentum transfer, is only the pi 1800. And there is a block here for the F0980 and the F0 1500 in the final state. Now you have amplitudes. It's not intensity, only with amplitudes up. And now you have, since amplitudes are complex, you can make an argon diagram. And this is shown here. So you have the argon diagram for the real and the imaginary part for the mass region indicated by this line here. And this line is almost purely pi 1800, not quite but pure, almost pure. And you see you almost start at 0, And you get your Argon diagram, and you get the nice circles as in the textbook. This corresponds to F0980, this corresponds to F1500. And then you can plot the phase variation of the pi-pi system. And this is shown here. That's the mass of the pi-pi, and this is the phase measured with respect to another system. And you see in blue the phase. And the question is this phase universal? Does it have any meaning? And you compare this with an analysis done by Babar. And then look at the d sub s decay to go k pi pi, and look at the pi pi. And those are the dark dots here. So, at first it's stunning how similar these two spectra look like. So there is certainly some underlying physics which is valid across the system, whether it's weakly decaying d sub s or strongly decaying pi 1800, it looks very similar. Of course, after being excited was the similarity. Now the interesting things start, because why are the differences? And that's where the real physics comes in. So I think I will spare you this, and I will come to the end. Compass has performed the first precise measurement of the power polarizability, and it's a very stiff system, and the value agrees very nicely with the calculation from power polarizability theory. And we have data which we're analyzing right now, which we want to use to separate electric and magnetic polarizability, and maybe we can even get the quadrupole polarizability of the pi out. And this process also is a new path to radiative meson excitations, to study radiative width of mesons, not only the A2 and the pi2, but hopefully also more heavy systems. Then we have developed a rather extensive partial wave analysis method using not only masses but also form entropy transfer, and this allows to separate out non-resonant and resonant contribution, not completely yet, but much better than before. And this way we found a new wave, or let's say new system, A14020, of which the origin is not yet known, and we don't know what the nature of this particle is. The publication should appear very soon in PRL and has been recommended for publication. And we have also shown that we developed now more methods to establish the shape of the isobar spectrum. We have done first application in pi-pi S-wave, and we've seen that we see very strong dependence on the pi-pi S-wave, both on the initial JPC and on form entropy transfer, and this yields quite some important information on the scalar algorithms. So this basically opens a path to the Danish analysis using PWA on states which themselves have only been extracted using PWA. So that is sort of the second order. For this you need high statistics, and at least in the 3-part sector we have this. Thank you a lot for your attention.
Thank you very much for the very nice talk. We have time maybe for a couple of questions. Questions?
So this should be a simple question. Your polarizability, given that it's determined by systematics, is there any chance to improve?
Yes. A good fraction of the systematics is statistically limited. So one important thing is, in order to study systematics on the method and on the spectrometer, we use the muons. And this we can't limit by statistics on the muons. We have much more data on the muons now, which we're analyzing. So this part should also be much reduced. There are certain systematics which are difficult to come by. If they're model dependent. If you want to get out, we always have strong direction vector underneath. You have a model, let's say Glauber model, in order to extract the strong and also interference part underneath the Coulomb peak, and this will stay. I mean, you have or you don't have it. But I think the most important for us, most limiting one is the muon, which is improved statistic accuracy.
So, an alternative to blending in the isobar mass, one could imagine using a different analytical parameterizations of the isobars, as opposed to saying, right, because I guess that you could be doing with mass. Something which is more flexible, which allows for different dependence for the isobar, the way it is produced from the tail of your object as opposed to read it the way around.
I mean, one thing which we, for us, it seems natural to start out with projecting everything on JPCs, which makes things more easy to analyze and interpret, and also then you have certain orthogonality. What happens if you start doing this, you realize that the normal isobar model isn't quite correct. In terms of principle, you have crosstalks between different parts because owing to the Bose symmetrization, the waves start talking to each other. And this is important for waves which contain Bose, and so this is something you see and you have to get rid of. And we're developing methods on how to get rid of these things. But let's assume you have let's say a rho and a pi, and you have L equals 1 between them. Then you have the rho, which already has a pion, which is L equals 1, and you can change the pions. And so you flip things around in the phase space of the two pions. And so this leads to ambiguities. And so we try strongly to get rid of this. This is fine as long as you restrict your two pions in an isobar, then it is, you basically fix the two pions over a rather small range of two pion masses. And for the rest of the phase space, you have the two pions that is suppressed in this case, just because the isobar model restricts yourself to this. If you leave this open, then these different parts of the spectrum start talking to each other. And that's something you have to learn how to deal with.
On your 1420, it wasn't clear to me whether you claim discovery, since you offered also alternative explanations for that structure. Is Compass claiming a discovery of a mistake?
Yes. Well, we make the discovery of a new resonance. We cannot say what it is. It is a triggering to relate this to the F1 1420. The width is not very large, actually. Depending on how you analyze, you can also get slightly smaller width than 150, but it will not be below 120, certainly not. The present calculations which have been done using alternative models, including the A11260, they don't reproduce everything which we see in the data. So I think that they're interesting that already they come so close, but they're always missing some parts. And for us, we say observation of a new isovector state.
On the topic of the pion polarizability, you pointed out that you use the muon as a point-like reference.
Yeah.
But I'm curious, will Compass be able to set a competitive upper limit on the physical size of the muon based on what you've got?
No. We are dealing here, if you look at the polarizabilities, we are in the order of 10 to the minus 4 centimeter cubed, which then, you bring down here something like 10 to the minus 1, 10 to the minus 2 centimeter of the size. But if you look at E plus E minus going to U plus E minus, then you get to the order of 10 to the minus 17, 10 to the minus 18 meters. So you're really far away from it.
Okay, let's send the speaker. So the next speaker is John Thomas.
thank you for the opportunity to talk. I want to talk to you about nuclear structure, and I want to present a point of view that is new. Now, it's hard to talk about nuclear structure and talk about something that's new. Can you hear me?
No.
No. Put it higher. Is that better? Yeah? Okay, so I want to talk about something that is new, a new view of nuclear structure. It starts from the idea that QCD is the theory of the strong interaction and nuclei are made of quarks. It runs contrary to the way many people like to think of nuclear structure, and yet one can map what I'll talk about onto those standard approaches to nuclear structure. But you can do much more. Now, why would you think that the fact that the nucleon is made of quarks might matter? Well, the answer is that on modern independent grounds, we've known since the 1970s, and the work of Jerry Brown and his group, and the work of Vin Mo and his group in Paris, that the intermediate range nuclear force has a Lorentz scalar component, and that Lorentz scalar component is large. Typically, the nucleon experiences a scalar field in nuclear matter of order 200 MeV. Now, I stress that's not a conjecture, that's model independent. So the question is, does the experiencing a force of that strength, is it really reasonable to think that a force, a Lorentz scalar which acts like a mass, is something that is not going to affect the structure of the nucleon when the strength is 1/5 of the mass of the nucleon? What couples a scalar field like a scalar field couples to a scalar field like that are the quarks. Not the brown muck inside the nucleon, it's the quarks that feel that scalar field. Quark masses are very light. Of course, that gets hidden by spontaneous breaking of chiral symmetry. But quark masses are a few MeV, and feeling, in addition to that mass, a scalar field of order 1/3 of 200 MeV, so 70 MeV for each quark, is a very significant change in the mass. It means instead of the mass being 5 MeV, in the quark that's confined, for the quark that's confined, it's minus 70 MeV. And that has a significant effect on the structure of a hadron once you include relativity. And so I want to tell you about that. So the outline is, what lies at the heart of nuclear structure? Well, the answer is QCD. We start from a QCD-inspired model. We can't yet do this in QCD, and ask how the structure of the nucleon is modified in the medium. So the approach is quite different to what's been the time-honored approach. Starting in the 1930s, build a nucleon-nucleon force, solve the many-body problem with the free nucleon force, find it doesn't work, add a 3-body force with some parameters. In the case of argon, something like 4 parameters fitted to the binding energies of light nuclei. And then gradually build your way up. Or the modern approach, start with a chiral force, build in parameters as you go to higher and higher order, and fit data. The approach here is to start with a nucleon, model of a nucleon, insert that model, that nucleon into nuclear matter, calculate the change in its structure, and from that you can calculate many, many things. So you don't start at the level of 2 nucleons and 3 nucleons, you start at the many-body level and solve for the change of the structure of the nucleon in the medium. From that you can make predictions for many things. It naturally leads to saturation of nuclear matter. You can derive effective forces of the Stern type, and you can do serious nuclear structure. And I'll show you some results from recent work that's not yet on the real sheet. And you can also look at predictions for nuclear. What you can do, because this thing is based at the quark level, you can also ask, how do the structure functions of the nucleon in the nucleus change? How do the electromagnetic form factors of the nucleon in the nucleus change? And so here's the pretty picture. You start with nuclear matter and a model of the hadrons. You calculate how the structure changes, and from that you can calculate the binding of any particle in nuclear matter, because the couplings are at the quark level. You don't need new coupling constants for the lambda, the cascade, and so on. They're given by the couplings of the mean fields to the quarks, which you know from studying the nucleon. You can also do nuclear structure by deriving density-dependent effective forces and turning the handle of nuclear structure. There are just three parameters here, which are the couplings of the mesons to the quarks, and the key mesons you need. It's a very simple theory. You could make it more complicated. Is the sigma meson, the omega, and the rho. The rho necessary because you need a nice effective force. So that's the starting point. This is the most technical slide for those of you who want to actually see how things work. In the MIT, if you take for the nucleon the MIT bag, you can do almost everything in closed form. So in fact, the modified wave function for a quark in a nucleon in a scalar mean field looks like this. The x is the modified eigenfrequency. The critical thing is this beta, which is the coefficient in front of the lower Dirac component, involves the frequency of a quark when its mass is 0 minus mq star. Mq star is the effective mass of the quark, and it's negative. So this means that the lower component gets enhanced by the fact that the quark's feeling an attractive scalar field. It slightly changes the confinement radius, but not much. From the point of view of nuclear structure, the critical thing is that if you calculate the integral of q bar q, the coupling of the quarks to the scalar field, mq star enters with a plus sign, and so this decreases as mq star gets more negative. So as the quark feels a stronger scalar potential, the coupling of the quarks, coupling of the nucleon to the scalar field decreases. That's what gives saturation. So whereas in the very rightly famous Kolechka model, the effective mass of the nucleon is just the free mass minus a term linear in the coupling to the mean scalar field. Once you take into account the internal structure of the nucleon, there's an additional term which has the opposite sign. So the effective mass does not drop so quickly. It actually tends to flatten as the scalar field grows. And that naturally leads to saturation of nuclear matter. This coefficient D is called the scalar polarizability by analogy with the electric polarizability of an atom or a nucleon in an electromagnetic field. In the bag model, you can solve for it almost analytically. It's about 0.2 times the bag radius. In terms of physics, what this change of the structure of the nucleon in the medium means is that you can picture it as an effective three-body force. That is, when you bring three nucleons close together, the interaction between them is not just the sum of the individual interactions between each pair, but because having one nucleon and another near it modifies the internal structure of this one, it means the interaction of that with another is different. And that is naturally the origin of a three-body force. So this picture gives not just the two-body force between nucleons or any other hadron in terms of the couplings of the mesons to the quarks, but it also gives a three-body force. So it looks this approach looks superficially like QHD, but it's fundamentally different. The self-consistent adjustment of hadron structure due to this mean scalar field, which is not a model dependent, well, the magnitude is somewhat model dependent, but the fact that it's there is not model dependent. The self-consistent adjustment through this scalar polarizability leads to saturation of nuclear matter, effectively because there is a three-body force in the theory. There are just three parameters. You fit those parameters to nuclear matter properties, and then you can calculate a vast number of things. Now, some time ago, it's almost a decade ago, Pierre Guichon, who invented this model, and I decided we should try to connect it to standard nuclear theory. And so we used it to derive a Sturm-type force that, so we took the Hamiltonian at the quark level, wrote it in terms of nucleons, and then wrote it in terms of an effective interaction that was equivalent, and showed that you get 2 and 3 body forces. And it didn't look too bad, but it's hard to compare because the density dependence in this theory is different. So we then, and most people now do not use the old Skirm forces with 2 body and 3 body forces. They use density dependent 2 body forces. And so a little later we were able to derive, and down the bottom you'll have to look here, a lot of references are going to drop off. But the talk will be posted. So this is about 2006. We showed how to derive a density-dependent energy functional from this theory. So if the interaction corresponding to that energy functional is local. It looks exactly like the effective forces that are written in standard treatment of nuclear theory. But what was slightly different is that the density dependence, so this is the central piece of the interaction, of the density functional. There's a nonlinear dependence on density rho. G sigma is effectively the sigma nucleon coupling in free space. And the nonlinear density dependence that enters down the bottom here is proportional to this scalar polarizability D. So the origin of that nonlinear density dependence is the modification of the structure of the nucleon in medium. Now, a little 3 or 4 years later, a group in Brazil, together with Urena Stone from Oxford and Oak Ridge, made a study of something like 233 Skirm forces. This is incredibly broadly used in nuclear structure. And they set 12 standard things they could test those forces against. And of the 233, only 9 satisfied the constraints that this group of people imposed. And amongst those were 2 of the Skirm forces that we derived there. The 700 and 750 correspond to the mass of the scalar meson, which is, when you quantize the theory, not quite well defined. That is, you can't say exactly what it will do. So 2 of these forces, all of these others have something like 12 to 15 parameters fitted to the properties of atomic nuclei. This theory has 3 parameters plus the mass of the scalar potential, which is fixed at 1 of 2 values. Doesn't matter, they both satisfy the constraints. Just 3 parameters for each. Now, most recently, this has been taken to a new level by doing serious nuclear structure calculations with these density-dependent Skirm forces. So the work, a lot of the work's been carried out by Urena Stone. We benefited enormously from P.G. Reinhardt's expertise in. So we take these 3 basic quark meson couplings. We require that we fit nuclear properties within the range with which the saturation density, binding energy, symmetry energy, and so forth are known. Fix that set of 3 basic parameters so that we satisfy these constraints in order to give the best overall description of finite nuclei. Finite nuclei are this group, so it's not just closed shell, it's all over the periodic table, complete sets of isotopes and isotones. So for example, if we come down here to gadolinium, Z equals 64 and N from 74 to 100. Okay? There's well over 100 nuclei that have been studied. There's a lot on this plot. What's plotted is the difference, the absolute difference of the binding energy of the entire nucleus in the calculation and experiment. So for example, down here in plutonium, which is about A equals 240, a deviation of 4 MeV is well, you can do the maths, it's about 0.25%, something like that. Overall, the agreement is typically better than 0.5%. As you get towards the end, that is to some of the nuclei, for example, here with very low Z for N equals 28. So these are isotones and these are isotopes. the deviation tends to go up to maybe 2%, but over most of the range, it's 0.5%, and in many cases, much better than that. The curves on here, the green points, are one of these Skirm forces fitted to these nuclei. So the 14 parameters in that SV-BAS force were chosen to give a best fit to this group of nuclei. QMC2, in that case, the symmetry energy was fixed to be 30 MeV. In QMC1, it was just allowed to be within the range allowed. So there's slight variation between those two in how the nucleomatic properties were chosen. Now remember, we're comparing the green with the red or the blue, black, whatever it looks like to you, and the level of agreement is really pretty good across the entire periodic table. If you're interested in spin-orbit forces, the Skirm force, which again is fitted to these things, QMC and experiment, and quite often the QMC calculation is actually comparable. It's always comparable. If you look at charge densities, the red is the calculated, and the red is the experiment. The black is the QMC calculation. It sits on it really describes the electron scattering data quite well. If you look at deformations of nuclei, in some cases the Skirm force, SV-BAS, doesn't actually lead to deformation as you increase the number of neutrons. Which case is this? Damn, this is gadolinium. What's this? Sorry, I forgot. It must be zirconium. No. Sorry, I don't remember what this is. But you see, we run across the periodic table all the way up to plutonium. Again, the green is SV-BAS. The blue is a very complicated calculation designed to deal with the deformation of heavy nuclei. And the QMC calculations almost always lie between the Skirm force and FRDM. But in many cases, with the Skirm force, with its 14 parameters, does not lead to deformation. QMC does. If we look at super heavies, so this is nuclei with Z greater than 100, so it's Z along the bottom and neutron number along the top, the level of agreement is around the 0.1% level for QMC2. It really is tremendously accurate for the super heavy nuclei. So, those are new results. Hopefully we'll publish them in the next month or so. Let's put them on the archive. The effective force that led to those results for real nuclei, more than 100 across the entire periodic table, was derived starting at the quark level. And it's based upon the changes in the structure of the bound nuclei. It's got less parameters than the standard Skirm forces, but reproduces this data at a level comparable to them, and in some cases better. The force involves delta functions, that is, it's a local density-dependent interaction. It looks like standard nuclear physics, point-like nucleons interacting through some force. But it's derived from an underlying theory where the nucleon has structure, and that structure is changing in medium. That means that you not only can do nuclear structure, but you can calculate the changes of structure functions in a medium. You can calculate the changes of form factors in a medium. And so the last part of the talk, I'll remind you of the EMC effect. I'll remind you that in a theory, in a version of this theory based not on the Bag model, but exactly the same idea, the scalar field leads to a modification of the structure of the nucleon in medium. In this case, you take the NJL model, so a covariant model, you can more reliably calculate structure functions with that than with the MIT Bag. So you start with this covariant chiral symmetric theory, fully relativistic. You solve for the structure functions in nuclei, and it reproduces the EMC effect. This is labeled boron 11 for a reason I'll tell you about in a minute, but the data is carbon 12 and the prediction is the EMC prediction, and also for aluminium 27. The reason I've shown this is that there's a prediction that hopefully will be tested at 12 GeV at JLab. It has to be tested. And that's the prediction that the EMC effect for spin is twice as big. And this is related, so the red is the predicted EMC effect for the spin-dependent structure function, G1, for these nuclei. Now, because of that usually involves just one nucleon, it's a smaller effect, but nevertheless, it's an absolutely smaller effect, but in relative terms, it's twice as big or more. This really has to be tested. It's a prediction that's been there for 8 years already. One of the problems in doing this physics is the time lag between when you actually think of something and when it can actually be tested. Another way to test this, and this is related to NUTEF and the flavor dependence of the EMC effect, the so-called isovector EMC effect. There's some very interesting things to do there with parity violation in nuclei, and comparing the EMC effect with photons and in a parity violating experiment. That is gammas in the structure function. I've talked about these, Ian Chloe has talked about these, you've heard it, and hopefully it will be done. I've just put it there to remind you that it actually has to be done here. And let me that actually started again almost 20 years ago, but we're hopeful that we'll have experimental results very soon. Is Zinedine here? No. Hopefully he's writing a paper. So if we go back to 1998, there was a suggestion by people like Stefan Straub that he could measure the modification of the ratio GE over GM in nuclei. And within QMC, there were predictions. This was 1998, it's hidden on the bottom. And then when the experiment was done, indeed, the predictions of 1998, which were the red curves, described the data reasonably well. But the interpretation of that met some, it upset some people, and there was a little bit of controversy about the interpretation of that experiment. So what I want to focus on in the last couple of minutes is another experiment, another approach to measuring the change of the form factors of a bound nucleon, and that's to look at the response functions in electron scattering. Once again, back in 1999, we had predictions for the effect of the modification of the longitudinal response in E primed for basically free structure functions and the structure function in medium. A very significant change in the response function predicted. Some 6 years later, Bentz and one of his students redid the calculation. This was in the bag, this is in NJL, and they also found a similar reduction in the response function in nuclear matter because of the modification of the form factor of bound nuclei. And the calculations I'll show you now, hopefully will be on the archive this week. They were prompted by this experiment by Chen, Choi, Metziani, and collaborators. These are the spokespersons. And they proposed to do a very accurate, systematic study of the response functions of nuclei here at JLab, and they did it. And they finished the experiment some 5 years ago, and there's just finishing the analysis of that data. And we wait with great anticipation to see that data. What I'll show you, the last couple of curves, are predictions for these experiments using the NJL model with the nucleon structure self-consistently modified by the scalar field that's generated by those nucleons. It's the same model that describes the free nucleon form factors, structure functions, and EMC effect that I reminded you of before. For the free nucleon form factors, you can look at this. What's shown here is, this is the free nucleon structure function in the model, the blue. The red is the predicted modification of F1 of the proton, and this is F2 for the proton. You see the agreement with the experiment for F2 for the free structure, for the free form factor is a little better, but this is still quite good for a model that wasn't fit for that. It's the same model I showed you before, and a prediction for F1P. And the red is the modification of the structure function F2 in medium. What we're trying to measure is this response function RL in inelastic electron scattering. The RPA includes some in this series, including correlations, including omega exchange. So the calculation, the RPA calculation, has short-range correlations in there, as well as, of course, some long-range. The calculations show the case where the nucleon structure, this is for nuclear matter, at nuclear matter density. The calculation dotted is Hartree, so just this diagram. The dashed is the RPA. There's a little bit of repulsion associated with the RPA, but the change is not great. At nuclear matter density, this dashed curve in green becomes the red curve. There's a very significant reduction in this response function in the quasi-free peak, as you would expect if the electromagnetic form factors are modified. The change is also there when the magnitude of the 3 momentum is 800 MeV over C. This is the last results curve that I'll show you. It's complicated. What we see is the free Hartree result, and the free RPA is the green. These points are the Green's function Monte Carlo calculation for carbon-12 that was recently published. You notice this, and this is for the Coulomb sum rule. So it's the integral of the response function at a given 3 momentum Q divided by the nucleon form factors weighted by Z and N. At large Q, in a non-relativistic calculation, this is expected to go to 1, and you see, in fact, the Green's function Monte Carlo, which is non-relativistic, does head to 1. In our calculation, which is fully relativistic, in fact, the asymptotic value is well below 1 because of those relativistic effects. And you see it's quite a bit below the Green function Monte Carlo. For carbon-12, a nuclear matter, which according to Ernie Moniz, so nobody here can challenge that, corresponds to carbon-12. This is the Coulomb sum rule for carbon-12. The yellow is data, so that should be compared either with the Green function Monte Carlo or with our calculation. Clearly at the higher Q, this point is compatible with both, and hopefully this will be resolved by the data that's about to be published from JLab. For lead, the data is shown here. The red is the calculation of, in this model, with the modified nuclear form factor, the nucleon structure modified in medium. We really look forward to seeing that data is from Morgenstern and Metziani a long time ago. We look forward to seeing the new, much more accurate data. But clearly, the difference between calculations where the nucleon structure does not change and calculations where the nucleon structure changes are dramatically different. This is a fundamental experiment. The results of this experiment are extremely important for our understanding of nuclear structure. So, to summarize, give Haiyan some relief, relativity is essential. The intermediate range attraction in the NN force is a strong scalar that modifies the intrinsic structure of a bound nucleon. It leads to a profound change in our understanding of the shell model. What occupies those orbitals are not free nucleons. They're quasi-particles with nucleon quantum numbers whose internal structure is modified. The scalar polarizability arises naturally in such a theory. It gives rise to saturation because of effective three-body forces that have a clear physical interpretation. The derived density-dependent effective force gives results as good as or better than most phenomenological Stern forces. The new results I showed you are that the initial systematic study of finite nuclei across the periodic table typically agree with binding energies within 5%, at least on the scale comparable to the best phenomenological Stern forces, with many times the number of parameters. The super heavies are especially good, typically better than 0.25%. Deformation, spin orbit splitting, and charge distributions all look good. They won't fit just the binding energies. And we, as I tried to explain to you, we eagerly await new data, particularly the data that was taken here more than 5 years ago on response functions in the Coulomb-Summer rule. And from 12 GeV at JLab, the isovector EMC effect, spin EMC effect, and so on. Some credits to the people involved in this. This idea started with Pierre Guichon. Koichi Saito, Tsushima were critical in developing the theory, along with Pierre and I. And more recently, Vance and Chloe have been vital in these NJL calculations. Thank you.
Thank you very much for the nice talk. Question,
Can you shout?
please.
In year 90, we observed evidence for very strong modification of excited nucleon state property in nuclear media. In particular, resonance of second and third resonance region, clearly seen as a peak of product, almost disappear in total photoabsorption cross-section of all atomic nuclei from carbon to uranium. Effect is extremely pronounced and far beyond the Fermi motion if we take into account Fermi motion. In order to reproduce experimental data numerically, we should increase resonance decay width by factor 3 and 4. So it's huge effect. It is very attractive to relate this effect to influence of scalar field you explain us, which can change coupling between chords. My question is, do you see any opportunity to compute modification of excited nucleon state, photocoupling, hadronic coupling, Q-square evolution of electrocoupling within the framework of this concept of scalar field inside atomic nuclei?
Simple answer, yes. There's been some initial work done by Kazuo Tsushima and collaborators. But yes, there's a lot of work to be done. And maybe you can tell me a little more, give me the references for that.
I don't understand how you avoid challenges from the relativistic dynamics of the bag or quantizing the bag shape when you have 2 or 3 interacting nuclei. You just say, the bag and mean field and I'm done.
No, the assumption is that you're at a density which is low enough that the nucleons are not overlapping enormously. Now, to some extent, the omega repulsion suppresses things at those short distances. But you're right. I mean, you know, back in the early days, people tried the really hard job of taking 2 nucleons made of quarks, letting them overlap and trying to solve that. That's really hard. And really, very little came out of that, I think, except that the wave functions in the colorless channels, the wave function suppressed at short distance. There's some non-zero colored components in the wave function. But really, you could not tackle nuclear structure in that approach. I think the progress with real nuclear structure here is something that was never thought of in those approaches.
So I was wondering whether you can use this technique for higher densities with neutron stars.
Yeah, yes. The advantage is that if you make the working hypothesis that rho, sigma, and omega don't couple with strange quarks, cycle type assumption, then you have no new parameters. You can calculate lambda hypernuclei and cascade hypernuclei. That's all been done. That was done 15 years ago. Cascade hypernuclei should be bound by about 15 MeV in heavy, in calcium, iron. Cascade should be bound by 15 MeV. So when you come to dense matter, where beta decay is allowed on the timescale of 10 to the minus 9 seconds, so you can convert neutrons to hyperons, you naturally get the hyperon-nucleon forces. The hyperon-nucleon-nucleon 3-body forces are all given in this approach with no new parameters. And so we've done that 2 years before the group in Virginia found the 1.94 solar mass star. We have maximum mass over 2 solar masses. That article reported that their data ruled out equations of state with hyperons, notwithstanding, it was in Nature, notwithstanding the fact that 2 years before there's a publication showing masses at that time with hyperons. Nature doesn't publish errata.
Any other question? If not, let's thank Monique and also.
So can I please remind you that the International Nuclear Physics Conference is in Adelaide in September next year, and I would love to see you and many of your friends there. I realize some of you want to get coffee. For anyone who wants to watch, here's a taste of Adelaide.
So, okay, we are also running 10 minutes late. It's all my fault. And before we are coming back and reconvene at 10:40.
at the back, somebody wave. Nobody wave. So, okay. What I'd like to do is to work through these aspects of the lab. I should say this tends to be a bit of a hodgepodge of the speech because your Bob takes the physics and Ryan takes the 12 GB upgrade, and of course you guys are talking about all the really nice stuff. But I'll try and give you a picture of what I see as the status of the lab. So this is the slide we'll use next week when we brief the Office of Science on the strategy for the lab. You see that the total budget costed dollars during 2014 was about $150 million. This continues to be completely dominated by the nuclear physics piece. The other aspects shown on our transparency, you're of course familiar with. We have a very strong user group that's evident by the attendance here, and of course we mentioned later some of the aspects of the science education. The safety record over the course of the last year has been excellent. We're hitting the mark in terms of the numbers, in terms of the total recordable cases, and in terms of those cases that lead to people being away from work. But as usual, with the low statistics, if you saw a big number, you'd say, well, it's false. And in this case, getting zero in some instances there actually masks a couple of near misses that were quite important. There was one subcontractor working on rerouting a feeder, which turned out to be live, and everything was done correctly in terms of protection, but nevertheless it was quite made me very nervous. So we enjoyed awards. So we have two local members of staff who became APS Fellows this year. We also have a couple of user early career awards. We kind of claim them because they're bridge appointments, and they've spent time here, which was left us very recently. So we're very pleased when we see that kind of thing. In the science education, Lisa Searles Law also received an award. And the picture there is the poster session after last year's summer student sessions. And the one on the left, I don't know whether you know, but we host the science bowls, both the middle school and the high school science bowls here, and then help run the National Science Bowl. And the perennial winners in Virginia are at Thomas Jefferson High School, and this year they also won the national competition. I mentioned earlier that we have a large active user group. This is transparency first put together by Patricia Rossi that gives you a picture of the actual international character. You see France and Italy are vying to be leaders, but there are not insignificant pieces from a number of other countries. So from my point of view, this aspect of this laboratory is one of the pleasing aspects. And I'll come back to the contributions in a couple of slides. The 12 GB upgrade project is, for a while this was caused by lack of sleep. We had some challenges with the magnets. Over the course of the last year, things have gone very well indeed. I don't want to queer the situation, but touch wood, we're on a very good track now. We had an excellent review in March. They were very complimentary. Some people who were students of this said they'd not seen such a complimentary review from PA for a very long time. At the time we had an ETC of $26 million. We've done, since that time, which was March, we've done about $4 million in progress. Not to steal Glenn's thunder, but the accelerator that's done, the whole beamline that from our point of view they're done. Civil construction is very, very close doing the last of the air conditioning, and we're at the point of 85% in halls B and C. The scientific capabilities in the different halls continue to match the story that they're complementary. Of course, it's known that Class 12 will have a shot at doing some spectroscopy, so Hall D won't have everything to its own way, and there are pieces of competition in other areas. But by and large, we benefit from having a complementary set of equipment here, and it, in my opinion, enriches the scientific program. One of the most spectacular recent photographs is the one on the left there, which shows you, and you might try and pick them out. There are 4 coils of the torus, the new torus installed in the hall. The other 2 required to make the magnet are in the process of being fitted in their cryostats. A 7th one of us spare is here, and the 8th is to arrive soon. So very good progress there, and also nice to see is the SVT is almost complete and good progress with the HTCC. So already showing very nicely. In Hall C, it's dominated by the SHLS, and there we have Q1 accepted, operated at 110%. You see also there that the yellow beast on the left is in fact the HB magnet, the horizontal band, which came from Michigan State. The 3 outstanding magnets, which I expect Glenn will give you some detail on, are the dipole and Q2, Q3 in France, and there also the technical progress is very, very good. They're a tad behind the schedule, but the technical progress is very good. I should mention that we've also got going with the solenoid in Hall B, 2 coils, second coil partially done. The CBAF, you had a very nice talk from Freiberger yesterday. He doesn't spare you any of the pain that he and his team go through in achieving what turns out to be very beautiful. I don't know whether you noticed, but he just happened to mention that for HPS they were threading the beam through a 1 millimeter hole. Right? That's remarkable. Any idiot that would put silicon 1 millimeter from the beam, once its head seen, that's the story that I would have given you before this happened. So.
Half a millimeter.
Sorry, you're right, half a millimeter. 1 millimeter is 2 times half. Okay, but the commissioning went very well in the fall. It seemed a little ratty during the spring, but nevertheless, I think pulled some physics out of it. And Hall D already at that stage in the fall was showing reconstruction of multi-particle stakes. There are some prettier pictures available now, of course, and some have already been shown. I mentioned the user community and its diversity in terms of nationality, but in terms of funding agency, that allows you to bring in also NSF and also to think in terms of HEP as well as the Office of Nuclear Physics. And this is a list, a rather impressive list of the stuff beyond the 12 GV formal project, which has been contributed by the user community here at JLab. It's really a remarkable list. You see all the contributing pieces of the world. Okay, so where does this leave us? This is what we're attempting to make. We're attempting to do, as we did last year, a 3-year schedule, which we don't change during the course of the year. Of course, if things go dramatically badly, then we would do it. But the idea is to give a picture at a fairly high level of the strategy for running the machine for physics or whatever. So what you see is that the incidence of blue, which is, if you like, operational beam for physics, is coming to be almost complete in 2017. On the left, we were in green, which was the code for commissioning. I note that, and the term was used yesterday by Arndt, the term opportunistic physics. This is a term that we use because if we promise physics, and nuclear physics in DOE understands that we promise physics, then it promises physics to its OMB beam counters, and we get charged if we don't deliver it. And at this stage, with a machine that is as young as it is, and with us still trying to do 12 GeV upgrade work, sometimes in the same hall as we're trying to run physics, then it makes no sense for us to claim that we will indeed, promise to deliver a certain amount of beam. Nevertheless, the goal is to do our best to do so. I understand that kind of thinking causes you to be a little schizophrenic, but really it's a significant strength if you can get to that position, certainly for lab management. Okay, the ability that we have to deliver on the kind of operations that I'm showing, of course, depends on us getting a budget. And in FY14, when we did the budget presentation following guidance to the Department of Energy, nuclear physics, we were very depressed because they were showing very weak running even in the output. So 17 was showing 25 weeks or less, or something like that. So we were rather depressed then. When we got guidance this year, it was significantly better, more like 27 plus. And so we were buoyed by that aspect. However, it's still true that the number that we got for FY16 was still small, and in our opinion, inadequate. So our job was to try and go and persuade the people who control the budgets to increase it. And of course, in this process, it's not done in a vacuum. I get to talk with June Gibbs from Brookhaven, with Bob Redwine from MIT, who is prominent in the DNP funding committee, and with the director at DEFRA, who's changed from Conrad Gelvin to Thomas Glassmacher. So we talk and we try and work out whether or not we can go and represent the field with a common message or not. And at the turn of the year, we managed, for example, to get 6 senators to sign a letter supporting nuclear physics. So we do a little bit of good, we think, but nevertheless, it's hard work, and sometimes good things happening, sometimes not. So what happened in the earlier part of the spring was that the House marked up the President's request. And the Office of Science was about $200 million under the President's request. The Office of Nuclear Physics was only $8 million under the request, which in the context was very good. And the number we got for operations was at the President's budget request. So if you like, that was we were pretty pleased with that. And the language there also is exactly what we would have liked to have been said if we tried to write it ourselves. That they like the physics we're doing, they like the operating, they want to operate the machine. That's all a very, very good message. We would still have liked to have $8 million more, and that's not the $8 million that Tim would have liked to have had. But still, this was somewhat encouraging. But then, we've actually, this is a little frustrating. We've actually, over the course of the last 4 years, had very good response from the Senate. We thought we had that trip, lined up. But people change, and of course the Senate went from being a Democrat operation to being a Republican operation, but maybe more importantly, a lead staffer changed his job. And so we got this markup from the Senate last week. You see that, first of all, it's as brief as you can be on nuclear physics, and the only, and you know that there's no mention of Jefferson now. So we thought we'd done better than expected with the House. We think we've done worse than we expected with the Senate. So there will be more work to do. Unfortunately, I'll get to go and spend more time in DC. Okay, we are working right now on developing, not developing, but in working a presentation for the Office of Science. We go in every year in June to present the plans for the lab to the Office of Science, and in particular this year there is a little emphasis on infrastructure, and so we'll give if you like, a rundown of the state of the facilities that we have and the plans we have for improving them. This is a fairly interactive process now. The way we get money to improve infrastructure is multiple. We get a couple $1 million in what's called GPP, General Plant projects. A couple $1 million from the Office of Nuclear Physics each year, and then, for example, the TEDF project was $70 million, $72 million from the Science Lab infrastructure pool. This year, so as a result of the involvement of the Office of Nuclear Physics, we've given them a briefing on what we intend to say, and then there are interactions, and one thing where we've been working hard but not making terribly much progress is on improving the end station refrigerator situation. And we were very pleased a couple of days ago when we heard that the Office of Nuclear Physics has supported, in discussions with the Office of Science, has supported the advancement of that in the SLI program. So that's not to say we're sure to get it, but it means we're in the competition, and that kind of extra boost, essentially from outside of our normal operating budget would be a very good thing to get. But the other thing you see on that transparency is the figure 8. We have, if you like, tried to reserve an oval tranche of land, which would require the city to provide that land to the Department of Energy if we were to be building an electron ion collider. So, as you know, the lab is built partially on the Yorktown Formation, and so, but we're not sure of the extent of that nice formation. For example, the TEDF building required 320 piles to support it. So, you know, crudely speaking, what we would like to do is to look into the land that we would be using to build an electron ion collider and to check it out, do due diligence on its suitability for building. And so we put in a request. It's varied over time, but we were approved for $3.7 million for site studies with a small amount to support the person to move forward on the electron ion collider. This coming from the Commonwealth. There was a lot of interesting language when the governor gave his speech on this, because he started making noises which made me nervous for my job about how he was not going to let any New Yorkers come down here and take away our project. But from a certain point of view, it's great. We're getting support. From another point of view, if you pull the tail of the big guy, then you've got to be careful. So some of the other things beyond the nuclear physics which go on at the lab, we saw that we've got a magnet from Ecuador. We are helping them with their cryogenics and also with some fabrication of some cryo modules, with the engineering of that. We're in a very big collaboration on LCRS-2. That's a new LINAC at SLAC 4GeV of superconducting LINAC for free electron laser work for the Office of Basic Energy Sciences. As I said, the LINAC is 4GeV. We're responsible for 2GeV of that in terms of cryo modules, but we're also responsible for the development and a lot of the procurement of the cryogenic system. So these are things which need managing. We're also trying to be involved with the Accelerator R&D Stewardship Program, which comes out of the Office of HEP, but which allegedly is meant to be a much broader program. And we got some seed money to if you like, advertise the possibilities. And there was a meeting in conjunction with IPAC 15 in Richmond a few weeks ago, which went along these lines. I guess that actually reminds me that I have not said anything about, not got anything more in the transparencies that address IPAC 15. But it turns out that over the course of the last few months, we're fairly prominent in discussions about accelerators, about the future of physics. We hosted the International Committee of Future Accelerators, that's the HEP side of the house in February. A lot of lab directors came for that. We're hosting in the Sura headquarters next week in 2 days. The meetings of WG9 and C12, the nuclear physics pieces of IUPAC. And then, just to top it off, there were 1,200 people at the IPAC International Particle Accelerator Conference in Richmond a few weeks ago, which we hosted. By all accounts, it was a major success. And we also got some political attention because Senator Warner was at the open reception, and Secretary Holton, the Commonwealth Secretary of education was in the open session of the conference program. Okay, so let me move on quickly. As you know, we have a second accelerator in the laboratory. We've been calling it, to everybody except myself, their dismay, we call it, as an interim move, the low energy recirculating facility. We've been looking at the plans, trying to make plans for using that. A year ago in the summer, we had a visit from the Office of Nuclear Physics. In discussions which followed, which involved NSF, because they are providing funding for the dark light experiment, which is an approved experiment in the lab. We had discussions with the Office of Nuclear Physics about how we might operate that device. And there is an agreement that there is, in principle, nothing against the Jefferson Lab operating funds being used for that. Of course, whether or not that makes sense depends on us actually having operating funds, and there's weighing that against the rest of the program. But nevertheless, it's an important step forward that the process, the possibility exists. And of course, we're working with Darklight, we're working with NSF on the development of their equipment. So there are other things, accelerator R&D, FEL used for lithography. We had a retreat led by Bob McEwen, which looked at these, and we see the ones which got some traction, if you like, they're above the line, and then the ones that got less traction at that time below the line. The low energy nuclear physics program is an interesting one, especially given the long range plan, and we didn't want to in any way confuse the situation as to what Jefferson Lab was interested in. But it's clear that there are workshops around the world that there's traction in minds, so it's clear that that's a discussion that won't stop now. So we started a couple of years ago a lab-directed research and development program. It's a modest program. The Commission on National Labs, when they visited here, they were shocked because they come from, they were looking at the NNSA labs, which would like to have 8% of their budget used on LDRD. It's a complicated, multi-year discussion about this. Once upon a time, LDRD was not permitted at single-purpose labs. We have instigated a program in conjunction, in consultation with the Office of Nuclear Physics, and you see there the three projects that got approval in the first year and made good progress. In the second year, we have the three programs from the first year continuing, and then three new ones were added. And the total funding is about 800K. Now that's kind of what we're starting off with is the sustainable level. And it turns out that the way the project falls, there will only be 100,000 carried over into next year. So we're on track for doing that. But we're going to look at how well it goes and see whether we're at the right level or whether we should be thinking of increasing it. But you see that the projects that are up there are actually extremely germane to our basic physics program, and they add a bit of excitement to the game. As you likely have picked up, there's work going on around us. Some of that is to do with the purely commercial development. Some of it is to do with the idea of a tech center. This is coming out of the Virginia Tech Foundation, which is attached to but separate from the university, and they are hoping to exploit the presence of Jefferson Lab to start a tech park, an R&D park, if you like. So, as as usual, I am going to show you some pictures of the local educational outreach program. But for his preparation for the long-range plan presentation, Rolf tried to bring up to date the picture of the influence of the lab on the nuclear physics education and sort of the PhDs at the top of the page, but also going into faculty positions. And you see that we always have difficulty in getting these numbers correct and checked out, and so Rolf worked in areas where he felt he could check out the numbers personally. But you see, no matter how you look at it, the influence of the lab on the university scene is very good. We hope that you appreciate that. So to the science education itself, we're very pleased to have something between 40 and 50 REU and SUNY students at the lab during the course of the summer. It's really good to have an increased number of young people around, and we think we do a pretty good job of hosting them, and judging by the poster sessions at the end of each summer, then certainly I'm always impressed by the quality of work they do, and that speaks well to the supervision they're getting. I think I try and tell them that they should expect to be given real work, not just make spend time work. We expect that the supervisors will really need their work product, and they seem to respond extremely well to this. So we're very pleased. And at a slightly less intense level, we're involved very strongly in the local school system. We have an evening in which 200 teachers come in and exchange ideas and equipment that is used for science education. And we bring in kids to visit with staff members and talk about how much they earn and why they're doing this and why would you like coming to work, and funny things like that. So let me finish. Basically, this is Bob McEwen's view of our laboratory, the laboratory for nuclear science, which he sold to Tim Holman, and Tim uses it, but apparently there is now a negotiation for an update, which Bob is working on. So in summary, I think that you should have heard me think that we've made excellent progress on the 12GU project, on the accelerated commissioning, on the BlueX commissioning, and on the Hall B and C detector and magnetic valve. On operations and funding, as far as we see it, the plans for 2017 plus are improved, but the response to the budget in 2016, the response by first of all, the President's budget and the two markups, it's clearly a mixed bag, and we need to work with that. We have this strengthening ancillary program with EFRID, LCLS2, and BRD, which I think rounds out the work we do around. And we are making very significant progress. UIM is the latest example of significant progress on improving our infrastructure in order to try and avoid the incidents that we had, like the impact of the power loss this year. So, thank you very much.
Thank you very much for the nice overview. Are there any questions? Can you shout?
I realized there might be questions, so I actually put my hearing aids in this morning so you can see how they work.
So Last evening, Art presented a very aggressive program for upgrades and repairs and moving forward with Accelerator over the summer. And then an aggressive plan for what the Accelerator wants to achieve in the fall. And I think it's absolutely critical that achieving the goals, specs of the Accelerator program for FY17 is the #1 priority. So I have an experiment on the floor in Hall A, and I'd love to have some data. I don't want to have a little bit of data that jeopardizes the full development of the Accelerator. So I think it's very important that we make sure that the Accelerator has the priority and not just trying to squeeze out a little bit of data.
Yeah, so I appreciate your comment, actually. You should be aware that we are pretty conscious of the tension that there is. It's probably 4 or 5 way, not just 2 way. For example, the most obvious region of tension this last few months was that we really needed to give emphasis to the building of the Taurus in Hall B. On the other hand, there was the opportunity to run an HBS, and so that situation we were very conscious of, and oh, by the way, that's the Taurus is also why there is no opportunistic physics actually advertised for next summer, because of what we imagine is going to be going on. It needs to have high priority. On the other hand, if you can manage things in a rational way, you can sometimes pull off gains. And so it might have seemed unlikely, but I think that you'll hear from me. I think the HBS told us this afternoon. I think you'll hear that they actually, I once told the lab director that there's no way you could do this. And they came up in the evening and ran until the morning and then shut down and did it again. And that with a little bit of management and cooperation, we can make more things happen. But you're absolutely right, Charles. We need to make sure that the completion of the accelerator is not just the completion of the KPPs for last summer.
Any other question or not? Okay, thank you, Mount. Let's move on to lab science. James of lab science.
Hear me okay?
No.
No? It's on. Hear it now? Okay. Okay, so I've got a selection of topics mostly related to the current and future nuclear physics program. I'll give you a few recent highlights. We'll discuss what's happening with the PAC, experimental equipment that's coming along, SBS and other enhancements beyond the 12 GeV project, the Muller and Solid projects, tell you what's going on with those, and of course, the future MEMC. So some highlights, I think you heard about this yesterday, a very nice result published in Science on short-range correlations in now heavier nuclei, and this has, of course, received quite a bit of attention. Particularly, it's quite interesting that it has implications both for equations of state of neutron stars, also atomic interactions in ultra-cold atomic gases. have results that reach out beyond just traditional nuclear physics. So I'm very happy to see that. This is the two-photon exchange experiment. Everybody associated with JLab, I think, knows this picture and the story behind it, the ratio of the electric to magnetic form factor of the proton, and the very nice polarized measurements that were done here. The interpretation of this difference, of course, has been two-photon exchange, and we just recently had a publication from the class two-photon exchange experiment where they used a comparison of positron to electron scattering and saw the expected behavior associated with the two-photon exchange. Seems to indicate that supports the interpretation of this difference here. And of course, there are other experiments. The Olympus experiment should be waiting in the near future as well, and hopefully further confirm this nice result. And in theory, we have lattice computations advanced. I think you may hear more about this afternoon. This is now a calculation of pi k scattering, including the inelastic channel k eta. And you can see the nice resonance structure of pi k, elastic, and then the inelastic channels also come out of calculation. And this is the first step towards calculating these inelastic channels, and is of course something we look forward to, calculations of transition backwards related to spectroscopy, UX, and so forth. So this is, lattice is marching on nicely in concert with our experimental program. We should have nice comparisons in the future. So you actually saw this, I think, from Ken Dix yesterday, and I think you'll hear more about it this afternoon. We're going to update maybe tomorrow, actually, update BlueX. But it nicely shows that they have, with a diamond radiator, they have a nice coherent Bremsstrahlung peak, and the rho production from that coherent Bremsstrahlung peak indeed shows the expected linear polarization transfer from the photon. So this is really quite a nice demonstration that the basic UX experiment is operating quite nicely. Okay, so this is the heavy photon search. This. You know that a lot of the motivation here, this is also positron to electron, actually positron to some electron positron in cosmic rays, and there's this anomalous rise at high energies, above 10 GeV. And I like to show this because it was recent data from the AMS on the International Space Station are really very beautiful data. And they continue to run, and one hopes that perhaps if this mechanism of dark matter annihilation is the correct explanation for these excess positrons, that one will see a drop when one reaches the energy associated with dark matter mass. So it's really quite interesting. But of course, if this is the correct mechanism, there is this intermediate boson called heavy photon, and one can try to observe these heavy photons in the laboratory, and that is indeed the goal of the HPS experiment, as well as dark light pink. That's in other areas of the lab. But the HPS experiment, of course, as Mark mentioned, completed its engineering run in the Ball B just a few weeks ago, and it's very nice. I think you'll hear more about this afternoon as well. Here's a nice graphic of the positron-electron-positron pairs, and the momentum of electrons and the momentum of the positrons. And so they actually have track pairs in their apparatus constructed. So we look forward to seeing further analysis and more results from that in the near future. This was something funded by the Office of High Energy Physics at DOE, construction of this experiment. So it's also a nice partnership with high energy physics. So turning to the PAC, we have now 70 total approved experiments. These are the topics and the different halls. We have 2 experiments that are not in any of the 4 experimental halls. One is the dark light experiment at Earth, and the other is the bubble chamber experiment for nuclear astrophysics, uses the injectable to AWB So these are the experiments, and as you know, we have now 4,400 packed days on the books, and this is, of course, we're very proud of the fact that it's great that this facility is so heavily subscribed. And as you know, we had to run a special PAC to pick out some high-impact experiments to run in the shorter term. And we did that. Seems to have settled down some of the concern that we had an unmanageable backlog of experiments. And so anyway, we still expect this continually grows, of course, and eventually we will have to get to the point where we need to implement some sort of jeopardy process, but we haven't started that yet. PAC membership, we had 4 retiring members at last year's meeting. Naomi Makins, of course, was a long-standing member, was the chair. We have some new members shown here that will be starting. And we have Jim Napolitano has agreed to be the chair of the PAC going forward. And look forward to working with him to running the meetings and getting the reports out in short orders. It's very interesting. Naomi was a wonderful chair, but it was a little difficult to get the report out. So here, of course, there's PAC 43. We had a call for proposals, and they were due in May, just a couple weeks ago. And this is the same charge we used for the last PAC, PAC 42. And there we received 8 new proposals, 2 run group additions, and 7 letters of intent. So we'll be meeting the week of July 6th to consider them. I think the run group, the handling of the run groups that we're using now seems to be working well. People seem to be adjusting to using this new system and taking advantage of actually the good things in it. So I'm glad that people are cooperating with that. That seems to be working right. So turning to the new equipment. Super Big Bite spectrometer for Hall A has been under construction for a couple of years now. They have somewhat of a ways to go. Here you can see the magnet, JLab, power supply, and here's some nice pictures of the polarized helium target, the helium-3 target that goes along with that, and the activity at the University of Virginia constructing the gem chambers is also moving along quite nicely. They've actually constructed 12, probably a few more now, before the gems, and passed the Q&A test. So that these gem chambers were, I think, part of the most concerning part of the project from the point of view of being able to use, and it actually seems to be going well. Okay, future projects. Of course, there's the Muller experiment, and this is a possible major item of equipment with the Department of Energy that we've been discussing with them for some time. And maybe if this were 17 start, it's still possible, we're hoping. This is a high precision standard model test, as you probably know. The Department of Energy ran a science review in September of last year, and the experiment received strong endorsement from them. So we're trying to look ahead now to a technical cost and schedule review. We'll probably do this as a lab-run director's review first, and try to get both the collaboration ready and whet DOE's appetite for running the actual DOE version of that review that's necessary, of course, to establish it as a project. And so we're trying to put that on maybe this fall. For solid, this is something that involves a substantial collaboration from China. It uses the Clio solenoid, and we have an agreement with Cornell to move the Clio solenoid here, and the details of that are being worked out. We can expect it to be here sometime in the next year or two. We ran a director's review back in February of the solid experiment, and we got lots of good feedback, and the collaboration is working on their pre-CDR to strengthen it with the feedback Doc for this review. And we look forward to discussing that in the future once we have this PCDR finished, discussing it with the Department of Energy a little more seriously about how to move it ahead as a project. Probably will start sometime later in this time frame, as we say at this point. These, of course, are MIE projects are related to the NSAC process as well, because in fact, Tim Holman himself makes the statement that when he started in his position as the Associate Director for Nuclear Physics, there were 4 of these MIE projects in the nuclear physics program. Today, there were 0. So the squeeze on the budget to keep facilities running, to keep research budgets going, and so forth, has squeezed out these kinds of projects. And in fact, Pat Daner introduces it when she talks about the Office of Science budget. She talks about how many MIEs there are in high energy physics and how many there are in EES, and then points out, well, gee, nuclear physics doesn't have any. She knows why. So this is a problem for the field, and is one of the reasons it's difficult for us to get these 2 projects started. We're hoping that with a little support from the NSAC long-range plan that we will start to try to begin this program to do some of these kinds of projects, so that they help free up some money for these 2 in particular. I think from what I can tell, certainly in the town meetings and so forth, but from what I heard from the long-range plan working group, these 2 projects were very well received. The science was very well received, so I think they would have good words in the long-range plan document. So let's come to the electron ion collider. As you know, it was on one of the slides with Mont that we have this figure 8 concept, and this really is optimized for ion polarization, particularly in the polarized deuterons. Luminosity up to about 10 to the 34, and our design has what's called low technical risk. Okay, basically it uses established technology. Sometimes pushed a little bit beyond, but it's pretty much established technology, so there's a lot of confidence that you could actually build this. It's upgradable to higher energies as well, 250 jet protons, 20 jet electrons. We think there's an advantage in the fact that there's a flexible time frame for construction. Construction of this is not tied to anything else on the site, so we can continue to operate the 12 GeV fixed target program while construction goes on. And in fact, since we're so happily running along, doing our physics program with the 12 GeV machine here, there's actually no preferred time frame. There's no urgency to get this started. So the project can start whenever the budget cycles can accommodate it. So we think that this flexibility is a very important part of our proposal. As was mentioned by Don Giesemann yesterday, we completed a cost estimate and presented it to the NSAC team. And I'll tell you a little about that later. And we also, as part of that, had to address the issue of operations. We think that this machine will have fairly cost-effective operations. I'll bring that into the discussion later as well. These parameters, which were agreed upon in establishing the white paper and jointly with the Brookhaven community, these parameters are in fact fulfill the white paper requirements. And current activities involve site evaluation, as Mark mentioned, Virginia Funds, accelerator and detector R&D, design optimization, and cost reduction. So baseline design that we presented to the committee back in January is shown here. It is the figure 8 as we've had for some time, but with some changes. We made the ring larger and made the ring larger with the idea that we could reuse PEP2 magnets from SLAC and the RF and the vacuum chambers that go with it. It saves considerable funds. So even though a larger tunnel costs more money, we save a lot of money here, and it's trade-off incentives. This is really a much better way to go. The iron, and we're in a much better position to upgrade in the future, of course, having already built the tunnel to the large ratings. The iron collider ring will use new design of superferric magnets, which are superconducting magnets that use iron, saturated iron, to shape the field. And these are magnets that need some R&D, and so there's a group at Texas A&M that is indeed planning to do some prototyping of these magnets. So this is an important thing that we need to demonstrate before we build this device. Superferric magnets have been built before, but this particular design is somewhat different, so we need to actually get a prototype going. And the SRF LINAC for the iron injector is something that oscillated for a while between a normal conducting and a superconducting machine. Turns out that we think the superconducting is actually correct. So this is the charge to the cost review. You can see that they were asked to provide NSAC with their best current estimate of the costs of the projects, including R&D, construction, operating, and detector. So this is what's called the total project cost, TPC. So we had to address all of these items, which were quite an ambitious exercise for us. And there are other statements here, but this had to be presented all in FY 2015 dollars. We could choose staging options to implement a use of science goals, consider those as well. And so this was all done at a rather rapid time scale in order to provide input to the long-range plan process. And so it was quite an effort to put this together. Lee Harwood, most of you know him here from the lab. Accelerator construction is now commissioning. The accelerator construction for the 12 GV upgrade is completed, and Lee was in charge of that, and now has some time to help us with this EIC cost estimate. And he put a lot of effort into this, and it really turned out to be quite successful. Very grateful to Lee for his efforts on this. So here's what it looked like at what's called level 2 of the project. And you can see that most of the scope is in the accelerator, $700 million here. This is the contingency. Conventional facilities. So, of course, you need to construct a configuration tunnel. Okay. All of that, plus the buildings, cost with contingency $250 million. So that's a substantial chunk of funds right there. This is integrated commissioning and then management of the project and so forth. So the total scope for the accelerator, including contingency, came out to be almost $1.3 billion. Very expensive. Experimental systems, this comes out to be $180 million. So it's 188. And so when you add these two together, you get pretty close to $1.5 billion. So this was the cost estimate that we presented. How did it come out? So this is actually the summary slide that Ed Temple, chair of the committee, showed to NSAC when he presented the results of the cost review to NSAC. By the way, the cost review report from this committee, there is a full report, which has not been made public yet, but it is final. And I talked to Don yesterday, and we'll get it on the NSAC site. Public to read the whole document. So for ERIC, which is the Brookhaven design, they said it incorporates certain technical advances which are beyond state of the art. The 31% contingency that they had, in the opinion of the committee, is sufficient. For MEIC, our design was based largely on conventional technology with fewer technical risks. Proposed 35% contingency is marginally sufficient. And they concluded, based on our estimate, that an EIC could be built for about $1.5 billion in FY 15. The Brookhaven design was presented, it came out to be a little less than $1 billion, close to $1 billion. And but the committee had no And so these extra technical risks would represent a very big uncertainty of the cost. And so they really couldn't say anything about how much the E-RIC would actually cost. They thought it would probably be more than $1 billion, but they had no basis for another estimate what Brookhaven had presented. And so then they talked about how the total long project cost may potentially be reduced as technical risk is retired by off-project funds, especially for detectors from international sources, redirection of operating funds of the host laboratory, or by reducing the design requirements. So we're looking at these things as we go along. So I think this was a pretty good result for us in that they did pretty much endorse our design as a workable design, and that the cost was reasonable. So I think we came through this in very good shape. Very grateful to everyone around the lab that helped me with this cost estimate. It was really quite a good effort. One of the things that I presented to the Temple Committee at the end, so we were a little concerned that the NSAC people would get sticker shock with $1.5 billion. So tried to do a little bit more on this. So here was our TPC without detector, with the detector, and there's the operations budget would have been $117 million per year. So if you consider 15 years of operations, which pretty much is what you would need to cover what's in White Paper, for example, you would have $1.76 billion in operations. And if you add these two up over a period of perhaps as much as 25 years, which is going to take 10 years to construct, you get $3.24 billion. And if you assume that the nuclear physics budget is constant effort over that 25-year period, this would represent about 20% of the anticipated nuclear physics budget during that period. Okay. Not evenly spread out necessarily, but 20%. Presently, CBAF operations is about 16% of the nuclear physics budget. And presently, the RIC operation is around 28% of the nuclear physics budget. So 20% of the nuclear physics budget shouldn't be too much of a frightening prospect. Should be able to actually do this. And we did another calculation. We took the CBAF 6GeV construction, added the ops from 96 to 2014. That comes out to be just about $3 billion in FY15 dollars. So it's not so different from what we've done before. I think if you did this calculation for RIC, we'd probably be substantially higher, for example. So we think the nuclear physics could manage the scale, and we're hoping that NSAC. So, future EIC activities. There is a poetic workshop in France in the beginning of September. I think it's important that our community remain as active as possible in the EIC community. MEIC collaboration meeting. This is just being started to get together now as a collaboration meeting. Accelerator side of MEIC held a collaboration meeting in March, and we were busy we had an EIC user meeting at the same time, so they held a very successful collaboration meeting of the accelerator people. They had people collaborating from Oregon, Slack, and other laboratories, and the Texas A&M people were there and so forth. So they were talking about doing it again. What we'd like to do is bring together the accelerator and the physics part of MEIC and have a collaboration meeting in the fall. So just a heads up, I think we're doing that. There will be an EIC user meeting, which is joint with the E-RIC community, late in 2015. Still talking about when and where that will be. We're also thinking, North End has brought up the idea that 3 or 4 years ago there were a series of user workshops covering the EIC physics topics that were organized by JLab user community. We think maybe it's a good idea to restart that process and get some more workshops going. And so we look forward to discussing that with you, maybe with board of directors this evening. So, okay, so in summary, physics output from 6JLab is healthy. You see some really nice, important results coming out. We know there are more in the queue. We see preliminary results from one experiment that's very exciting. We're anticipating some other results coming out in the next few months. Experiments on the floor have done very well. SBS is making good progress. We're trying to move Muller and solid along. The EIC science and designs are making good progress, and we're awaiting results of the long-range plan. So that's all I have. If you have any questions, I'm happy to try to answer them.
Thank you very much. Are there any questions? Such a wonderful job, so no questions. That's great. Okay, let's move on to the last part of the session. I will Young about boundary experiment.
Okay, so this is a quick run through on 12JLab. You're going to recognize some of this, in addition to the canonical new front slide that we use. We're in the last throes of the project. We have about 6% of the total dollar value to go. As far as the accelerator, you heard at length yesterday from Martin about that part is done, and there's in fact an official gatekeeper piece you have to go through to keep performance parameter. It is done. There's also Hall B up and running, so I'll have a few slides about that. Then the last bit of civil construction, which is air conditioning in the tunnel, so if things will be more reasonable in the summer, is down to the last couple of percent, and then I'll spend about the last third of the talk talking about finishing up the upgrades in halls B and C, which are the last pieces we have to do. If you look at, just a quick reminder of what we're trying to do from the experimental hall side point of view. We've got 3 new experiments, apparatus, if you will, to get in. There's a near complete rebuild of what was in Hall B, not quite. We retained the 40 calorimeter, for example. Hall D, of course, was green field when we started. That's completely from scratch. Keeping with that, we have a somewhat venerable magnet in it. And Hall C, this is a view shot. Almost looks finished if you look at it until you start looking at it carefully. The new SHMS spectrometer that's going in, and that's the engineer's view, and of course this is the reality if you want to get down and see it. Hall A, we didn't do quite so much from the detector side. We did upgrade the polarimeters, and so they got to get up and get running somewhat early. Bob discussed at length, of course, some long-term plans involving Muller and also long-term solid to go in there. In terms of what we have to do for the machine, there's certain definite things we have to run through. 5.5 pass machine had to be in. Published date, if you will, was December of last year. We actually did it by June. We had to show we have beam lines capable of 11 JEV going over to A, B, and C, and then one capable of 12 going up to the Tiger area on D. That's all was done last spring. The machine then had to be commissioned on one pass, taking at least a couple of nanoamps, 2.2 GeV, no cheating. You have to get 2 JEV once around the machine. That was done, in fact, in February. And then the civil construction had to put out the hall, counting house, space for CHL2, and so on. That actually, except for the tunnel air conditioning, was done back in June. So CD4A, the formal statement, was given back in July, which means the accelerator part is finished. Operations can start, and Lauren told you yesterday how all that went. The particular part I show you here is getting the beam up to the Hall B tagger. This is the beam line coming from the machine going up the ramp. This is a picture of the tagger deliberately taken back when it was still under construction, partly because I wanted to have one that showed you where the electrons end up down there, old green steel. Photons head forward, and there's a few shots coming around R10, 5.5 past beam, then a 10.5 jab, and then actually into the tagger dump, which dedicated crew you see happened just before midnight back in May of last year. If you then go on and look what's over in the hall, they're finished. This is a couple shots of the magnet, the large barrel calorimeter that Regina built for us. You can now just sort of see the tail end of it, including electronic loops. The forward drift chamber is shown there inside the bore. The forward calorimeter Indiana brought in is shown here together at the time of flag wall, which is shown there in the tail. And then the central drift chamber, which is the upstream part of the tracking, the drift tube side sawtooth part of it is shown there, and a start counter in the middle. If you then come to what we had to do to convince DOE that we had something running, there's a set of what are called key performance parameters. I want to leave them up a bit because the other two halls still have to do this. And this is typical of what we'll have to do. So there's a statement here in green, which is, also will tell you, is taken verbatim from what's negotiated with DOE. So that's a given. This is what we have to do. You notice the beam energy is modest. The energy is above 10 JeV, 5.5 passes. It's the only way you can get over D anyway. And then we have to do the following. You have to show the detectors running for a shift, bringing data in from all subsystems. We want snapshots, the status screens, and the log entries, and then we wanted relative timing. And if you run through, this is all the major detectors in Hall D plus the tagging devices over in the tagger across the photon experiment. We then wanted event displays that show we have correlated particle hits in the various tracking and timing detectors, and then calorimetry, some reconstructed particle trajectories, and then finally particle ID plots. So D is done. This has actually been finished. There's a draft of this up for Hall B now, and I imagine one coming fairly soon for Hall C. So if you look at Hall D, this is a shot of things getting ready to run. There was a couple-day running period. Notice this is above 10 GeV. There's mathematical insistence here. It's maybe anything above it, but it's good. There's the target reconstructed. Here's a strip chart of the beam running. I happened to notice last night, going back to the talk, that if I'm reading the date off correct, these guys are pretty dedicated because this finished at 6 o'clock on Thanksgiving morning. They stuck to it until they had it. So big thanks to the Accelerator Operation Crew Engineering and all the Hall B staff and the Blue X collaboration. There's one last bit, which is the diamond radiator I'll come to in a minute. But first I want to show you that the machine kept going. This is then all three halls running together. Hall D kept going. This is now the Omega reconstructed from it. And then we, in fact, have been able to have some running in Hall B with HPS. It was opportunistic, as Mon mentioned. We're installing the Taurus as this goes, but in any magnet installation, there was a couple of bits here and there where you need to be working somewhere else before you bring the next large object down. We took good advantage of that and had a fair bit of first data on it ended up wrapped up in May. Hall A, we were able to get running. As Arne mentioned, there were some issues with power on site, so we weren't maybe able to run the energy we wanted, but they did demonstrate high current running and yet being through the polarimeter and take data. So this is quite encouraging. If you go on to Hall D, Bob and I think Ken Hicks showed this yesterday in the NSF talk, the interest from the project's point of view is in addition to the amorphous radiator, which is in the project to tune things up and get initial photons, we then took a somewhat older diamond, put it in. The advantage to that is you now get coherent ground so on, and you get tens of % of linear polarization in the beam. And if you then take a look at how this is, that polarization will transfer to the row, and if you look at the correlation of the row decay constructed through the pi plus pi minus branch, you can see that in fact it does line up nicely with the plane, as you see from here. Whereas off the amorphous radiator you get no, in essence, a flat correlation, as you'd expect. So that was the last big thing this spring, to see that all get tuned up, and many thanks in particular to Ken Livingston and his crew to help on that. So let me shift over and talk about B and C construction project progress. Since we formally have to give numbers to DOE, your percentage is what's finished for those of you who like that. The detector and electronics are getting very near the end in both halls. I'll have mostly photos of finished things there. In the case of the DAQ and computing, in fact, C is finished. B simply has a procurement that is hanging out there for the beginning of fiscal 16. Beamlines are not quite halfway. That was by design. In fact, B doesn't start theirs until next fiscal year, so we'd expect this. Whereas the infrastructure is making very good progress. This is putting in all the tooling and fixturing, putting in the detectors, and in the case of B, this is actually the magnet, and C both, this is the magnets getting swung into place. In the case of B and the Taurus, it's actually the magnet getting put together because it's the one magnet where we put the internals together as opposed to have a vendor do it. So in fact, we'll spend a bit of the talk on the magnets, which is the main thing we have remaining still to do. But I'll note that in Hall C, of the 5 they have to get in here, 2 are here. In fact, our superconducting and have that power. So let me come through on the detectors for Hall C. This slide is starting to get a bit long in the tooth because they've been ready. Most of them have been ready to go for a while. We notice the complete tracking chambers, both aspects of the otoscope, the shower counter, which is in fact installed. Here's the Regina heavy gas Trankhoff counter. And I'll comment that the last one, as the project that is scheduled, is the noble gas Trankhoff counter. And I'm told by Howard that the mirrors are either back from CERN, coated and either in Dulles or headed our way as a winter model. So we in fact now have all the parts here are showing up in the US, and we'll be wrapping that up fairly soon. If you go down to the hall and take a look, sort of the view from below of the shielded part of the spectrometer, the view you saw earlier was all that over there. There's the shower counter in, the frames coming up for the simulator otoscopes, and then a dry run to put the mirrors in for the noble gas Trankhoff for when they show up. So this is progressing and is very close to done. If you go look at the magnets for Hall C, there are 2 that are in. The first one that came in is the focusing quad. Those of you who know the HMS will it's rather closely related to that. This is in fact been up to full field, as we'll mention in a minute. The other, which is in front of it, the horizontal bender, which is a septum type design. The bore is here. If you look rather carefully, what your eye picks up is the LE yoke and the cryogenics control. That is now installed on the platform. And then we have 3 magnets which are under construction as contracting went. They both ended up at Sigma Phi, which is in Brittany in France. The dipole, to get you an idea of scale, since I didn't have a good one of the current magnet, is this thing. It's an object which is about 3 meters long. This is the coil package, which has been carefully buttoned up in final epoxy. And what you're seeing on it is a test collar. It'll be lined. It'll have 24 of these aluminum rings put around it. Once it's assembled, when you cool it, those shrink somewhat faster than the copper and the coil does, and that gives you the compression that then resists the forces as the magnet is powered. There are then 2 smaller magnets, similar bore. The part you see now is 70 centimeters. It goes down to 60 once the cryostat is added. This is Q2, which is will be the higher field repair. As far as the company is concerned, these magnets are identical. The yokes are slightly different. This is, the coil has been assembled. What you're seeing is the technicians working on splicing the various layers together. There are 15 out of these splices that have to be done with a nano-1 each to be sure that you don't generate too much heat inside the helium bath. And then this is the second of the quads, or Q3 as it's called. These are 2 halves of 2 of the coil windings here have now been put together. The other 2 are on the floor as of this morning, waiting to get made into the other half of this, at which point in about a month it will be joined up. By the end of the summer, we expect to see this fellow collared, this one being collared, and this one lined up to have his collars put on. And over the winter, they go into the helium cans, and from thence into the cryostats. We'll expect to see them appear here over the winter and into the spring. If you look at where they go on site, this is a somewhat better view of things lined up. The yokes are there. What we need is something to go inside the last 3 yokes. You can see the shield house behind, the dipoles on the tilt, so that the detectors are actually in. This fact that the dipole's on a tilt means that the cryogenic service tower, instead of being right on top, actually has to go on a chimney that runs out the top of the shield house. So there's actually a field joint that will be put together under supervision of the company by us in late winter when that coal mass shows up. So Q1's on site. Physics division has to run a review to be sure it's ready to run, like what we're used to for an experiment. This is aimed at, of course, energizing a piece of equipment. It's cold. In fact, it's been up to 110% of the operational current. One last step is we have to finish up the field map, and then we'll check it off and we have a fully running magnet. In the case of HB, there's one open issue we still have to resolve with the physics division. But we've gone ahead, put it on the carriage, given it an initial cool down, so it does have liquid helium in it, and then an initial power test to 10%, 1% of stored energy, just to be sure that we're superconducting and things behave as they are, and it is indeed a dipole field. So we know that. If we then, let me shift over to Hall B and talk about how the detectors are. If you go look at the forward carriage, you'll notice the pre-shower calorimeter, which goes in front of the existing cal, has been up and running for, in fact, about a year and a half. Hard to see now because what it actually looks like is shown over here, where two sections of the forward time of flight in South Carolina put together have been installed in front of us. So this is what you would have seen about 5 months ago if you go down to the hall. The drift chambers, all 18 sectors, which were a collaboration between Old Dominion doing Region 2, Idaho State doing Region 1, and then Jefferson Lab doing Region 3s. These are all sitting here. They're either in the ESB if you want to have a look, or go over to EL 125 where we have one of them under test. Don't stick your fingers around too much and have a look. If you take a look at the other part of the time of flight is the central time of flight, which goes around the target. That's 48 slats. The slats are currently all separated in their test traction. As you can see, they're wired up as of last month and hooked up to the actual electronics, so they're undergoing, if you will, a burn-in while we go ahead and get the support structure built. If you look at the other, the smaller of the Cherenkhovs, the one that's recommissioned, this is the first box, of which there's 6. The picture is a bit hard to make out simply because the mirrors are in the first set of mirrors are in the box together with the phototubes, and we'll get the other set here and close it up this month. The tracking detector for the central part is the silicon vertex, which has about 36,000 channels. It's full barrel mode. It's 3 regions get put together. This is a shot from about 3 weeks ago with 4 very happy fellows after they just had it assembled. This is a shot from last Friday of Region 4. It's deliberately over. I've oriented the picture so it's in its running position. You'll see an actual picture here in a minute of what it looks like, but it is also running as of Monday morning. So here it is, Region 4, the last one, being put together with Brandon Marzoff and Steve Christo, so one of the head mechanical engineers and head tech, doing last bits of assembly. This actually was the easiest of the 4 to put together just because it's the biggest, or the scale is the easiest to handle. So this is now running, so the entire SDT, in fact, is up and alive. We're happy to say that we have 36,000 channels. We have 1 or 2 that are misbehaving. So it's quite good. The other detector is the high threshold detector. You've seen a picture of the mirror. You get an idea of the scale of the mirror when you see it up on end. It consists of 48 segments. They're all made of foam and aluminized, so if you toss one up, it takes a while to fall back down into your hands. Here's the lead scientist, the lead tech, to give you an idea of the scale. This is the containment vessel. And then as of about 3 weeks ago, this is a close-up view of the entry point of one of the phototubes. What you're seeing is a laser pointer which has been put at the target position, bounced off the relevant mirror, and shown that even with nitrogen in it to simulate the relative humidity of the CO2 operating gas, that in fact the laser or the light from the particle is within ½ an inch of dead center, which is quite fine for this particular detector. So we're now at the point of lining up the last few phototubes, and then we'll take the mirror out, put the final covers on, and this thing will all be finishing out. If I look at the magnets for Class 12, there are 2. Fermilab is involved in the Taurus. It's a 6-fold Taurus, and I like to joke that they've delivered, of the 6 coils, they've delivered all 7. I.e., they're making a couple spares for us. In fact, there'll be 2 spare. The second spare came out of the mold this morning. Now that it's cooled down, it'll be surveyed in the next couple of days, and then we'll start getting the proper cooling panels on it to get it in its coil case. So by about third week of June, we expect to see the last of the wound coils come from Fermilab, at which point I hope that Lambert makes a nice phone call to Nigel and thanks him very much, because it's looking very nice from there. In the case, this is showing you one of the coils in a, if you want to go over to the test lab, there's a large foam cryostat, which we use to cool these down to nitrogen temperature just to be sure they're behaving before we then go and put them into a cryostat. This is, if you will, an extended cold shock to be sure they will cool. This is a conduction cool magnet, bath cool magnet, so we want to be sure that with one pipe making two loops around it, that it in fact does get cold. The other is the practice coil for the solenoid, which was wound over last fall. Better pictures are shown here. For the solenoid, this is the winding of the first coil, which finished up 3 days after your income taxes were due. We now are 2/3 of the way through winding the second coil and should finish that up by September. In the case of the Taurus, this is just a coil as it's wound at Fermilab. This is as it goes into starts going into the case. This is an early fit on the hub. This is how things look once we put the cryostat on it. The steel shielding blocks do disappear. The problem here is you have a 4 by 2 meter object, which is about 10 centimeters thick, and you want to weld it with a millimeter distortion so it doesn't turn into a potato chip. After some practice, you learn that it has a mind of its own, and it needs several tons of persuasion to stay put as you get the welding done. But we've mastered that. And then here's a close-up view of one of the coil cases as we add the instrumentation to it, and these strain and temperature gauges on it before we then bury it inside of the cryostat. So here we are in the hall. This is 4 coils. If you have your ag work or go down the hall, and your training, go down the hall B and have a look. You get an idea of the scale. That's Calvin standing up on the man lift after we put the 4th coil in. If you count them, you can see 4. If you come back in, I think about 3 weeks, the 5th coil should be up there. Most, we should have the last one in by sometime in July, at which point most of it, since the coils are in cryostats and pretty much closed up, most of the effort goes into these support beams that run between the coils. They're the conduits for the cryogens, they're the conduits for the conductor to give us a circuit. They're a way to get some of the instrumentation out. And what you're seeing, in fact, is the cold section. So the major effort between now and December is to get everything else added to these beams, get their thermal shields and cryostats on, and get the whole thing welded up and be pumping by January. That's the general schedule. So a couple dates as I wrap it up here. If you look at Hall B, we should have, the 6th coil is in here. We ought to be into the cryostat by the end of the month. The welding still to be finished then, but we'll be close to finished. The installation runs on to May of next year, so not quite a year. Coil winding for the solenoid goes on until November. We expect to see it show up on a truck from Pennsylvania where it's being built. In May, we then have to add the cryogenics and instrumentation services outside to it. We expect that, therefore, by the end of the year, we will be commissioned with beam. As Arne mentioned, even though the accelerator is finished, we still need it to run twice more on the physics side of the ledger because we have beam commissioned for B and then for C. In the case of C, we have 2 of the magnets in here in cold. We expect to see the last of the 5 show up again in March of next year, so about 10 months from now. It takes a couple months to get it up on the platform. We have physics to agree that it's a good magnet and we can run it and get it cold and operate it. So by May we ought to be done, and the plan in that case is then by at the end of fiscal 16 we'll be running having a beam on there. So last bit, 2 schedules, just to show you where we are. We're about to, we've hit these first 3 on the Taurus. This is the cold masses coming in. This is the last of the cryostats being done, which this is right at the end of June, early July. You then have this long blue bar where the Taurus gets put together, pumped out, cooled out, and checked. And there's a flurry at the end to get the wire chambers and the high threshold installed, since they have to wait until the Taurus is cold and mapped so we can do that bit of installation. You can see that's happening right at the end of fiscal 16. Solenoid is on a parallel path. We expect to see it in May of 16. You then have to put it in, put in the detectors that go around it, the CTOF, and also the CMD, which comes in, and then we have a beam run shown here in green. If you see the same schedule for all C, you can, Q1 and HB are in here. We've got some testing to do, and then we expect to have a burst of activity that starts right at the end of the calendar year that runs for about 6 months as the 3 magnets come in from France. And we will be putting detectors in as we can until the very last ones, which have to wait till the dipole's in place and the field joint is made on the cryogenics before we put the wire chambers in, just prudence dictates. And we'll have that being on the calendar year. Well, that's it. Thanks.
Thank you very much. Are there any questions?
Hi. I have a question concerning the mention that the doubling of the energy is completed, it's done. I think you said in your talk that that means that we got 10.5 GB in all D, a few nanoamps for shift. When I did my experiment on the floor, I thought it would be 11 GB in all A, 20 micron for months. So if your project is completed, where are you going to find resources to fill this gap?
I did not understand the question. So.
I think the question is 10.5 GB versus 11 GB and 1 nanoamp versus 20 nanoamp.
Remember, these are initial goals that the project has to meet to say that we built a capable machine, and capable detectors. The actual commissioning part where the energy comes up was described yesterday, where we get up to 11 GeV and from ABC and 12 GeV and coming up to the Tagger and Hall D. The project, in terms of being able to say that we built a capable machine, has the requirements as I showed you.
Which money are you using
So there's three parts.
Which resources are you using to fill the gap?
So this is the whole promo, isn't it? You have funds for the project, 12 CV. At the moment the project's complete, we can talk about physics operations. Until that time, DOE actually, nuclear physics, gives us funds for the transition to operations. So there are also operations funds, but not aimed at physics operations. So those are the weeks which essentially Mon talked about and Arne talked about. So those are the 16 weeks. So the 16 weeks, for instance, we get for FY16 are transition to operations funds from DOE nuclear physics.
So where do you get the money to implement the CHL?
Office of Nuclear Physics, DOE. I'm not sure I understand your question.
Any other questions?
That question was, when will we get the money to repair CHL? Was that?
No.
Yes, that was the last question. Yeah, I can speak up. The horizontal bender in Hall C, you said there was an issue. We know that there's the issue with the fringe fields associated with it. Is that?
That's not the issue.
And I know there's solutions that have been proposed. Is that?
The issue I was referring is if it undergoes a quench, how does the thermal shield react? There are always forces when you quench a magnet. You unavoidably get eddy currents in the thermal shields. One of the design parameters is how hot will the magnet get localized. Another way of saying that is how long does it take to cool it back down. And you tend to size your dump resistor and your power supply to decide how long you want to take to let it cool down. Big resistor means the power comes out quickly, the hot spot's fairly small, but that leads to a lot of stress on the shield. You can trade it off the other way, reduce the stress, but then you have to take a higher hot spot. We're in the middle of discussions about exactly what happens to the shield in the case of a quench. And that's required. It's turned out to require a bit more engineering study than was, I think, understood when the magnet was designed. So we're talking with Patrizio's committee. I think that's fair to say. There's a fair amount of calculation that shows that we don't think we'll tear the magnet up. That we have to work our way up in steps to be sure that it behaves. So in fact, there will likely be a series of tests at various currents as we bring it up. We don't want to quench it for obvious reasons. These are cryostable magnets, so they're hard to quench anyway. The it's a bath cool type magnet, but we can do a fast dump that simulates the stress that the shield will see, and then we can measure how the circuit, in essence, how the electrical circuit behaves as you do it. So that's the open issue that we have to resolve to her committee satisfaction. So at the time, we know that at 10% current, we have no issues there. The magnet barely knows that you turned it off. So that was a fairly easy discussion. But we want to start working our way up to half field, at which point you have to start being a bit careful. And that's the discussion, that's the open issue.
Any other questions? If not, let's thank all the speakers.
CGE.
Microphone's not on.
Can you hear me? All right. Thank you so much for the invitation, the opportunity to give an overview talk on the VCS program at Jefferson Lab. The question that we try to answer with this program is how can we describe the nucleon in terms of its constituents? And then kind of a sub-question is where does the spin of the nucleon come from? 50 years ago, our studies for the nuclear structure were somewhat limited to form factors, which gave us a description of the nucleon in terms of the transverse distance, and deep inelastic scattering, which gives us a description of the nucleon in terms of the longitudinal momentum. It's clear from these two pictures that the nucleon has a multidimensional structure, and therefore we need something more. One way to describe the nucleus in more general terms is particular distribution, which are 5-dimensional distribution in terms of x transverse position and transverse momentum. And here we get the zoo of distribution for the nucleus. We have the bigger distribution that can be reduced to transverse momentum distribution and can be measured using semi-inclusive deep inelastic scattering. Or we can get back to the one that was studied 50 years ago, particle distribution function, which can be studied with the deep inelastic scattering, but also recently with the dihedral measurements. And then what we're interested today is a generalized particle distribution, which can be studied with the DVCS and DVMP. We will focus on the DVCS today. And one essential component to make all these studies is to use polarization observables, which give us access to several quantities. So GPDs are fully correlated coordinate distribution both in coordinate and momentum space. So they are kind of answering our questions about what is the structure of the nucleon. So deep distribution quantum scattering, as you're well familiar with the process, is production of electron scattering on a proton or a neutron type with the production of a real photon. And we are in a regime for which we just interact with one quark, and we are sensitive to the structure of the nucleon without really breaking it. And the GPDs for the DVCS that describes the nucleon are 4 GPDs, the H tilde, E, and D tilde, and they're a function of 3 variables, x sub I. The experiment to the actual GPDs require some model, or we require some new experiments, like for example the double DVCS. These GPDs have a relationship with the nuclear spin and the quark spin. The H and the E, the GPDs are the so-called unpolarized GPDs, because they're basically a sum of the quark spin, and the tilde ones are the polarized one because they are basically a subtraction, but they all preserve the quark spin. The H and the H tilde are the one that conserve the nuclear spin, while the E and the E tilde are the one that flips the nuclear spin. When we access the GPDs via the VCS, it's clear that we have, on top of the VCS signal, we also measure in Bechdel-Heiter, which is emission of a photon. And these two processes are undistinguishable. But at least for some of the measurements, Bechdel-Heiter is good for us because it's functioning as an amplifier of the signal, since when we do asymmetry, the symmetry depends on the interference term, which is the product of the VCS and Bechdel-Heiter. So Bechdel-Heiter, to some degree, is helping us. The DVCS amplitude depends. It's the dependence of the DVCS amplitude on GPDs. It's through an integral, which can be expanded in terms of an imaginary part, which is the GPDs at x equals psi, or the integral over x for the real part that can be measured through double spin symmetry and cross sections. When we do polarization experiments or even cross section, what we really access, as I just mentioned before, is the so-called Compton form factor. And different observables gives us different sensitivity to the various imaginary or real part of the 4 GPDs. If we do measurements on the proton, we are beam asymmetry gives us access to the H GPDs, target asymmetry on the, it's a unique way to access H tilde, double spin asymmetry, it depends on the real part, and the transverse spin asymmetry is important because we can access to the E GPDs for the proton. If you do measurements on the neutron, due to the different strength of the form factors, we have different sensitivity. Beam asymmetries give us access to E on the neutron, and the target spin asymmetry on H, double spin asymmetry again, real part, and then transverse the H GPD. These are the main players on the VCS experiments worldwide. These are some older measurements, but anyways, these first three are high energy, and their measurements are in low X, which is more sensitive to C quark. And if you look at Jefferson Lab, class, and whole A, and then what we will get in OB, we see that we have a large ring in X, which gives us a unique access to the valence quark region. So today I'll be talking about the Jefferson Lab experiments. And the two holes that we've been focusing on the DBCS program are hole B and hole A. And they give us different kind of results. One large acceptance with larger kinematic range, and this one is high precision but more limited kinematic space. So this is the result that started all. Is in 2001, Stepan analyzing run and extracting the beam spin symmetry. It was not a dedicated run, so the statistics was very limited, but there was a clear sine phi modulation, a clear dominance of the sine phi term, which confirmed the applicability of the handbag the twist to dominance even in this energy. And in the same journal, same number, concurrently, Hermes published also beam asymmetry. And that pretty much started all the whole DBCS program. After Stepanian measurements, there was a dedicated experiment for the beam spin symmetry, where there was an additional hardware component of the forward calorimeter to measure the forward photons. And this was very high statistics, so the data was binned over several bins in Q-square and Spjorkin, and it was the sine phi moment was extracted for all these bins. And here you can see a comparison with some prediction like the VGG model. Another pioneering experiment was the target spin symmetry, which was again an extraction done on data that was not a DBCS run per se, and again very low statistics, but there was a clear signal, and also Hermes had the extraction of the target spin symmetry, seen a non-zero sine to phi moment, but this data did not allow to do any study in this regard. After this preliminary measurement, there was a dedicated experiment, the so-called EG1 DBCS, which was a high statistic measurements, 10 times more than the previous one. There was a, thank you to the forward calorimeter, there was a complete detection of the final state, which gives us a very tight exclusive cuts. We had the polarized target, the polarized beam, so we were able to measure simultaneously the three asymmetries. And this one also allows us to, even with just this data, to do a simultaneous fit of the asymmetry and have a first look of the Compton form factor. So this experiment improved drastically our knowledge to the point of these three experimental quantities. This data was published in January and March. We did this publication. The first publication was focused on the target spin asymmetry, and here you can see how the data was been in Q square and S Bjorken, and also 4 bins in T. And these are the different target spin asymmetry corresponding to these kinematic bins, fitted with a sign fine dependence and also compared with the DGG model. This show the sign fine moment as a function of T, and also comparison with the various models. Best agreement is with there's qualitative agreement with all the data. There is agreement with the Hermes previous measurement, although the kinematic range is different. And good agreement with the KMM model, although it's limited to T less than Q squared over 4. One interesting thing that gives us the first look inside of the nucleon is that if we look at this T dependence of the target spin asymmetry as compared to the beam field symmetry, you can see that the sign phi moment for the target asymmetry falls off slower in T as compared to the beam field asymmetry, which gives us an indication that the axial charge, which is related to the imaginary part of H tilde, is more concentrated than the electric charge, which is related to the beam speed asymmetry. The second publication was focusing, it was a long paper reviewing the whole analysis and also showing results for the beam spin asymmetry and the double spin asymmetry. This is our results for the beam asymmetry, and this is are the sign phi extraction. Data were compared with the previous hydrogen measurements, and they're in good agreement. And again, we have the same qualitative agreement with theoretical prediction. The double spin asymmetry, it's depending on the real part of the GPDs, and it's an even function in phi, as you can see. We fit it with a constant term and a cosine term, and but this one is dominated by beta Heiter. And so the agreement with the model is pretty good because models do good in predicting what beta height is, and the statistical precision is somewhat limited. The one thing that was nice about having the 3 asymmetry simultaneously was that we were able to fit this data to extract the Compton form factor. We used the Michel Vidal fit, which is a quasi-model independent fit. The only limitation is E tilde equal to 0 and a maximum variation of the Compton factor within 5 times the VGG model. We extracted the H and H tilde, and we reproduced again what I said before, slower fall off for H tilde as compared to H. Again, an indication of the distribution of the valence quarks as compared to the C quark. The change a little bit kind of measurements. There has been measurements of cross sections. The first one was done in Hole in a publication 2006. I believe there is a talk after mine of somebody from Hole, so we'll need probably more details. But the cross section is trickier measurement because, as I said, it's the sum of beta Heiter and DVCS. But there is if you look at the models prediction, there's definitely a non-negligible DVCS contribution, so it's still significant to look at cross section. And from this measurement, they found, as I said, a non-significant, a non-zero DVCS contribution and a negligible twist rate contribution. We just, the whole B collaboration just submitted a publication for their cross-section measurement. It's a class measurement, so a very large kinematic region in Q square, S Bjorken, and several T bins. And they measure both cross-section and difference in cross-section. This gives access to the H tilde, but also gives access to the real part of the GPDs. And one can see comparison with various models. One thing is that the cross-section definitely favor H tilde equal to 0, which is slightly in contradiction with what was found in the whole A first measurements. This data was also fitted using Michel-Vidal feeder. In this case, the E and E tilde were set to 0 to limit the free parameter, but they were found as well-defined minimizing value for the imaginary part and the real part of the HGPD. And also the data were fitted with a simple exponential form, and one could conclude from there that the size and protonic content are bigger for smaller momentum fraction. And the archive one can find also the recent whole reanalysis of the data that I showed before. This reanalysis, it's a reanalysis, but they also added some kinematic means. And so kind of this result supersede the previous one. From the cross-section measurement, they found again a big DVCS term and again a small twist 3 contribution. And from the cross-section difference, they found a larger on and small twist 3 and the dominant twist 2 interference term. This again is another snapshot of their whole day results and comparing different models. And one interesting thing from their publication is, or soon-to-be publication, is that the agreement with the model improves drastically if they add to a model the target mass correction. Speaking of DVCS contribution as compared to interference, there is a proposal in a way with analysis ongoing that plans to separate precisely these two contributions, taking advantage of the fact that there is the DVCS terms have a kinematic factor depends on the beam energy, while the interference doesn't. And therefore, by taking data in two different beam energy, they can do a Rosenbluth-like separation of these contributions. One thing that I kind of light over is that when I talk about GPDs, they are either on the proton or on the neutron, and they're a combination of the different flavors. And depending on the kind of target, you have different combination. But ultimately, what's interesting is extract the flavor of GPD, the GPD for each individual quark. And so if we have measurements both on proton and neutron, we can extract the GPDs for the U and the D quark. And here it becomes essential to have different measurements of different quantities and different targets that are sensitive to all these pieces that we need for the separation. One perk of having the quark GPDs is that we can, for example, use it in the G sum group to get the information about the quark angular momentum in the nucleus. There are already neutron measurements. In Hole 2007, they used the neutron target and they measure coherent and coherent scattering. And then they used their proton measurements to subtract the contribution from the proton and obtain basically the sum of these two terms. From these results, one can see that the sum of these two terms is basically 0. Which indicates opposite contribution from the neutron and the neutron target. And then this data was fitted to separate the contribution from the Compton factor of the deuteron and the neutron. Now, the results for the Compton factor for the neutron is compatible with 0. Nevertheless, it's an important measurement because one can see that if in the model we change the values of the quark angular momentum, there is sensitivity to these quantities. We have an ongoing analysis, another pioneering measurements on the neutron using the EG1 DVCS data. The data is still at the coherent stages, but we observed non-zero beam spin symmetry for the neutron. And lastly, we have in-class measurements on nuclear target. We use the helium-4 target. And helium-4 is a spin 0. Therefore, only one GPD is surviving, which is the HGPD. which makes both things a little bit easier. They measure the beam spin symmetry coherent on the neutron, and here on the imaginary part and the real part of the HGPD. At the same time, they was measured the uncoherent DBCS, and the two asymmetries were compared. It wasn't really looked at, but there are two asymmetries overlapped here. And ultimately, this experiment will try to get some information to resolve the EMC effect. At Jefferson Lab, as you heard in many talks, we're planning an upgrade, and all the three holes all have experiments in DBCS. You can see here the class 12 will increase drastically their kinematic range, and all the three experimental holes are planning to upgrade the detector. Here are my conclusions. GPDs are a very powerful and unique tool to explore the structure of the nucleon. They give us a 3D imaging of the nucleon. We need complete measurements of different observers and different targets to do a true extraction of this quantity and have the dependence on the three variables. And I think that the 2G3 will bring us pretty close to have a good picture of inside the nucleon. And my last final remark, these are my two that are possible to measure either the spatial or the momentum distribution. Thank you.
reveal my ignorance in asking this, but I don't know what it means to talk about a GPD on a quark. I thought GPDs were supposed to, encapsulate.
No, GPDs is the distribution of the quark within the nucleon. But then we can talk about GPDs of the proton or the neutron, which is a linear combination of the GPDs of the individual quarks that make the photon. So we really look at the distribution of the quarks inside.
Okay, all right. I thought you were looking at H sub U and H sub D, for example.
Yeah, those are the GPDs of the quark U and D. But when we do measurements on proton and neutron target, we don't have access clearly to these quantities separately. It's a linear combination of the two. And then we need measurements of both proton and neutron and several observable to really disentangle this full contribution. So, for example, we really need a measurement of the transverse target to get access of the E GPDs on the proton, and we need measurements on the neutron target to get access to E of the neutron. And then once you combine these, you can combine all the different contribution and extract the GPDs of the quark. Did that answer your question?
I think maybe my question is more simple, so I'll have that offline.
Or maybe it's just a bad English.
Okay, okay, now I
All right, maybe it's just English. Possible.
last users meeting, 2014. This is basically the outline. So what we've been trying to do is to run two experiments simultaneously, the DVCS experiment and the GMP experiment. I will describe a little bit the goals in a minute, but this is how the configuration looks like in the whole for the last year. This is the top view, the beam coming from the bottom. So we are using, this is the reaction we are interested in for DVCS. We detect the scatter electron in the left HRS and the photon in a dedicated calorimeter. On the right HRS is used by the GMP experiment, which is interested in an elastic reaction detecting the scatter electron. And this is just a view from the back where we see the left, this is the right HRS, the left HRS on the DVCS calorimeter here sitting in the middle. So the plan is to run both experiments simultaneously. Due to the placement of the DVCS calorimeter here, the right HRS cannot go to the very forward position, so some of the GMP kinematics will need to be run with the left HRS anyway. So it's partial simultaneous running and then some sequential running of the two experiments. But the configuration is simultaneous like that in the whole right now. So the motivations of the DVCS experiment, well, we've had a whole talk about this, but just say that, okay, we are interested in the regime where the GPDs are accessible to DVCS, and this is the regime where Q squared goes to infinity. Now, the actual value of Q squared, where this starts to be true, the experiment must be tested, and this is the goal of the DVCS program in whole, like to make Q squared dependencies of the cross section compared to the Q squared dependence predicted by the handback diagram here, and then make an assessment of whether the kinematic regime is appropriate or quantify the higher twist contribution. So these are the kinematics, the Q squared explained. We plan to do 3 scans at constant x values of 0.36, 0.5, 0.6, and at each value of x, we have 3 or 4 settings in Q squared, again to study this Q squared dependence of the cross section. We have 100 back days approved, 88 days of data plus 12 days of overhead. It's a rate experiment, and it was also labeled as a high impact experiment by PAC 41. So this is how whole A looks into the 3-year schedule that Monte showed this morning. This is how the schedule looked when we started planning the experiment in December 2013. This is where we are here, and there was an opportunistic update of the schedule right where we were about to start physics. So now it's labeled as opportunistic physics. Physics will be in the 2017 year, but we're still hoping to get some beam time there and hopefully get some data for these two experiments. So we are running, right now we are here, and I will be describing these 2 run periods, basically fall 2014, where it was commissioning, and then some opportunistic physics we took on the 2015 run, spring 2015. So this is the manpower we have for the DVCS experiment. There is a core team. Basically here the message is this is a mainly off-site collaboration. 70% of the users are from either off-site or even from abroad. In order to run this experiment, many of us have been relocated here. So we have 4 people from Ohio, having stationed here at JLab for 1.5 years. 4 people from Marseille, where we have been 2 years stationed at JLab, and then UVA, as one graduate student has been stationed at JLab for almost a year. And then we have also some local collaborators from ODU, 5 people, and 1 particular staff from JLab. But of course, all the online collaboration, physics and technical staff contributes to the running of the experiment. Now the GMP experiment, the goal is to make an accurate cross-section of elastic cross-section in order to measure form factors of the proton with very high precision and at high Q-square in the region where there is very inaccurate data at the moment. The challenges of this experiment is basically the beam requirement. It requires a very good control of the beam energy, target density, and scattering angle. So it's a very demanding experiment as far as the beam quality is concerned. The manpower is basically 4 senior people, 3 graduate students, and 1 postdoc. I was counting over the weekend. We had about 6 back days for this run period, which were breakdown in this way. So the commissioning was pretty fast. It was roughly half a day for the electronics. We had about a day of calibrations, and then we took about 4 days of data taking. Now, in order to accomplish these 6 days, we have taken a lot of shifts, 879 shifts over the 3-month period, have been extended over 139 days. So as Mo mentioned this morning, we can get mean time out of the commissioning of CBAF. It is not entirely clear to me this is the most efficient use of the user's manpower. It is a tremendous effort by both the users and staff at JLab, and it puts a lot of stress on the very small collaboration, actually, to run these experiments. So this is a plot that I've been seeing this morning many times. I made this in December last year. It was made in order to motivate 5 weeks of running in spring that we actually couldn't do. So basically, what we have right now is this point at a P-square around 3 GeV that we took in the fall 2014. So the hope is to get at least 1 Q-scale dependence so that we can make some physics out of this data. So the goal of this talk is to report that we did with these 6 days of beam time, and we did quite a lot of things. So here's a list, and I will go into some details of this item. Some unrelated beam activities, but it was part of the commissioning, was that we installed a new bedtime monitor system in the HRS. We improved the light collection of the BMTs in the gas Charikov. So with wavelength shifting pane, we improved the photoelectron yield by more than 50%. The polarimeter was commissioned over the fall and spring run. The DVCS experiment has already been commissioned. The DVCS polarimeter calibrated. We took some data, as I said, in the fall 2014. And GMP took some optics data and some elastic and 1 elastic point over the fall. However, the uncertainties on the beam were not enough for this data point to be useful for the GMP physics. Now in the spring, the beam energy, well, I forgot to mention, during the fall we only had 1 HRS working, so it was not simultaneous running, so there was some dedicated time for the GMP collaboration to take this piece per point. In the spring, both spectrometers were working. We started with a higher beam energy. After the power outage, this came to 2 GeV. These are the list of things that we did. New raster system commissioning, BPM and BCM calibration, beam energy measurement, and then the content polarimeter commissioning was also done. And then on the GMP side, we took some data for the optics calibration of the HRS. Right. So now the molar polarimeter, we took 3 molar runs over the last 2 run periods. First one in December with a beam energy of 7 GeV. It was not completely finished. The beam was lost before the full procedure was completed. But we did take 2 more runs over the spring, one at 9 GeV and one at 2 GeV. First one, the high energy, the beam was not very stable, and there was also some power supply problems. We still could make a preliminary measurement of the polarization. And then the real run for the molar, where the beam was stable and we were able to take a lot of data to do systematic studies, was in April 2015. So the conclusion of the molar commissioning is that it's operational. It has been run successfully at an energy of more than 6 GeV. It was found that running at full energy in NGV would require a stronger power supply, but another solution to this is just to lift the detector by 3.5 centimeters, which is of course cheaper, and it has been studied. It can be done within the geometrical constraints. So this is, I think, the solution is going to be taken. And as I said, in the April run, they have a lot of data to study systematics on the model measurement, and that's under analysis. Now the DVC experiment commissioned successfully the electronics. So this is 1 gigahertz custom electronics, which allow us to sample EMP signals at high frequency. This was already successfully used in 2010, so basically the commission was to check it out again in the fall with the new network system, and we found that the dead time is smaller because there have been some network upgrades things, so that was not a real commission. Now what was more tricky was the commissioning of the trigger module, which is something we had a lot of trouble in the past. We had a lot of time since 2010 to work on this module, so the commissioning worked pretty fast. Actually, you can see here some coincidence in the spectra between the spectrometer and the calorimeter. And one of the concerns that we had before was the measurement of the dead time. So we need, for an accurate absolute cross-section measurement, we need to control the dead time very well. So you can see here a beam current scan, where we increase the the beam current, and we look at some single rate. This is the black points. And then when we correct by the dead time calculation that we have, you see that we get a very proportional rate as a function of the current. You can see here the residuals. Maybe you don't see very well. There are two set of points, red and green, that are two independent corrections of the dead time that they both agree very well. So we are confident now that we can correct for dead time up to the currents that we will run the experiment, which is 20 microns, with about 1% at certain. The DVCS calorimeter was calibrated. We used the elastic reaction for that, where we detect the proton on the left HRS, on the electron on the calorimeter. We obtained a 3% resolution at 7 GeV. It's some online analysis that is still ongoing, and more details on that. But the main point was this online calibration was to check the relative gains of blocks. We found that we could match them within 5%, and this is important because we have an online threshold on the trigger, so that we need to make sure that the threshold is uniform all over the surface of the calorimeter. So from the actual base of data that we took, I showed here some spectra that had been shown already before. This is the pi-zero reconstruction of the calorimeter, and this is some DVCS events. This is the Misimas square, where we detect the scattered electron and photon, and these are the proton events that we're interested in. So this was taken at 7.3 GeV, slightly smaller than the beam energy that we had in mind, but still it will be one useful point if we get a scan at the same X at higher vision. Now, one of the activities from the GMP collaboration was to improve the tracking on the HRS by adding one additional chamber to the BBC. So we have, these are the two standard BBCs. There is one additional chamber that has been added that will be useful to disentangle or to reconstruct ambiguous tracks where we have two clusters in one of the planes of the BBC. So you can see here some preliminary analysis from multi-cluster events. So in this round it was about 8.5%. But you can see here is for one cluster events on the BBC. You see that about 40% are on the last peak. If we select events where we have two clusters in one of the planes of the BBC and one cluster on the other one, so these are the unambiguous events, if we use the third chamber, we still get the same amount of elastic events. So that means that a great fraction of these multi-cluster events can be reconstructed or recovered from the use of the third additional chamber. We have calibrated the BCMs. This data comes from the spring, where we could already run the beam current to a higher value. You can see here two different outputs of one of the cavities, one which is supposed to work at a higher beam current, and one which is useful for smaller beam currents. So this is the frequency as a function of the answer current, and then this is the residuals of this fit on the right. So you can see that for both high and low current, we have some reasonable calibration of the BCMs, and this last plot is a new BCM receiver, which is supposed to work all over the range, and this is basically what you see here. We still have some problems at low beam currents that we need to understand, but it is clearly linear all over the full scale. Now BPMs, or this is a typo, this BPM calibrations consist basically to calibrate the readings of the BPMs against an absolute measurement given by HARP scanners. You can see here the calibration of the upstream and downstream BPMs. And the raster current calibrated against the BPMs is what you can see in this plot. We project once we have the BPM calibrated, we project the values to the target, and we calibrate the size of the raster against the current. So this is a new raster system that was in place for the 12GB. So it has already been commissioned during this spring run. The last days of the run, this was already at low energy, but it was very useful to commission the quantum calorimeter. What you can see here is, well, of course, the first step is to go through the chicane. This was achieved quite quickly, and once the background were minimized, the collisions were observed between the laser and the electron beam. You can see here, this is the photon rate, and when we turn the laser on, we see that the rate increasing and decreasing as the laser turns on and off. That was the first accomplishment. So it has already been observed an asymmetry, and I think Arne Mohan showed that yesterday. You can see here is the typical spectrum from a quantum spectrum, where you can see the quantum edge, which is the maximum energy of scattered photons. The conclusion is that it's operational, at least the photon detector part, and in order to get an accurate measurement of the polarization, there's still some offline analysis that needs to be done, especially understanding the acceptance and the response of the detector. Now, as some of you may know, the plan, as I said, was to use the right HRS for the GMP experiment. However, the Q1, the first quadrupole of the right HRS, was not operational last year, so it was decided to replace it by the SOS first quadrupole from Pole C. And you can see here how it looks mounted on the right HRS. So it's a warm magnet. It's slightly smaller than the original Q1, but as it turns out, simulation of the acceptance gives a very similar acceptance if we manage to match the integral field. You can compare here the blue acceptance compared to the green one, which is with the SOS one. Now the acceptance is similar, but they're not exactly the same. There is a loss in the vertical acceptance, mainly due to the smaller core length of the SOS magnet, but it's not that bad. It's a reasonable match between the two magnets. We took, of course, some optics data in order to calibrate the new magnet. You can see here data taken with sieve coming from the middle, the central fold of the target. And we can very clearly see the sieve pattern. And there is some analysis ongoing to optimize the optics. In the last few days, last weekend of data, we took some angle scans with the spectrometers just to check the mispointing and misalignments. You can see here the elastic peak reconstructed at 3 different values of the HRS left angle, 25, 25, 45. Once we correct by the vertical position of the beam, it turns out that the difference with respect to the proton mass is consistent with the typical mispointing or misalignment of the spectrometer angle, 0.4 milliradians. Other activities I won't mention in detail, mainly because they're still under analysis, is some target boiling studies we took at the end of the run, where we had high beam current, a series of runs to study boiling of the target. We also have some beam energy measurements that show that the arc system is fully operational. Even if we didn't have time to perform a measurement in dispersive mode, we still have a roughly 10 to the -3 agreement between the accelerated value and the arc measurement in non-dispersive. So in conclusion, we had about 6 days of beams spread over the last 2 run periods. We have commissioned most of the whole equipment. The commissioning of the DVC experiment is completed. We didn't have enough data to make a Q-square dependence of the cross-section. There is no physics data for the DVC experiment. The collaboration is exhausted, and our off-site collaborators are required to return to their home institutions. So we have used all our sabbatical and free time for running this experiment. Now, I won't go into an outlook. I will just stick to the official word from the lab, which is physics in 2017 in OLA. And I will finish with a big thank you to the OLA collaboration, both the technical and physics staff for helping running the experiments, both DVCS and DFT, and even a greater thanks to the accelerator and engineering staff. I've really spent endless days and nights trying to deliver beam for physics. So thank you very much.
Thank you very much, Carlos. Questions?
You showed that you could accurately make your dead time corrections. What do you expect to run the experiment? What kind of dead time do you expect to run your experiment?
We had run in the past about up to 40% dead time, but that was before, when we had the trigger module was not working, so it was single range basically. Right now we haven't managed to get above 10 to 15% at the rates we're expected to run now. With the new network upgrades and the coincidence modeling in place, it's about 10%.
Thank you for giving me this opportunity to present an update on the HPS experiment, the heavy photon search at Jefferson Lab. So first, really, what is this heavy photon? From very general principles, you can assume that there is a possibility to have an additional U1 symmetry if you extend the standard model from its current configuration. It's very easy to come up with new models, new theories that have an additional U1 symmetry in it. And as soon as you have an additional U1 symmetry, you get an associated new gauge boson. And when you get such a new gauge boson, there will be kinetic mixing between the standard model photon and that gauge boson. If you look at the Lagrangian, so the extension of the Lagrangian that you would be writing, you'll get a term like this that mixes the standard model and the new, actually the standard model gave a new boson right there as a kinetic mixing term. Pictorially, that would look like a regular photon coming along, fluctuating into some pair, and then fluctuating back up to this new gauge boson instead of the original photon. And this can be at any mass scale. There's no real, there's not much constraint on that. You can rewrite this basically as a photon fluctuating into one of these new gauge bosons. And this new gauge boson has several different names. We call it the heavy photon. It's also called the dark photon or the A prime. And you can find different names in literature, but I'll stick to A prime or heavy photon in this talk. So what does this, what's the result of this mixing? So wherever you have a photon, it can fluctuate into one of these A primes. It's relatively simple to rewrite your theory to get it a little bit easier, and you can basically make a little shift. It's just a slightly different way of looking at the same thing. So equivalently, you can write that any charged particle acquires a millicharge due to this mixing. It acquires a millicharge under this dark photon. And so you get basically an epsilon factor times the charge of the particle that you're looking at, and that is the coupling that you get to produce one of these A prime particles. When you do that, that means that you can also fold this a different way. That means that the A prime, which is a massive particle, can decay into a lepton pair, or when it gets heavier in mass, muons, pions, etc., as you get more mass in this A prime particle. So this is really a very, very general statement about what happens when you add a very simple additional symmetry to your overall theory. Put this in perspective, here's a very interesting Venn diagram of all the theories that are trying to extend the standard model with regards to finding dark matter. And I don't know, I think I kind of wanted to print this on a t-shirt. But anyway, the dark photon has a little corner over here. So we are here among this large zoo of possible extensions. Another thing to take note is that so far we haven't talked at all about where this dark photon would live in parameter space. And so you clearly have two obvious parameters. One is your coupling strength, and one is your mass scale. And if you just take a very wide-angle view of this, then you can have coupling strengths over 15 orders of magnitude and masses over 30 orders of magnitude, and you have pretty much an impossible search. So you want to zoom in a little bit. You want to have some argument. The argument is that you want to look at sort of naturalness. This is a very common idea in theoretical physics to say, well, you just don't want to expect anything. You want to say, what is sort of natural, where's the first place that you're going to look? And it's sort of natural to assume that the mass will be inherited from the electron mix scale, and with a little bit of cranking of theoretical machinery, you can then make an argument that the mass should be around epsilon times the W boson mass, or maybe a slightly different factor. But anyway, the argument gets that with a coupling that is between 1 to 10 to the minus 8, we would get masses that are between an MEV and a GeV. That puts it well in the scale of where we can look at Jefferson Lab. And so search area of choice then is the upper right corner of that huge plot that I showed before. We still show it in a log scale, where these gray areas are areas that are excluded by various other experiments and processes that I'll detail a little bit more later. Now, since 2009, 2010, when this idea was revitalized, there's been a huge amount of interest, and you can see that The two original papers that really brought this back to life are Cunningham-Mentz paper and a possible of Ritz paper, and they have had huge numbers of citations in the last few years because there's been a lot of interest, and this interest was driven by some astrophysics anomalies that appear to be quite compatible with this idea, and also by just the basic realization that the dark matter searchers looking for recoiling dark matter weren't seeing anything. The LHC wasn't showing any sign that they were about to discover supersymmetry. And so people are starting to look more at other places, and this is a good other place to start looking for new physics. This was the exclusion area that I showed. So these areas here are excluded by old beam dump experiments that were reanalyzed for this A prime. Here's some precision measurements and some data from Babar. And when we were proposing our experiment in 2010, this is what the map looked like. Wind forward 5 years, and this is the new map. The beam dump experiments got more accurate analyses, and so cover more area. The precision measurements have gotten much better. And so there's a lot of activity, and it shows you also how much interest there is in this physics. So a little bit of a guide here. Beam dump experiments here are in the gray area. This red bar here is precision measurements. This is the anomalous magnetic moment of the electron cutting on the slice here. There's fixed target experiments. Of note here is the Apex test run that was done in Hall A, and the A1 experiment MAMI. Then there's rare meson decays, Phoenix, Chloe, Hades, that have looked for this. And of course, the flavor factories can also play this, and this is Babar did. We are going to look at this in a fixed target experiment. I want to focus on that a little bit. Why fixed target experiment? Well, you can get to really, really high luminosities, certainly compared to colliders. You have a dense target, you take a high Z target, so there's lots of electrons, lots of charge there to scatter off of. You take an electron beam, you can get very intense electron beams here at JLab. And so what we do is we scatter the electron off of the high Z target, and in that have a Bremsstrahlung A prime that then pair produces into an E plus E minus pair. The competing process that are obviously always going to be background is the Bethe-Heitler process, which we've also heard about in our DVCS talks. And of course there is this radiative process, which we call the trident process, where a photon fluctuates directly into an E plus E minus pair. When you plot that, this is a Monte Carlo, when you plot that and you plot the energy of the positron versus the energy of the electron, you find that the Bethe-Heitler, which is really, at our energy, is the massively dominant process. You get far, far more Bethe-Heitlers than you get radiative processes. But they're all clustered in this lower corner, where the radiative process is mostly along this line where the two energies add up to very close to the beam energy. So this allowed us to actually have our experiment because we can construct a trigger that prefers this area over this area, and so we can actually take data at reasonable rates. Two ways to look. What you then look is you take all this data and you do one hunt. You look at a signal over background. You can improve that a little bit by distinguishing your signal from background using vertex. So how does this work? Well, if you look at the gamma c tau of the heavy photon, so that is how far it travels, which is of course directly related to the lifetime of the particle. This goes like some factor times 1 over the coupling strength and also 1 over the mass. So what this means is that when you're looking for very, very weakly coupled A primes, so that means epsilon is very small, you're increasing a beam completely in a beam dump, and then the lifetime of the particle that you're looking for is long enough to actually travel to a detector that is completely in the dark, that doesn't see anything that's normally produced by the beam. But because of this decay length, you would still be able to see a signal if this existed. we can make use of this by making a cut on the vertex. We then cut out only a little bit of our signal, but we cut out almost all of our background. And that allows us to get much higher sensitivity than we would without such a cut. Unfortunately, it also decreases with higher masses, and so you get this diagonal line. Above this blue line, your vertex distance becomes very, very small. And so because the mass is now getting larger, this is getting smaller again, and so this vertexing becomes very difficult. And then this is sort of, for us, the golden area where you have centimeters length vertices. Here you get to very, very large detached vertices again, and that's again outside of the range for this experiment. So how do we then detect this? We have an electron beam coming in, a target, there's a scattered electron, and either a radiative photon or a radiative A' that is created. And then we have a decay of that. We detect the outcoming lepton pair, electron-positron pair. When you do this, the A' or the radiative photon will have an energy that is very, very close to your beam energy. That means also that it is produced almost dead forward. So the A' goes almost perfectly with the direction of your beam. The decay angle of your lepton pair goes like the mass over the energy of the pair. And so that means that at large beam energies and relatively small masses, this decay angle is going to be very, very small. So in order to do this experiment, what we need is a very small angle detection of the positron-electron pair. We also need very high luminosities in order to get to these small coupling areas. And we need good invariant mass resolution so that we can actually distinguish this bump over our background. So we need a detector. We recycled the old Primax magnet, we inserted a tracking system, and here you can see the actual setup in Hall B, the alcove in Hall B, where you have our actuators here that allow us to move the target and also move our detector in and out of harm's way around the beam. An engineering drawing shows here the setup a little bit more clearly. We have three magnets forming a chicane, so the beam gets taken a little bit out of the path, then there's an analyzing magnet, and it gets put back on the path to the beam dump over here. Inside our analyzing magnet, you find our tracker. It's about 1 meter long, it has 6 layers of XY tracking made from silicon trackers. And as I said, there's these actuators that allow us the first 3 layers of this silicon can be opened up so that there's a larger gap for beam tuning and allowing us to have a little bit of a safety margin when we first start up the experiment. Behind this tracker is an electromagnetic calorimeter made with lead tungstate crystals in order to provide a trigger and additional energy measurement of the particles that we detect. So just to give an appreciation for what we're actually trying to do, this is the beam eye view. So this is before, just when the silicon was put in our detector, but before it was all closed up. And so you can see that there's a tiny, almost invisible gap here that we have to snake the beam through. It really is only 1 millimeter between the 2 layers, the top layer and the bottom layer of our silicon. That's where the beam needs to go. And you can really pretty much not see it. It's very remarkable that with a 50-meter lever arm, the accelerator people can steer a beam so exactly that it goes right through that gap. I can't do it with this laser pointer. Okay, so we had our spring engineering run. We started installing the eCal. In the end of February, we had our silicon tracker installed, and March and April was used for commissioning the beam line. Clearly, to get such a high-quality beam, there was some time required in order to get that beam at very high quality through our protection calorimeter all the way through to the beam dump. Unfortunately, just before we were able to really start taking data with this setup, we had this power event that you've heard about earlier. JLab had a power outage that took down the machine for quite some time, and actually brought it was almost going to be up until the end of the run period. Fortunately, the administration was graceful enough to extend the run until May 18th. We were then able to start finishing the commissioning of our trigger and the SVT, and we started production running around May 1st at 1.5 millimeters from the beam. This was a little bit safer than immediately going right around the beam. We still needed some experience with the beam, seeing how stable it was to make sure that we don't have a little beam wobble that goes right into our silicon and therefore destroys the detector. After a while of running like that, we realized that we were actually safe. The beam was very, very stable. The orbit locks were actually working well. And we brought our detector all the way down to 0.5 millimeter from the central point of the beam that started at May 12 and ended on May 18. And so here you see a picture of what the track looked like at the minimum opening angle. This is a track right at that 50 milliradian scattering. Beam quality is clearly really important for this experiment, so I do want to spend a little bit of time talking about it. What we need is a beam that is very high quality with a very, very low halo, because anything that is even just a little bit off center of the beam will hit our detector and create huge backgrounds. So we need very low halo beam. We also need a sort of peculiar profile. We need sort of a ribbon. It needs to be fairly wide in X in order to spread enough of the beam over our target to spread the heat load. But we need very small in Y for two reasons. One, in order to stay away from the silicon, but also to really improve our tracking. It makes the vertexing much easier if you know that the beam came from a very, very small spot in Y. We also needed that beam to be very stable over time. We cannot really suffer wobbles of our beam, because any kind of wobble would steer the beam right into our detector. And so we spent quite a lot of time studying the stability of the beam and also studying the fast shutdown. We have a system that allows us to shut down the beam in less than 10 milliseconds if there is a slight wobble of the beam and our halo counters increase by an amount that we can set. And here you see that on May 12, this is really one of the best mornings. From about midnight to 6 in the morning, we have extremely stable beam, almost no beam trips. This was really beautiful data. We thank our accelerator friends very much for being able to provide this for us. So this is what the running looked like. This was opportunistic running. So we would get beam only during nights and weekends. And so starting here at May 1st, you see that we started on a weekend, and you have a nice constant slope up. And then there's class installation during the day. Then you have to come back, you have to close the hole, you have to reestablish beam, you have to reestablish a good quality of the beam, and then we can run a little bit more, and then we shut down again, and we can run a little bit more. Here there was an event in the hall. Here's a weekend again, so we have a little bit more. This weekend was a little bit shortened because there was a tour of the accelerator on Saturday, but here we have some good data again. And then again, we go through this, no running during the day, a little bit of running at night, little steps as we get. And then here, this is the last weekend, was a long weekend of 3 days where we were able to take quite a bit of our data. This is the point where we closed our detector in from 1.5 millimeter to 0.5 millimeter. And so you can see that about half of the data was taken in that last period, the other half was taken in the earlier period. We have about 10 millicoulombs of data at each setting. What we had hoped to do originally was a full week of running at 50 nanoamps. That would have amounted to about 30 millicoulombs. So we got about a third of what we had hoped for at the 1.5 millimeter settings, but that is really. The experiment was actually doing very well. This was a real concern. It was a concern of the pack that this was just not going to work with electrons. And so we saw very quickly when we looked at our calorimeter, these are the rates on the calorimeter, and we can see exactly this hotspot. The beam goes through this hole in our calorimeter, and we can see the hotspot caused by the beam. And this looked very close to what we had simulated before. And so this really gave us confidence that our simulations were correct. We see this also in our online plots. And we see this in the occupancies. This is very hard to read. It's a very busy plot, but we could see that the occupancies in our SVT when we were running at the nominal setting were very close to what we expected from our simulations. Analyzing that data shows that we can now reconstruct for pairs. This is at the 1.5 millimeter setting. And what we can see here is indeed a large area where we see mostly beta Heitler, and along this line would be the data for where the energy of the positron and the energy of the electron add up to the beam energy. And so this is the area where we are going to be searching for those radiative events. We can match our tracks to the clusters that we see in the calorimeter. This is on uncalibrated data, so please note this detector is not fully calibrated. There is clearly some alignment needed, but you can see that the tracker, this is the difference between the position measured by the eCal and the position measured by the tracker. And you can see that we're already quite close. This is in X, this is in Y. And for the energy, we clearly need to do a little bit more work on calibrating the energy here. Part of that is alignment of the tracker. Part of that is energy calibrations of our calorimeter, because this really should be a peak at 1, and it's a little bit below 1 right now. We can also look already at vertices, even though our alignment wasn't done yet. So we did not do an offline alignment yet. This is only using the survey data for lining up our tracker. And we already get an RMS in Z of about 8.7 millimeters, the RMS in Y 0.3, RMS in X 0.7. So this is really quite remarkable without having to do a lot of work for aligning our detector to already get such good vertex results. So all these promising things put together, we can make our invariant mass distribution on a very, very tiny fraction of all our data, an extremely preliminary look. There's a lot to be done before we can take this in the next step and start hunting for anything in it. But this is the kind of spectrum that we will be analyzing to great extent in order to search for a bond. And no, I don't think it is right there.
No, 0.6.
Huh?
0.6.
0.6, right here. Yeah, no, there was actually a paper that claimed that it was going to be at 18, so we might, actually it's going to be challenging, but there's certainly some sensitivity there. But anyway, you can see how this game will proceed. We have a data blinding policy to make sure that we don't get too enthusiastic looking at all the data. We're going to be required to look at only 10% of the data. Then our analysis will have to get signed off on before we can see the rest of it. And anything that is real would then have to survive the additional factor of 10 with total data. That should guarantee that we don't get too excited for little things like this. Most likely just fluctuation. What does this translate to in terms of reach? This was a relatively tiny bump. The contours that I'm talking about are these contours here. And these are calculated assuming 1 pack week of data, which would be this area. 5/7 of a pack week, which goes in a little bit, and 3/7 of a pack week, which is this red area. And so we got a little bit less than that amount of data. So that would be, if our analysis really works completely, perfectly, this would be the kind of area that we can cover with the data that we just took at 1 GeV. On the bump hunt region, we would not be getting any new territory, but the measurement areas are more certain because there the 1.5 millimeter data is also going to contribute significantly. And so here we will at least have a clear measurement, but unfortunately there's no new territory. Other experiments have already claimed this and excluded it. To give you a little bit more of a sense of how sensitive our running is to the amount of data and the settings, if you just take a line right here, right through the middle of this, at 3 times 10 to the minus 9 in epsilon squared, and you look at how does the sensitivity change over the mass, what you see here is that we clearly need to run our experiment as designed with the tracker all the way closed. So what you see here in red is the tracker at 25 milliradians. This is 3 days of data, packed days of data at 25 milliradians, and you only barely get, for a small region or mass region, you only barely get over a 2 sigma significance where you can claim that you most likely have excluded that range. And if you were to see anything, you cannot claim discovery because you really would need 5 sigma signal in order to claim any kind of discovery. If you go take those same 3 days of running, but you close your detector to the nominal setting at 50 milliradians, you get this gray curve. And so you can see that you really accumulate data much quicker at those small areas. You now can cover a larger mass region because now you're sensitive to this lower mass area. And so you get a much better experiment. If you increase that from 3 days to 7 days, you get to the light blue line right here. 7 days to 14 days, you get to this darker blue line, and you get diminishing returns. So at that point, it makes it a lot more sensitive. Instead of taking more data at that energy, it will change energy. The whole curve shifts up to a higher mass region. And that gives you then a new area to search for. And so you'll be able to still say something at those more challenging areas. Adding all of this up, looking at what HPS will be able to do with a modest amount of beam. So this will be 1 week, one full pack week at 1.1 GeV, 1 full pack week at 2.2 GeV, and 2 pack weeks at 4.4 GeV. That covers this dark blue, this greenish region right here, and a greenish region right here. Adding a bit more data at higher energies, going up all the way to 6.6 GeV, extends our data here, both, and it gets additional sensitivity here, and it also makes a big difference here in the blue curve, giving us more reach. This area here, and getting out to the high mass region, is extremely challenging and will require a whole new kinds of experiments. So to conclude, the HPS had a very successful completed first physics data in our engineering run, taking opportunistic beam this spring. We were able to get roughly 1/3 pack week of data with the SVT, 0.5 millimeter from the beam. This will be enough data for several PhD theses for our students who worked really, really hard and diligently on this experiment in order to get it staged and completed in such a short amount of time. It was a very quick turnaround for an experiment like this, building a full spectrometer. Initial look at the data says it's very promising. I think it's very promising that we took high quality data that we will be able to analyze and extract physics from. It also showed that opportunistic running, while class was being installed during the day, I want to emphasize that it really was a very challenging way to run. And it's not, as the previous speaker said, it's not a very efficient way of running in terms of manpower, but it was possible. We showed that it was possible. We could take good data, and that was a really great success, and we weren't so sure originally that that was even a possibility. And we hope that in the next few years we can take a lot more data in order to really make a big impact in this field and cover this region where no other experiment is capable of measuring. Thank you very much.
Perhaps you, perhaps you said this already, but is there an easy way to explain why your experiment has coverage of 2 areas of epsilon squared? You know, one the very low and the other, where all the other experiments just cover the one at the top.
Yes. Because of our special setup and because of this really actually very sophisticated tracker, it's small, it's only a meter, and the areas of the tracker is very small, but it's really, it's very high-end tracker. We can do vertexing that no other experiment has shown capable of doing. So we can make this cut, if you go back to this plot. So what we can do is we can say that we can over here we have the ability to detect whether an event came from the target or came from just behind the target. And no other experiment really has that sensitivity. These other experiments look at an E plus E minus spectrum, often in, say, a collider or in from a meson decay, where you really cannot get any handle on the vertex of that.
Do you have any evidence that you can see events in the data that are? Do you have any, events that trace back to a vertex point that's outside the target?
Well, not outside the target. But so this is our vertex as it is right now. Before we align our detector fully, that should get narrowed. The next step is in data analysis. Now you really are going to do a very, very accurate job of track quality, because you want to make sure that you eliminate all the ghost tracks.
No, here. At some point, you said that the A prime should have the energy of the beam. That basically, I think you were saying the electron gives up all its energy.
Yes, pretty much.
But then on the other hand, you're showing us plots and distributions where the energy or the mass that you're sensitive to is on the order of 20 or 30 MeV.
Yeah, there's a difference.
Missing?
Right, yeah, so there's a difference. When I say the mass, it's the invariant mass. And so the particle that you create, right, you don't create it at rest. So you create this A prime at very high energy, very forward. It decays, giving a very energetic electron and positron that have about half the beam energy each. But when you calculate back,
okay, no, I get it. So then the follow-up question is, why should the A prime get all of the beam energy? What is the physics that says that the electron gives up all its energy to this thing, and not just, shaking off a lower energy thing like when you're doing Bremsstrahlung or something?
Yeah, it's a different process from Bremsstrahlung.
No, I know it is, but why is it different?
In the radiative case, you have exactly the same thing. So the radiative production, this photon dominantly has the beam energy. It's not all of them.
No,
but
but
the
why?
spectrum is,
Why?
Why? Let's go back to field theory. This is not my strong point. I'm not a theorist, but this has to do with the same thing as Compton scattering is also very forward. All these processes are forward.
So that means that
off-shell electron is minimum off-shell if you're carrying all the energy by that photon. Because you have to carry mass. The dielectron pair has mass, so you want to be as on-shell as possible. You want the photon to be as on-shell as possible.
This is casting on a nucleus, on the zero nucleus. There is no energy transfer. There is no momentum transfer. Anything you produce with any significant mass and you push it forward. It doesn't mean that they produce all that energy of the beam, but the spectrum is sharply dropping from beam energy to down just kinematics, very cold. The photon is zero mass because exactly opposite direction.
Yeah, but this problem is normally the Bremsstrahl's spectrum goes like 1 over energy. So he's right. I mean, that's how the Bremsstrahl's spectrum goes, and it doesn't matter whether you produce a particle. The Bremsstrahl's spectrum goes like 1 over E gamma. N gamma, E gamma over E gamma is constant.
No, but when you give your photon mass, it's not exactly the same Bremsstrahl.
But you only give it 30 MeV. That's his problem.
Huge compared to the electron.
Yeah, it's a very high mass.
It's small compared to the beam energy.
Before we solve this problem during the coffee break, I was just going to go back to this vertex distribution. And already it does look to me as if there are more events to the right than to the left, which gets me to ask, so you consider beta Hadler and radiated events, which are spider events in the main background. At what level do things like any particles that get produced in the target and then decay, other than as A prime, contribute? Like, for instance, Stalic's decays of Hyman theta or something you name.
I think that
is the case of pi zeros again decays promptly at the target.
Yeah.
So you don't have the sun.
that I know of decays promptly. The reason that it is a little bit higher here than here has actually nothing to do with particles. These are the ghost tracks. So what you get is you get spurious events in your detector, and you're much higher. Your likelihood of having a spurious event or spurious hit in your tracker, in your first layer tracker, that is closer to the beam than the actual hit of the particle that went. Right. So if you have your strips, and you have an accidental hit here, the actual hit is here. Your tracking might actually choose this hit, and it points a little bit further in, and that gives you a fake detached vertex. And so that's where we need to really control the tracking very, very accurately in order to actually get rid of the excess of events here, which is due to accidents. We show this in Monte Carlo as well.
We can speak up like this. How well do you know your mass spectrum and possible backgrounds and your resolutions? Or you're just trying to get the background from the data itself and just make us look for bumps?
We will just be looking for bumps. We will be able to cross-calibrate the tracker and the calorimeter in order to get a energies and mass resolution. We expect the mass resolution to be 3 to 4%. There is very little in terms of data that we can do that gives us a signal that you can calibrate against. Say the phi is too heavy, so we don't really see that. So it will be a challenge to get an absolute, really high accuracy mass calibration, but we don't really need it because it's all relative anyway.
So, what vision
Yeah, it's actually fairly much covered now. So the muon excludes this region above here, And the favorite region is right here. It's now already buried by various exclusions. And so had a A prime been discovered along this green band, that would have fully explained the anomaly.
And there is partly violation in the garden of A prime, there should be also some constraints. So the A prime would couple the partly violation instead of coupling the
Yes. We're talking about even smaller. I don't think you want to look at this very much.
Okay, thank you very much, and Maureen.
three-dimensional nuclear structure, which Shandong was going to talk about. And I will talk about more technical stuff. And also there is this difference is also started from the start, because in his first paper it was GPDs were introduced as a means to study proton spin, while in my first paper it was written whether it is related to proton spin or not. GPDs are interesting on their own. And of course, I mean, in 1996 they were not called GPDs. We called them forward Parton distributions. Then there were other names, non-forward Parton distributions, non-diagonal, off-diagonal. In fact, before publishing my paper, I came to Nathan. I said, Nathan, what is a good name for the stuff? Because my feeling is it might be important. And what is your idea? Okay, I said non-forward. Okay, that's very nice, very nice. Then finally it was skewed Parton distributions for some time, but when people started to treat it seriously, it included as one of motivations for upgrade, I was told that no guys, skewed sounds like weird. We should be doing serious stuff, so it is, it was not invented by G, it was not invented, I mean, the name by me. It was invented by a group of experiments who decided it should be generalized. Okay, so as I said, that for me it was playing with Parton distributions is the main business of my life. And the point is why we are talking about distributions is like what we are doing with dealing with ECD and what differs ECD from, say, Higgs discovery? That all relevant particles are established, force and gluons, Lagrangian is known, and only we need to understand how ECD works. And also, I mean, Higgs explains the mass. No, you know, 96% of proton mass is gluons, and gluons are massless. That's the mass. Understand mass from mass is confined. Okay, so how, all another problem is confinement, how to relate hadronic states which are observed to quark and gluon fields into Lagrangian. Then the center way just do projection, take the fields and project on matrix elements, you get meson quark matrix and variant quark matrix element. And one can try to interpret these objects as hadronic wave functions. And in fact, there is approach like conformalism, which is explicitly deals with wave functions, but because it's quantum field theory, you can fork composition, every hadron is infinite tower, and so describing it by something like Schrödinger equation, I mean, it looks nice, simple, but E is here infinite tower, so in practice, these equations have not been solved and unlikely to be solved in the near future. Now, Stan Brodsky at this moment always said, oh, they were solved in 2 dimensions. Unfortunately, our salary comes in 4. Okay, so in these situations, what we can do in terms of logical functions? Okay, what do I mean? The old functions are form factors, fusion particle densities, distribution amplitudes. And new functions are these exactly the generalized Parton distributions, which are hybrids of form factors, Parton density, distribution amplitudes. And the old functions are limiting cases of new functions. In fact, there is a hybrid of hybrids, which is a linear function, which is a hybrid of GPDs and TMDs, but I don't know. Discuss this closer. Okay, so for factors are defined by matrix elements of local operators. We can have 1 or 2 possible structures, and we have 2 for factors and 1 and 2 for nuclear. The point is that the fields are taken in the same location. Usual pattern densities are also given by matrix element of my local say operator. But now taken in different positions, and then if you like symmetry, you can take it minus b plus 9 by 2, b divided by 2. But they are taken on the light cone, not in one for 0, z equals 0 by z squared. And definition of pattern densities is given here. So you take matrix element and write it as decomposition in plane waves, and immediately that gives us momentum space interpretation that these functions here just describe your fields with momentum xt by now. And also important is the set of x probability. And so if you take now local limit, because z equals 0, z squared equals to 0 and z equals 0 may be realized together, so then you have reduction from factor to just number of valence cores. Okay, so as I said, the GPDs will be hybrids of usual former known functions. Okay, so let's try to combine form factor with pattern density. So then what we will have will be something with fraction x and also with momentum t. So basically that means we can write form factor as the integral of x of something like can be called non-forward pattern density. And we can do non-forward, can do flavor composition also. If you take t equal to 0, you reduce it to usual pattern density. And so you see that at t equals 0, it reduces to usual pattern densities, and also it should give form factor after integration. So if you just write it as a product, then both conditions will be trivially satisfied. But if you take like on formalism, take simplest Greek function, you immediately see that it is not as simple as that, and there is no trivial interplay between x and independence. And even with these simple Gaussian models, one can describe the product form factors. If we are talking about three-dimensional, then really the point is that if you take Fourier of form factor, then your function will be dependent on x and even parameter, and that is what normally considered to be three-dimensional description. And impact parameter here is distance to center of momentum, as Matthias Bucher told us. And so it describes the Euclidean structure in transverse plane to propagation, and that is some two-model function. Also, it is important that these input parameter dependent distributions have formalistic interpretation, and so one can look at z direction as direction of propagation, and R here will be notation for input parameter. So with respect to input parameter, we have something like charge density distribution. With respect to the z direction, we have x dependent functions, not usual pattern distributions, and together they give you the stuff. And in fact, we all love when something you did is cited and count citations. So this picture probably has zillions of citations. It was presented many times, but I never seen the reference. Who did it? The answer is idea of the picture is mine and implementation by Andrei Pilitsky, and copyright is now with the report about pattern distribution. Okay. So if one will do not just this Gaussian, but some more complicated stuff, namely embedding rigid type behavior for small t, which should be here, and also doing different models for functions which contribute to F1 and F2, namely different power. One can, in fact, describe all four nuclear form factors F1, F2 for GM for both proton and neutron. So that was done like 10 years ago in paper, our paper with Michel Vidal and Van der Hagen. And the point is that it described these form factors even in QCD when it had predictive power, not just fitting the curve. Okay, so now I told you that there is this third ingredient, distribution amplitude, which should be also taken as a part of this hybridization. So distribution amplitude is a function like on the light cone, but in exclusive processes, when you are dealing not with quark and anything else, but exactly say with 2 quarks in meson, 3 quarks in baryon, and so on. So then you also have, like for pi and pi local operator on the light cone, but now the brackets are asymmetric. You have total momentum flow in that direction. And then you introduce the function which is distribution amplitude, which describes you how this momentum is shared. So now we are ready to go to GPDs, and the process in which it is visible is deeply neutral compensator or deeply neutral meson production. So that is the cartoon. So here you have hard interactions, and it is carried like QCD, and soft part is exactly GPDs. And kinematics should be specific. Q squared should be large, S should be above resonance region, ratio X Birkin is fixed, and T is small. And especially this condition is difficult to realize having low energy, so 12 GeV upgrade probably will be a big step in this direction. Okay, so the point is that it's like we can, to understand what is new in GPDs which was absent in other, in previous functions, is that like look at DVCS in virtual gamma and nuclear stellar mass frames. Then along the direction we have virtual photon and real photon, real proton colliding, and in final state we have real photon and real proton going again along this the same z-axis if t is small, which is assumed in the definition. So that means we can use these guys as two bases. Momentum for z direction, and so that means virtual photon momentum is q prime minus x Bjorken v as easily calculated, and that means that momentum transfer should have z direction. So we used to think about the momentum transfer being like exactly perpendicular, transverse. No, here it is exactly you need z component or plus component in momentum transfer, and that is something which is specific to GPDs. It should have a GPU component, and if you are measuring momentum in terms of initial proton, this fraction is simply x Bjorken. Or now you can describe, say that you are doing this skewed kinematics, so that kinematic is still skewed, not generalized. And for the VCS, this skewness is equal to x Bjorken. And so in my second paper on the subject, I introduced these non-forward Parton distributions with skewness parameter being exactly x Bjorken and forward limit with usual Parton distributions. And it is not trivial because this non-forward Parton distribution is an inclusive object, while usual Parton density is produced by inclusive reactions by summation over all state. but still zero skewness limit remains these functions, and if you keep t, you reproduce the x. Okay, so also you can relate it to form factors, and if we are careful with kinematic factors, there is this one of minus x divided by 2, which you should use to relate this non-formal distribution to t. Originally, Chandon proposed so-called off-form part distribution, in which momenta are measured with respect to average initial and final moment of the proton, and so then instead of p here you have 1 plus cp, 1 minus cp, and also you have these guys here. There is translation, and c is related to x working by this formula. And there are 4 GPDs, H, E, H field, E field. And the point is that there are 3 regions of increased GPDs depending on relation between X and this skewness C. We have Clark distributions, anti-Clark distributions, and distribution amplitude in central region. So when this pair looks like a measurable. And these are forward distributions, which now are called generalized particle distributions, can be also related to form factors and forward densities. So that is a relation to forward densities. And this is just some rule, exactly for which Chandon invented this stuff, so that if you take H plus E at t equal to 0, integrate over x, you get a contribution of Kvartov species I to proton spin. And for some reason, instead of F, I use here I. Because it is some. But also you can relate to form factors, there is no kinematic factor. Okay, so now to find GPDs, of course it's nice to look at GPDs and see how they look like. But if you have no idea how they will look like, probably you'll find nothing. Because you should extract them from data. Data, as we know, have some complications. So it is important to model GPDs, and there are basically 2 approaches. You can just take some dynamical model and calculate them, and so make model kind of or you simply just do physiological construction, because we know that in some limits they will reduce to known functions, and then with some fantasy you can try to see what how they will look like. And this fantasy is strongly restricted by the fact that these GPDs are related to so-called double distributions. And double distributions, in fact, this is what was described in my first paper. So I should confess that in my first paper, based on double distributions, I was trying to understand scaling limit of deeply virtual scattering, and I wrote the formulas which are correct even today, but I was not able to reproduce G's formula for deeply virtual scattering. Only in my second paper I found relation between these double distributions and GPDs. Okay, so what is double distributions? So if we take our basic object here, like one momentum, initial momentum, final momentum, and decompose it into average momentum and momentum transfer in z direction, we can write this combination as superposition of momentum flow in S channel and in T channel. And so the point is that in with respect to P or beta variable here, it looks like usual pattern distribution, and with respect to momentum transfer, it looks like distribution amplitude. And now this double distribution is exactly the function which describes fractions of initial average momentum and momentum transfer, beta and alpha, and you can connect it into GPDs using the point that this guy X should be given by beta plus C alpha. And the forward limit of these guys also gives you usual pattern density, just like GPDs for C equals 0 and T equals 0 give you usual pattern densities. This can be translated on condition of double distributions, U. And the life of double distributions is restricted by this rhombus from -1 to 1, from -1 to 1 inside. They are living, so integrate over vertical line, you get usual pattern distributions. To get GPDs, you should say what kind of C you want to connect it with the corner and then scan it with parallel lines. So that will give you GPDs from double distributions. And in principle, it looks like a movement. Okay, so again, our fantasy is here. It allows us to use a simple factorized model. It should be usual pattern density in beta direction and solution with alpha direction. So that is exactly implementation is beta function being something like 1 minus beta cube. And so when you scan, you get the function which, if you take C equal to 0, it reduces to usual pattern density, this function, or when you take C equal to 1, it reduces to profile function similar to distribution. Okay, so now that is simple, of course, naive. In principle, the idea is to reconstruct GPDs from what we know about usual pattern densities. But there is something which will be invisible because like X smaller than C region is the region in which you have something like meson propagating from the core. There's no relation to forward density. So these terms will be missed. So if you have meson exchange in this channel, or even two meson exchange, and exactly so-called D term is the guy in this structure. You will be missing here. So the model is just reconstruct from forward limit plus and D term. And this picture was created by Mark van der Hagen, I don't know, probably 15 years ago or more. But still, it reflects all the story about an important point when you are making this hybridization of forward distributions with part distribution amplitudes, this is the profile. You more or less have the same profile in direction of x, but in perpendicular, you may choose whatever shape you want. And basically, like this combination here is just keeps the double distribution on the rhombus. The parameter of the game is B, so how wide is your profile? So depending on this profile, you get different GPDs. And again, like 10 years ago or something, people were fitting asymmetry data using these models, and they choose different possibilities for this parameter, and more or less they described it, and I looked at the recent talk by somebody on conference, and believe it or not, curves look very similar to this one. Okay, so, but life may be ugly and complicated. Just like I said, the idea was take forward distribution and do the profiling and everything will be nice. But further development demonstrated that, in fact, projection is not to pattern density, but to pattern density divided by x, which is much more singular function, especially if you take also range behavior for original which will 1 over root x or 1 over x or divided by x. So the point is that still if you integrate vertically, no problem. Just for every point x, integrating vertically, you will produce your favorite part of density. But the point is that if you integrate horizontally, you should get detour, and if your function behaves like this, you will never get finite answer, because just like debate over beta. Arithmetically divergent, any small power here, it will be divergent, and also what is bad, that it will be even function of this guy. So whether we like it or not, we should use some highbrow mathematics, plus prescription, which is equivalent to normalization. We are just subtracting infinity like we are doing in quantum field theory, and saying, you know, the term is finite. Okay, to make this long story short, that is the result for GPDs in this new construction. And it looks like hopeless to extract it from experiment point by point. The good news is that what we really need to know is GPD of the diagonal or border function x, h, c, and t, of course, and d term. Just these guys are non-trivial. All these beauties are reconstructible. And so I'm very optimistic. New precise JLab data we just reported, and so what we have now, exciting time for extractions of GPDs. And concluding, what we can say, the theory of GPDs is well developed. There are several big volumes. I also am guilty in contributing to one, which is one of the longest. His reports exist in 100-something pages. And so new precise data are ready for GPD extraction, and also 12 GeV data on PVCS and DBMP. Also new proposals which I didn't ideas behind them I didn't touch in my talk is time-like compensator, double deeply virtual compensator, which are produced also extend range. And finally, I want to say that progress in GPD field is the result of collective effort of many theorists and experimentalists, and returning to beginning when I said that this talk is reflecting some award, I should say that I want to emphasize that it was a collective effort, and especially I would like on my side that there was push from experimental side also, because Charles Hyde was always saying, why you are not doing virtual content? You should do it. So he was extremely instrumental. Also, I want to thank my collaborators, Igor Musatov, Lev Mankevich, Christian Weiss, Michel Vidal, Maxim Polyakov, whom I wrote some of the papers on GPDs. Also, I would like to thank Elizabeth Pease, Steve Wallace, and Charles Sukenik, who nominated us for this award. Also, I thank Bob McKeown, who was leading the committee which made the decision. Also, I should say that I always felt encouragement from Directorate of Jefferson Lab, starting with Nathan Isgur, Herman Grander, Larry Cardwan. Hugh was always sympathetic to what we are doing, and theory group leaders, Nathan was already mentioned, Tony Thomas, now Mike Pennington, always, I always felt they are supporting what we are doing. At Old Dominion University, Gail, as active participant, was always sympathetic to our business, and Jim Cox, though he was atomic experimentalist, and Charles Sukenik also was very helpful. And finally, I thank all of you who are here, who are not here, and With your support, we will finally produce another fusing port with GPDs for every species, every flavor, and other sphere configurations. Thank you all very much.
Very nice discussion. Any questions? Time for a few shots.
Everything was clear, and especially like compared to real talks on this, that was very simple.
Okay, let's thank the speaker again and move on to the next one. The next speaker is the postdoc winner. That's Raul Ricino. He's going to tell us about the exotic frontiers of lattice music.
Can you hear me? Okay. Thanks everybody. So I also want to start with a big thank you to the JSA, the JLab user group, everybody here, and some of my mentors, supervisors, and colleagues for all the support. If you're not here, if you're not shown here, I'm also very thankful. So let's just begin. So when I first came to JLab, which was about 1.5 years ago, Joe Dudek and Robert Edwards asked me if we could possibly do hadronic, so meson photo production or electric production on the lattice. And immediately I said, sure, we can do that, not really knowing how and if. So then I went ahead and started thinking about this and the possibility of actually trying to do this directly from QCD. If you haven't thought about this much, which I had at the time, here's a little cartoon of this process. So you have some external probe coming in and probing some target, in this case, proton, which is made of quartz. One of the photon hits one of the quartz sufficiently hard that it drags it out and it drives away one of the quartz out of the vacuum. These are confined, so they have to go on alone, and they have to go out together. And lo and behold, we have a proton and a pion in the final state. So that is a basic idea of meson or meson photoelectric production. But this on its own is not really interesting. Why am I actually interested in these types of processes? That's because I need to mention GlueX, not just because I'm getting paid by the lab, but because I think it's actually a really interesting experiment. And what they're trying to do is to carry out this process where you have an external probe hitting a proton target and creating a meson, but not just a pion, but something more rare like a pi 1 1400, which the reason being because it has exotic quantum numbers, so it has quantum numbers that are not consistent with a simple quark model, right? But it should be consistent with QCD. If you want to study such system, it is a hadronic, so it is a QCD resonance, which means that it can decay strongly. So it has a rather large width, and it can decay strongly to 3 pions, but it also has the same quantum numbers as a pion and a B1, and also the same quantum numbers as a pion and eta prime, and you get the idea. So there's many open thresholds below this one state that one would like to study via experiments or via QCD. So this is certainly a hard problem. This is a few-body, strongly coupled multi-channel problem. This is very daunting. And the message that I want you to take away today is to not panic. This is the direction that we're going, but it is a challenging problem, but I think that it's doable. So I would like to explain some of the steps that we're taking towards being able to study these types of processes directly from QCD. So the, QCD Lagrangian we've known for a long time. It's very simple. I can write it down in a single line like this. And the beautiful thing about it is that it consists of, essentially 6 parameters. So lambda QCD, the up, down, range, charm, and bottom quark masses, which along with alpha QED, so along with QED, describes everything that we do, everything that we're trying to study in nuclear physics. So that's really compelling. Just wanting to understand one equation that can in principle describe everything. But as we know, this is a theory that is non-conservative. So that is a big drag, and that's really why we still have nuclear theory. If we could solve this, basically your jobs will be essentially done. And the only way that we know to this day to actually study QCD at low energies is numerically. We say, look, at this point we can't really solve it analytically, so let the computer do all the hard work for us. And this is a basic program of lattice QCD. In doing so, in order to write down this equation into a computer, we have to do a couple of things. So let me walk you through those. First, the basic notion, the basic name. So lattice QCD, what it refers to is that we put spacetime in a lattice. So spacetime is discretized. So here, for example, I'm on my little proton and mesons, and they have to lie and they have to exist in a Euclidean spacetime that is discretized. So we introduce some separation scale, which is the lattice spacing that separates all points in space. But you can just think of it as a UV regulator. And it's a very small scale, so it's in the order of 0.1 Fermi these days. Furthermore, if you had an infinitely large Euclidean, infinitely large lattice, and you tried to put that into the computer, your computer would just simply run out of memory. So that is impossible. So in order to be able to put it into a computer, we truncate spacetime. And so we set this spacetime into, we truncate it to roughly the lengths of the scale 4 to 6 Fermis. So it's a very, very tiny world, and they're typically performed in a cubic. So the lattice calculations are typically performed in a Euclidean, in a cubic space, in a cubic geometry. The third step is you just simply have to tune the quark masses. Once you tune the quark masses, you can make any prediction you want. It has everything. Once we set the up, down, strange quark masses to their values, then it includes the 2-body, 3-body, 4-body, n-body forces. It includes everything from QCD. This is a technically challenging problem, setting them to be physical, so typically calculations are performed on unphysical quark masses, but there are calculations being performed at the physical point now. And finally, you simply make a prediction. And this is this hard step, and I'll talk about the challenges associated with these in just a second. One of the main subtleties that arises is that when we put particles in a box, the notion of asymptotic states simply goes out the window. When you go into quantum field theory, basic quantum mechanics course, you think about asymptotic states coming out from infinity, interacting for some instant of time, and then going out into infinity. If you put these particles in a box and you make that box periodic, they cannot go to infinity. So there's no notion of asymptotic states. Therefore, we can't really do scattering on the lattice. Nevertheless, the fact that we put particles in a box allows us to extract the finite volume spectrum. And what I'll discuss in just a second is that we are able to study the S matrix. So we are able to extract the scattering parameters from the finite volume spectrum. So before I talk about what my collaborators and I have been working on, I just want to give you a little sense of the present day state of the art. So there's a calculation by the BMW collaboration where they've determined mass splittings for various different variants using dynamical QCD and dynamical QED. So there's everything. I mean, this is a mass splitting of variants, including everything in it. And so this is really impressive, and you see that they compare rather well with experiments and even make predictions. Another nice plot is a summary plot, which is a summary plot by the Flag group, this is 2013, where they summarize the determination of Fk over Fpi by various different lattice QCD collaborations around the world, using various different approximations for the discretization of spacetime, so different actions, They've used different quark masses and extrapolated to the physical points. Some are done at the physical point, and what you find is a broad consistency between all of them. So this method is really working, and that's the take-home message. And so you might be tempted to say, you know, is that the research and development phase, in other words, the R&D phase of lattice QCD is over. You might just say, you know, at this point we can pretty much extract whatever we want from the lattice and directly compare it to experiments. And the answer is, you know, for simple observables, yes, we're getting there. I mean, physical, for masses of stable particles, we're definitely there. We're there now, decay constants, and you know, these are places where the R&D phase is almost over, and where, you know, everything has been taken into account. In more exotic systems such as QCD resonances and many body observables, there's a lot more R&D to do. And that's actually where I've been focusing in most of my research for the last few years. So I want to give a couple highlights on this, and I'm not going to go into much math, but basically a year ago, I was able to find a direct relation between, the most general relation between finite volume, the finite volume spectrum of 2 particles in a box and infinite volume scattering phase shifts. And this was after various different works with different collaborators, or that would be in Tom Liu and Martin Savage. And the basic idea is that, you know, we extract the finite volume spectrum, and that gives us directly phase shifts. Okay? And alongside with Max Hansen and Andrew Walker, we grab these ideas, and then also we're able to show find a relation between finite volume matrix elements of 1 to 2 systems, and relate that to 1 to 2 transition amplitudes in the infinite volume. So this circumvents that idea of not having asymptotic states. And so you might say, okay, this is really cute. You know, you have found a mapping, you know, that claims is model independent and is general, but why should we care? You know, what does this give us? So let me walk you guys through a couple examples. First, let me discuss some recent work on the spectrum of 2 particles in a box. So I think it's useful to first introduce a little toy model to give you a little more sense of what's happening. So if I put a single particle in a box, so there's my box in a 1 plus 1 dimension, so time is it's perpendicular to you, and I make the volume periodic, that's just a circle, I put my particle in my box. I can define the wave function of this particle, which is a plane wave. If I require this wave function to be periodic, meaning that L is equal to 0, then that gives me a constraint on the phase. You know, that tells me a constraint, that gives me a constraint on the momentum that I can have. Basically, it has to be discretized, and it's inversely proportional to the volume. So that's simple enough. If I put 2 particles in a box, life gets a little more interesting. So I can define X to be the separation between these 2 particles, and then P to be the relative momentum between these 2 particles. And I play the same game. I can, if the particles are sufficiently far away from each other where they're no longer interacting, then the wave function is equal to e to the I p x plus a shift in the phase, which is the infinite volume phase shift. Once again, if I require this wave function to be periodic, that gives me a constraint in the phase, which tells me that the phase shift, now this is the infinite volume phase shift, is related to both, it's related to the volume, and in a way, so it depends on the energy at which it's evaluated in the volume. So let me give you a little more intuition of how this equation works. So here, what I've done is that I've generated some random phase shift. It's just a polynomial in momentum, and it's a function. So it's a function of momentum here. I put it into this equation. I set n equals 0, and then I solve for the momentum as a function of the volume. And that's what I get. If I set n equals 1, I get this line. If I set n equals 2, I get this line, and so on. But what we do in the lattice calculation is the opposite problem. We actually extract the spectrum, we put it into this equation, and that gives us the phase shift. So this is roughly how it works. If I determine the spectrum of the ground state at 7.5 Fermi, I put it into this equation, I set n equals 0, and I get this point for the phase shift. If I then get the first excited state, I get a different kinematic point for the phase shift at the same energy that I've extracted. If I dial the volume, I get another one, and another one. And you slowly start to map out the phase shift from the finite volume spectrum. That is the basic idea of this formula. In 3 dimensions is more complicated, but there's really no point to go into it. This really illustrates everything. And so this has been exploited by various different groups on various different observables. And one of the most beautiful results is by some of my collaborators in the hadron spectrum collaboration, which have determined the pi phase shift. So all these little points, you see, these are all energy points that they've determined. They put it into a generalized equation that I talked about, you know, the actual equation that describes the three-dimensional spectrum, and they get this phase shift. So they get the spectrum, put it into that equation, they get the phase shift, then they fit it to a Breit-Wigner, and they're able to obtain from the phase shift the energy of the rho, the energy of the rho, which is complex. Nice example because it illustrates that even though the rho itself is not a particle, right? It's not a stable particle. It's never going to hit the detector, and it's not an eigenstate of QCD. What we can actually obtain are phase shifts from the finite volume spectrum, which we can then fit, and then from there analytically continue them. Analytically continue amplitudes into the complex planes, extract the poles which are associated with resonances. So that's one way to study resonances from lattice QCD. Oh, that's unfortunate. So I don't know what happened. I wanted to show a plot of a more challenging problem, which is the two-nucleon system. So here, you have roughly 30 kinematic points. In the two-nucleon system, the first determination of phase shifts has been done by NPQCD, and it was a calculation done at 800 MeV, and it was it's a plot worth seeing. But the point is that studying two-nucleon systems from lattice QCD is far more challenging. And so up to this point, the only determination has been of two nucleons in an S wave. So the spin triplet and spin singlet channel. And so my collaborators and I from the JLab collaboration decided to investigate whether we can extend this and be able to study not just even parity S wave two-nucleon scattering, but also study P wave or even D wave two-nucleon scattering. And so here's an example of the results that we're finding. So there's a preliminary result, and what you're seeing here is a 3p2 phase shift. So q cubed cotangent delta. The points with error bars is the results from the lattice QCD calculation. It includes 2 different points, and for the experts on the field, on the audience, they correspond to 2 different cubic irreps. So what this is really showing, so one nice thing that you see is that this function, which is supposed to be an analytic function of the energy, is simply flat. It's just a constant, even above the T-channel cut, where you would expect logarithms and arctangents and so on. So it's simply flat. And also, the nice thing of this example is that it really is illustrating that the finite volume formulas allows us to extract phase shifts, from different cubic irreps and different volumes. So it's really working. I can then, from here, extract the phase shift. Oh, and I should say, the band is my fit, which is just basically just a scattering length, or in this case, a scattering volume. I can then grab this and plot the phase shift, and if you're familiar with this particular channel, it's also a repulsive channel. On the physical point, it's slightly less repulsive, so a heavier pi masses just seems to be more strongly repulsive. Oh, sorry, attractive. Take everything I just said and replace the word repulsive with attractive, and that is correct. So there is a more attractive channel than these quark masses, which are rather heavy, than one sees in the experiments. Another place that we've seen a little bit of progress, and that I was alluding to in the beginning, was regarding the matrix elements of 1 to 2 systems. And so I just want to point out that the formalism that I developed with Max Hansen and Andrew Orcolado has made the following calculation possible. So without this formalism, we couldn't do the following calculation. So here, I've been doing some work with my collaborators, the hadron spectrum collaboration, and what we've done is an exploratory calculation of pi gamma star to pi phi. So where the pions are in the rho channel. And so it allows us not just to extract pi gamma star to pi pi, but also pi gamma star to rho. This is again done at heavy pi masses, and we've done an extensive determination of these matrix elements, including roughly, it led to roughly 500 matrix elements, which led to approximately 40 different kinematic points. So it is a drastically more simple problem than the than the two-variant sector. So you might ask, why should I care about pi gamma star to pi pi? Well, first off, it's a building block to more challenging processes. For example, n gamma star to n pi pi. So if I want to determine, one of the possible contributions for this type of reaction would be, you have a nucleon coming in, it emits a pion, which then hits an external photon and creates, creates another meson in the process. A second reason is, well, it's a testing ground for a more challenging process. Up to now, there has been no lattice calculation of this kind. So we need to, if we're going to do the first, we want to do the simplest one. So once we understand the lessons learned here, we might be able, that might allow us to then look at, for example, n gamma to n pi pi. Third is related to the G-2 puzzle. So there has been proposals to study G-2. So one of the contributions to G-2 is the hadronic light by light. So it's this diagram, the light by light contribution, which has a hadronic piece where basically you have two photons coming in, and then you have everything allowed by QCD in between, which would be hadrons moving through, and then two photons going out. And this diagram contributes to the new and magnetic moment via this way. And this is an interesting problem because there is tension between experiments and the standard model. And it turns out that this diagram can be studied using dispersive techniques. And one of the inputs into the determination of this amplitude of this diagram is this amplitude. So here's some preliminary results from this calculation, which hopefully will be coming out soon. And what I'm showing here is the transition amplitude of pi gamma to pi pi as a function of q squared here. So we don't just get the q squared with the photons on shell, but also various different q squareds in these fine units of n pi, inverse n pi squared. And here is the amplitude as a function of e pi pi, which is the center mass energy of the outgoing two pion states. This is the three-dimensional plots are always a little hard to read, so let me project it into a two-dimensional plots. And so here I'm just showing the same thing for q squared equals 0. This is band q squared equals 2 n pi squared. This is red one. Q squared equals 4 n pi squared, and so on. And below, so this is a function of the energy. So we're sweeping the energy of the final state here. And below what I'm plotting is the phase shift, the determined phase shift of the pi pi, so the pi pi in a p wave. And what you see is that as we go through the resonance point here, this amplitude gets a nice bump. And that is really nice. I mean, this wouldn't have been possible without that formalism that I discussed earlier. So it's really nice to see that the formalism along with lattice QCD is leading to something that makes that you would intuitively expect. And the nice thing is that we get the full amplitude. So we have the pi gamma to pi pi, the full amplitude. We can actually analytically continue this amplitude onto the rho pole and get the residue of this amplitude, which is the pi to rho form factor, where now the rho is on shell, so it's an actual honest to God particle. And so it looks, we get the real piece and also the imaginary piece. And this imaginary piece hasn't been determined before. And so what I want to show last is this plot that many of you have already seen, which is one of the many plots of the spectrum that is being extracted from hat spec. And just point out that, look, the exotic spectrum is already being determined. It's already there. And the main limit right now is the formalism to map these quantities, these finite volume energy levels, to the corresponding, physical quantities that we would be determining. So, connecting this, say, with data spots, phase shifts, and so on. What is missing right now is the formulas, and that's, what we're trying to go towards. But I'm really hopeful that we'll be able to develop it, and that we'll develop all the tools that, that are going to lead us to be able to analyze these energy levels. And lastly, what I want to leave is, this might sound somewhat crazy, that we're really trying to study these, multi-channel, multi-particle systems with many open thresholds, and people might be a little skeptical that whether it'll be achievable. But here's one place where like history is really on our side. I mean, there's many things that people were said that at some point that, or at least thought, were impossible via lattice QCD, and Ken Wilson, who was the founder of the field, was one of them. And then in 1986, lattice QCD conference, he expressed his doubts about the timescale of lattice QCD. But with time they grew wiser and said that in 2004 in the lattice QCD conference he went to congratulate the community on his success. And so I think with time, everything that we find to be challenging and limit us, we'll be able to circumvent. So I think all we really have to do is just think harder and just go for it. So with that, I would like to thank you all.
Questions for all?
Okay. So thanks very much for the nice presentation. If I get correctly, you, with the pi gamma goes to pi, basically calculate the chiral anomaly on the lattice. Is this correct?
Yeah. So okay. So I've been asked this question before, and I think it's so we could in principle. So I mean it's QCD, right? So it includes everything. So I mean the chiral anomaly should be there. At this point, so one thing that I worry about is that I think it actually is a sub-leading. It would come in at higher orders in QED. And so right now we're just calculating the leading order. We're treating QCD non-perturbatively, but we're treating QED at leading order only. And so it only is a matter of where does the chiral anomaly come in, and I think it comes at a higher order in QED.
Okay, but compass measures pi gamma, pi exactly this process from threshold over the row, so in principle it's all in there.
Right,
now
exactly.
You get the answer. Second question is, once you do this, can you in general address radiative width of methods?
Yeah, certainly. Yeah, I mean, I think that would be something that we'll be able to do in the future. I mean, right now, so there's many challenges that are rising now that I don't really know that I haven't really thought about. I don't really know the answer to just yet. Which is we have an amplitude depends both on Q squared and and energy, and I think at this point what we want to present as a result as it stands. But I think in the future we'll be able to exploit a lot more of this data with more sophisticated analysis. And there's somewhere where I think we'll be able to learn from experiments, from experimenters. So.
Any other questions? Okay, if not, let's thank the speaker. The next two talks are the two thesis co-winners. The first one is Adesh Subedi, who is going to tell us about the cubic experiment.
Today I'm going to talk about the cubic experiment, but in slightly different context. This will not be a regular cubic talk in the sense that the results I'm going to show are from my thesis and are not collaboration with yours. But this also means that you will get a sneak peek of things that you have not seen in our collaboration with those talks. So this is the setup of cubic experiment back in 2010. It ran in Halsey of Jefferson Lab from May 2010 till May 2012. We took data for about 1 year infinity run TDS, run 0, which has been analyzed and published, and I'm sure you have heard about it a lot of time. And run 1 is the data on which my dissertation is based, and that was from February till May of 2011. And this is about 1/3 of the total data, and we are in process of finalizing our, getting our final results. So the outline of my talk, I will tell you the motivation behind the QUIC experiment and introduce you to the QUIC apparatus and talk some of the things that I did in my dissertation. And I'll talk about the blinded run 1 data analysis. The result is still blinded, and all the results I present will be very preliminary because blinded. And then I'll tell you how we extract the weak charge of the proton and then summarize my results. So what is the weak charge? The weak charge of proton, the weak charge is we can think of it as the neutral weak analog of the electromagnetic charge. In an electron proton scattering, we have the amplitude, we have the electromagnetic interaction amplitude which dominates the scattering, and at the same time we have this electroweak or parity, which is parity violating amplitude as well in the same scattering process. And because of the parity violating nature, we can access this asymmetry, the electron-proton parity violating asymmetry, which is given by the difference over the sum of the cross sections at two different helicity steps. And this quantity is very small, of the size of about minus 220 parts per billion. And so the goal of the QUIC experiment is to measure this asymmetry. And in terms of electromagnetic and various neutral weak form factors, which are color coded here, blue and red, the asymmetry can be written in this expression, where tau, epsilon, and epsilon prime are various kinematic variables. In the forward angle limit, where theta is almost 0 and epsilon equals to 1 and tau much less than 1, this expression can be written into more good-looking form. So what we do in the experiment is we measure this asymmetry, we measure the Q square, and then we use the world data, existing world data, to constrain this B term, which is the hadronic structure term. And it is a function of Q square and theta. And then I'll tell you towards the end how we use all these ingredients, asymmetry Q square and this B term, to extract the weak charge of the proton. And that's not all we do. Once we have the weak charge of the proton, we can extract the weak quark vector couplings C1U, C1D, and as well as make a determination of the weak mixing angle, sin squared theta W. And once we have C1U and C1D, we can get the weak charge of the neutron as a freebie. So this table shows the particles and charges, electric and the weak charges of up and down proton and neutron. The electric charge, the more familiar one. The weak charges can be written in terms of C1 and C1U and C1D for proton neutron as well as for the up and down quarks. What is interesting here is we can also write the same weak charge in terms of sin squared theta W at the 3 level, or weak mixing angle. And the C1U and C1D are the quark vector couplings which are defined in the effective Ford-Fermian contact interaction. And what you see here is the weak charge of the proton is highly suppressed in the standard model. And this accidental suppression makes it very sensitive to the physics beyond the standard model. So the goal of the QUIC experiment is to measure this parity violating asymmetry to 4%, which enables us to make a 0.3% extraction of the weak mixing angle at low Q square. And this also enables us to extract the C1U and C1D in combination with the atomic parity violation data. I'll come back to these things later. But here is the QUIC experimental apparatus. I showed you a picture. So here, the beam comes from right to the left. We took up to 180 micrograms of longitudinally polarized beam with up to 88% polarization and at an energy of about 1160 MeV. And this polarized beam passes through the target chamber where there is a liquid hydrogen target of about 35 centimeters, and they scattered, and then a series of collimators define the acceptance of the scattered electrons. The scattered electrons coming out of these collimators are then scattered, are then deflected by this toroidal magnet, by the magnetic field of this toroidal magnet onto the set of 8 main detector quartz bars, which we call the main detectors. So basically we ran in 2 different modes. One, the asymmetry measurement, which we call the current mode or high current mode, where we had very high beam currents, and we also ran at very low current mode, beam current modes up to order of several nanoamps to determine the kinematic variables like Q square and theta. And this was this low current tracking mode operation was done using drift chambers and the trigger scintillators as well as the main detector bars in tracking mode. So how do you get an asymmetry from an experiment? So, and Jefferson Lab is the best place to do that because we can easily get electron beam with opposite helicity states. And turns out that the left and right helicity states are just you can go back and forth, just, or a parity transformation just gives you back and forth of these. So we make use of this process by flipping the helicity of the electron very rapidly. For the cubic experiment, this flip was done at 1 kilohertz, about 1 kilohertz, and I'll tell you why this was so important for cubic. And then we form a quartet. A quartet is simply a basic unit of computing an asymmetry, and it can have helicity windows of this form plus minus minus plus or minus plus plus minus, where minus and plus are the opposite helicity states. And we integrate all the signal in each helicity window. This is not in the current mode. We just integrate all the detector signals and get the yields. So we now form an asymmetry which is given by the difference and the sum of the yields, because it's divided by the sum of the yields at opposite helicity states. So this is the asymmetry, and then we add a blinding factor just to keep off the bias in our analysis. So this is what we see here. This is the asymmetry distribution of the quartet, and we see that the asymmetry width is about 226 parts per million per quartet. Since QE aims to measure the asymmetry with such a high precision, it is important that we collect a large number of quartets as well as have this width of the quartet as small as we could. So to deliver this and to make this possible, and this all was made possible by the QE target, which is also the world's highest power cryogenic target, which took up to 2.2 kilowatt of just beam power. And this was for the first time in any parity Boyleston experiment was designed using computational fluid dynamics to reduce target AC fluctuations. These are several components of the target: the heat exchanger, the target cell, high power heater, centrifugal pump, and other components. And I'm not going to focus on the target, but rather on the target performance. So one of the challenging goals for the QE was to take up to 180 microamps of beam current and then limit target noise less than 50 ppm. And so we did a series of tests, independent tests, and one of them is this. Here I am showing on the vertical axis on the left is the main detector asymmetry weight. The horizontal axis is the pump frequency. So we fix the beam spot size of the target at the size of 4 millimeters square, and we fix the beam current at 169 micrograms, and then we vary the pump speed. And as we go on decreasing the pump speed, you can see the asymmetry weight, which are the blue points, they go on increasing. And this is expected. And let me tell you why. So this is what we actually measure. Asymmetry is formed from these yields. So this is the main detector yield at 28.5 hertz, which was our nominal running point. And this is at 12 hertz. So as you go from 28.5 hertz to 12 hertz, you can see a large drop in these yields. This is basically because of the boiling in the target. As you slow down the pump that circulates the liquid hydrogen, the fluid, the liquid hydrogen will remain in the path of the beam for a little longer, and that causes these target density fluctuations. So once we have these asymmetry weights at different points, we fit them using a model that assumes all of these changes coming from the change in the pump speed only. And then we can fit the data to that model and then extract the target boiling contributions at different pump speeds. And there are other independent ways which I'm not going to talk about, and all of these are within a few ppm, and all of them tell us that the target noise was really less than 50 ppm, which was its design goal as well. And also to mention that this 50 ppm is very small compared to the total estimated width of 226 ppm because it gets added in quadrature. And fortunately, we were able to take some more data at different loop temperatures. So the nominal operating temperature and pressure was 20 Kelvin and 35 psi for the TU target loop. We took data from 19 till 22 Kelvin, and this clearly shows that. And these are again the pump scans like I mentioned in the previous slide, and you can see that as you go on cooling the loop, you get better noise suppression. So this can be very useful for future experiments. We tend to have even lower target noise. And just a while ago, I mentioned that we did the helicity reversal at 960 Hertz. The idea was maybe by doing that, we can suppress the target density fluctuations in the asymmetry measurements. So how did that happen? Here I am showing the fast Fourier transformation of main detector yields at 2 beam currents, 20 microamps where we won't expect target voiding, and at 180 microamps where we expect target voiding. And this shows 1 hour FTL at lower frequencies, which suggests there is some noise at lower frequency. Now, can we quantify this, whether the reversal at higher frequency help? Maybe. So what I did was, I take the normalized main detector yields from different helicity windows that we measured, and then I can reorder them in different ways to mimic the helicity reversal frequency. And I do that in 2 ways. I form a quartet, which is the first and the last minus the sum of first and last minus the sum of the middle 2. Or I can form a pair where I take the first 2 and subtract the next 2. And since each window is at 960 Hertz, having 2 of these is equivalent to having 1 of 480. That's why I call it 480. And if you take 4 of those, that makes it 240. So you can have either a quartet pattern or a pair pattern. And in doing all this, I'm ignoring the helicity sign, because target voiding does not care about the helicity sign. It cares about the and the asymmetry width is independent whether you have the plus or the minus helicity. So the asymmetry I get from here is not physical. So we cannot use that in physics analysis, but all we care about is the main detectors, the asymmetry which we can get from these distributions. So I get the asymmetry widths at various helicity, mimicked helicity reversal frequencies, and then I do this fit that I mentioned earlier, and then extract the target noise. And this is what I get. The solid red curve is blue curve is for the pairwise pattern, and the red curve shows the voiding width dependence with the helicity reversal frequency of 1 over f to the power 0.4, where f is the helicity reversal frequency. And also clear from the plot that the quartet ordering suppresses the target noise better than the pairwise pattern. And these are the 2 data points which we took at 2 different helicity reversal frequencies during the experiment, and they agree quite well with this study of mimic helicity reversal. So this seems very encouraging, and then you might just ask, like, why don't you even further flip the helicity even at higher frequencies and even suppress the target noise more? Sure, you can do that, but there is a trade-off. It will increase your daytime associated with the faster helicity reversal, and then you will have to make a compromise with the statistics you get. So there has to be some balance in there. But nevertheless, I think this is an exciting prospect for the future experiments. Okay, now that we have the asymmetry, what do we do with that? The first thing is to remove the false asymmetries. These false asymmetries come from helicity correlated beam properties like beam position, beam angle, energy, and charge. And throughout the experiment, we try to identify, minimize, and correct for such false asymmetries, and they can be written in this form, where the first term is the slope of the sensitivity slope to that helicity correlated beam parameter, and then this second term is the helicity beam parameter difference. So we measure these differences with beam monitors at various positions in the beam line, and then there are 2 ways to measure the sensitivity slope. You can either use the data and do linear regression on the natural beam motion, because the beam itself moves as it's the target, or you can deliberately change the beam position and angle by using magnets, and then and use that driven motion to calculate this sensitivity slopes. I use the first one in my dissertation, and then once you do that, you can apply these regression corrections at the quartet level. And let me remind you again, quartet level is at the time scale of 4 millisecond. So far so good, but this is what it turns out being. The data I looked at, I found significant non-zero residual correlation at the slug level. A slug is about 8 hours of data. That is when we change our halfway plate in and out. So we take data, so the helicity reversal is done at 960 Hz. Another slow reversal is done every 8 hours where we inserted and took out the halfway plate. That basically reverses the helicity. So the residual asymmetry is the asymmetry without the physics asymmetry. If you take out the physics asymmetry, whatever you get should not be correlated with the beam position, beam helicity correlated beam parameters. But what I found out was these are strongly correlated, and most of the correlation is coming from the x-angle. So what I did was I corrected for this slope, which was highly correlated with other parameters, and it cancels out most of the slopes except for the charge. And then in the next step, I did another simple correction for the charge, and then this pretty much nullifies all the residual correlation for these beam parameters. And as a note, this should be done in more rigorous way all at once and not by one step at a time. But this is what I did in my what is reported in my cases. So what's the use of this post regression? So as I said earlier, we do helicity reversals in and out every 8 hours. So there is a parameter called null asymmetry, which is like a check of how good the health of a data is. So by the name itself, null asymmetry should be 0, but after linear regression, we found that null asymmetry was 0 within 5 sigma. And after applying the post-regression corrections, it brings it back down to less than 2 sigma, which is about 3.3 sigma shift. And post-regression correction for all the not only improves the null asymmetry, but also the blinded physics asymmetry, which is in minus out, and it shifts the the physics asymmetry by about 12.2 parts per billion, which is 1 sigma shift, and it's still within the statistical error of the data set. So we see that post-regression helped the data, and this was for the first time we were able to bring down this huge null asymmetry we had in term 1. And there are still more other corrections to come. This was just the removal of false asymmetries. Now, moving forward, I divided the corrections to the asymmetry in 2 levels. The level 1, which affect the chi-square per degree of freedom of the data, and that involves linear regression and the new post-regression correction and negligible transverse leakage and the non-linear correction. The last 2 are basically 0 with some error bottom line. And then this is what I get. A rho is what we measured, and after all these corrections, I get A measured, and then I correct for the beam band background correction and normalize this quantity on the numerator by P, which is the beam polarization. And we have to do this just to account for the fact that the beam polarization was not 100%, it was only 88%. And so after all of these corrections, so I'm plotting here again the result of the null asymmetry, which is slightly more than 1 sigma, and it's looking a lot better than what it was before, 5 sigma. And there are other corrections to be made, mainly the background corrections, the aluminum window background coming from the target cell windows, the neutral background correction, and then the inelastic background correction, as well as the experimental bias corrections. But these corrections, and then this R-total does not affect the chi-square, the particular freedom of the data, because all of these corrections are applied uniformly to all the data points. They do not change from one data to another point. So after all these corrections, I get about minus 300 ppb ppb of asymmetry with 13.4 statistical error, plus minus 17.2 systematics, plus minus 68 ppb of the blinding. So remember that this data is blinded, and only when we unblind, which we hope to do later this year, hopefully, then only the exact value of the asymmetry will be clear. So for now, But we live with what we have, and then that's why there is this huge blind box. It's not exactly an error, but this is the range of the size of the blinding box. And the effective kinematics was simulated for this particular result. Okay, now that we have this asymmetry which is blinded, we cannot really do anything, we cannot take any scientific conclusion from it, but what we can do as an academic exercise is go from there and then extract the result of the program. And like I said in the beginning, in this expression, we use all the parity volatility electron scattering experiments data on hydrogen, helium, and deuterium, and then do a global fit with 5 parameters. The 5 parameters are the quad vector coupling C1U, C1D, strength, charge radius, and magnetic moment, as well as the iso-vector axial form factor. And all the hydrogen data in these are corrected for energy and Q square dependence for the gamma Z box, electroweak radiative corrections. And once we do that, the width charge is given by the intercept of the field. But as you can see here, this expression, this V term is function of Q square and theta. And for the visualization purpose, we extrapolate all the points to theta equals to 0, and this is what we get. So here, these are all the data points. This red point is the run 1 data point. With the error bar, are only the systematic and the statistics. The larger error bars are the run 1 blinding band. So this point can actually be anywhere within this range. You can say that why don't you just take the whole data and just do a fit and get a measurement for QE? Sure, you can do that. And if you do that, this dotted line shows the value of QE that you will get just using the data except QE. So we need to have the QE measurement because it makes the extrapolation to Q square equals to 0 much more reliable. And it really anchors the extrapolation of the fit to Q square equals to 0. So here's the standard model prediction of the Q sine width chart of the program, and this is what I get. And of course, this central value does not mean anything. The only point of interest is the error bar of this. So just from run 1 alone, we can expect the size of the error on QE measurement to be this. Moving forward, we can now go one step forward and then use the atomic parity variation data on cesium-133 and combine with all the parity violating electron scattering data, including QE. So this is the green band is the APV data, and the blue ellipse is the PDS data. And when you combine both, you get this red ellipse. And this line is the standard model value and standard model prediction, and here is the standard model value. So what we do here is plot this vector and isoscalar C1U, these combinations, and then this fit allows us to extract to a high precision these C1 coefficients of like quartz. So once we have C1U and C1D, we can pretty much calculate the weak charts of any system. So here again, the central values do not mean anything. It's just the error bar. Just to demonstrate the fact that the QE measurement can provide a much more precise values of C1U and C1D. And from there you can get the weak chart of the neutron as well. This comes for 3 from the QE measurement. And lastly, the goal of the QE is to test the standard model by testing its prediction of the weak mixing angle, sine squared theta w. This plot shows the running of the sine squared theta w in the minimal subtraction bar scheme, where this curve is the standard model prediction, and the thickness of width is its uncertainty. The red points are several different measurements. Some of them are still moving up and down. This point here in purple is from the 4% of the published QE result, and this point here in black is from the result I just showed you on an arbitrary vertical axis with the error bar, but the error bar here shown is from the statistical and the systematic uncertainty. If I were to include the blinding box range, it would be this. So this point can actually be anywhere in this range. And since the data is not going to be unblinded now, we just have to do this. But the take-home message is once we have the full result, we'll test the QE result will test the standard model prediction of the weak mixing angle. And this is the final anticipated uncertainty on the weak mixing angle. So once we have the full data set, that will be a really competitive measurement. Okay, now so if we see a significant deviation from the standard model prediction from the cubic result, then it would mean that there are some interesting physics that are sensitive to new parity evaluating physics that come to Swedenborg and quarks. There are several models out there that deal with this, and if we do not see, or if we see agreement between the standard model and the cubic within the error bar, then our model independent mass risk, which is given by this relation where I'm using the error on my cubic point from blinded run 1 analysis to be greater than equal to 2D. And this is at 95% confidence limit. But to set the exact mass limits, you have to choose the value of the top limit z. In popular literature, people use z equals to 1 or 4 pi. So depending on what you use, your mass limit lambda is going to be of the order of several t. So an agreement of the cubic experiment with the standard model will signify, will rule out new physics at the level of certainty. And that remains to be seen. So to summarize, the final cubic measurement will test the standard model. And one remarkable thing about the experiment was the cryogenic target was not only the highest power but also the least noisy. Usually the higher the power, the more the noise, but this has been really a huge achievement, and this is pretty encouraging for the future experiments, I think. And blinded random statistical results are reported in my thesis, and we are working hard to get to finalize the whole analysis, and we hope to have the final results soon. And I'm not going to call all the names, but this is a wonderful collaboration that made it all possible. And I want to thank the cubic collaboration, and of course, thank you. Yes. I did not quite get your question. Can you please repeat?
No, I'm asking that, so if you do the same thing for the electron-neutron scattering, what would be the asymmetry?
Interesting. I have not really thought about that. Well, electron-neutron scattering is not as obvious as electron-proton because we do not have a free neutron target. So I cannot really comment on what would be the asymmetry mean for that scattering process.
But let's thank the speaker. The next speaker is the other winner, the other co-winner of the thesis prize. It's Cristiano Fanelli, and he's going to tell us about wide-angle complex scattering.
So I presented the results of binding analysis on electron scattering on proton. This experiment has been performed in OOC in 2008 under the guidance of Stephen Wood, the OOC leader, Morgan Jaworski, the wide-angle scattering spokesperson around coordinator, David Hamilton, the analysis coordinator. And the advisors of my PhD thesis are Professor Johnny Salman and Dr. Lisa Shismani from Sapienza University. So, real quantum scattering on proton in the wide-angle regime is a powerful probe of the Newton structure. It is elegantly simple and involves only a real photon and a ground state proton in both initial and final states. Nevertheless, it's rather underutilized, and it is one of the least understood fundamental processes in the cellular GPG. And the physics involved is similar to elasticity scattering or big virtual quantum scattering in the sense that the electromagnetic response is investigated without complications from other agents. So the common issues are to study the interplay between the hard and soft processes, and to investigate the onset of the asymptotic regime, and therefore the applicability of perturbative QCD, and also as well as the embed mechanism and generalized particle distributions, and therefore our data allow to constrain theoretical models. So wide angle quantum scattering? The angle refers to the central mass scattering angle of the proton, and if this regime is reached when all the Mandelson variables are larger than the square mass of the nucleon. And under this condition, we have the factorization of the transition amplitude into a product of soft wave functions representing the coupling of the quarks to the proton, and a Kerr function representing the coupling of a quark to the electromagnetic probe. Competing reaction mechanisms, but the two more developed frameworks are perturbative QCD on left and embed on right. Perturbative QCD is characterized by a two-arm muon exchange, and the cross-section scales at the denominator as S to n minus 2, where n is the number of active constituents. The embed is characterized by GPD, and a quark is picked by the generalized particle distribution, and then interacts with the electromagnetic probe, the photon, and then is reabsorbed in the nucleon. In this case, the cross-section scales as the Klein-Shima cross-section times real quantum scattering for factors. So the generalized particle distributions, keeping in mind the relation between quantum and deep energy scattering provided by the Ottner theorem, the real quantum scattering for factors and the generalized particle distributions are related by this formula. Basically, they are the inverse moment of the GPDs. And in analogy for the elastic quantum scattering, we see similar formula for the theta external power from factors. And also, in the lower table, we see the interesting T equals physical limit, where we get the particle density function, unpolarized, polarized, and also the total angular momentum contribution from quark to the quark. So GPDs will allow unification of the Newton structure. They are accessed through exclusive reactions, such as quantum scattering, and they correspond to the proton in light from the elements. And they allow a description of the longitudinal momentum fraction and transfer location of the proton particles. So the technique used in this analysis is the famous JLab polarization transfer technique. We have a longitudinally polarized incident photon impinging on a proton, and we want to measure the transfer polarization to the final proton in the recoil direction. So this is the meaning of K and L. And this is the expression in terms of the differential cross-sections, where the two arrows refer to the helicity of the incident photon and that of the final proton. I will describe more in detail later in the next slides, but JLab provides a very different predictions for the two frameworks that we want to study, perturbative QCD and embed. And a previous experiment, E99114, provided a stringent test that wide-angle quantum scattering proceeds via photon interaction with the leading quark at a central mass scattering angle of 120 degrees. And in brackets you see the values of the Mandelson variables. So as for our experiment, this has been performed at a different scattering angle, 70 degrees. And these are the values of the Mandelson variables, where you can see that the values of the U Mandelson has been increased up to 4 square GT. The layout of the experiment is presented in the next slide. So we have an incident beam of electrons, polarized electrons, and we want to produce polarized photon beam. And we do that by a radiator, capital radiator, and we take advantage of the Bernstein effect. But we have to reach a good compromise in terms of the flux of photons and at high energy. Indeed, at high energy, we get a high polarized photon as the polarization of the electron beam. So after we get a polarized beam of photons, these photons impinge on the protons within a liquid hydrogen target. And in the final state, we want to measure the final photon by the shower calorimeter. And in front of it, we have a deflector magnet to deflect background electrons. And in the adjoining arm, we measure the recoil proton scatter. And they are measured by the HMS high momentum spectrometer, and then they reach the protons, they reach the focal plane calorimeter, and we measure the polarization of the focal plane. A detail of the high momentum spectrometer is supported below. We have 3 quantipoles and a dipole, and therefore we have to take into account the precession of the proton spin, and then the proton reaches the detector hut, within which we have the 2 focal plane calorimeters, carbon analyzers, surrounded by 3 chambers to measure the proton trajectories. So, as mentioned earlier, one of the most important parts of the analysis is to model the spin precession through the HMS magnetic models. So we took into account the precession of the proton spin governed by Lorentz-Force law, then the precession of the proton spin due to the magnetic models, as described by the Thomas-DMT equation. And then if we use a geometric approximation, we can see the speed, the total spin transport matrix relating the proton polarization at target to that measured focal plane. So the proton, when they reach the focal plane polarimeters, they scatter off matter in the focal plane polarimeters by spin-orbit coupling. And this gives rise to azimuthal distribution F plus minus, as recorded in this formula. This distribution depends on several terms. The first are the phi azimuthal angle, then the analyzing power of the polarimeter, and then we want to extract the 2 polarization components, Py and Px. Plus minus refers to the initial P melicity of the photon. And therefore, if we take a difference of helicity correlated proton rates as a function of the azimuthal angle phi, we get these graphs. These are for several selection. The red points are for the wide angle quantum scattering selection. The full circles here are related to one of the main diagrams, that is pion for production. The open circles are related to elastic electron scattering. And therefore, from this asymmetry, we get information at the focal plane of the polarization transfer. But we want to backpropagate this information at target. So once we backpropagate this at target, we also have to consider an additional matrix, that is the Wigner rotation, in order to be consistent with theoretical prediction expressing the helicity S frame from center of mass. And so we can build a likelihood function on an event-by-event basis. And we can insert here all the measured quantities, like the azimuthal angles phi, the elements of the spin transport matrix, the analyzing power. And we want to extract the polarization component, labeled here as P. And we do that by a Markov chain molecular. With this method, we are able to extract the distribution of these polarization transfers. And for instance, the plot here represent JLab versus KLT for the one selection. On the right part, you see a survey of the statistical property of the Markov chain molecular. And we have a control that the extraction is good. So the electromagnetic form factor ratio. We can measure the electromagnetic form factor ratio by the elastic electron scattering. The elastic electron scattering is a byproduct of our analysis, since it is one of the background of the analysis. And by this measurement, we can validate the analysis procedure. And the value that we have obtained is this point, supposed to be red, at 2.25 square GT. And the value obtained is 0.74. That is quite consistent with the best fit of all the previous measurements performed, this kind of performed on JLab. Also, on the right part, for a comparison, we show also the data point extracted with the Rosenblatt separation method. And so the famous discrepancy between the 2 methods. Another important part of the analysis is the measure, the calibration of the analyzing power at the focal plane polarimeters. The analyzing power properly describes the proportionality between the polarization of the incident proton in the focal plane polarimeter and the size of the azimuthal symmetry. And these are the plots of the analyzing power as a function of the transverse momentum of the proton for the focal plane polarimeter 1 and 2 using these formulas. So taking all these ingredients into account, we can try to identify the events of wide angle quantum scattering. First of all, the main variants here are reported. Pion for production events, elastic electron quantum scattering, and Betty Eibler with a final radiative photon. 2 important plots are shown on the right part. Delta Y versus delta X in the calorimeter, Delta y is the difference between the measured and the predicted by two-body kinematics. Y coordinate in the calculator is the same for delta x. And you see that the events wide angle complex scattering are located in this small peak, which is contaminated by very high events as well. Beneath this small peak, we have polynomially distributed events due to pi and photon production. The highest peak here is due to deflected electrons in the final state, due to elastic electroproton scattering process. Another important plot is here is delta y versus the reconstructed incident energy. And the region of wide angle complex scattering is located here, in the window of the incident energy between 3.6 and 4 GT, and a delta y around 0. And all the other samples are represented in this plot as well. So the background contributions. We want to measure the polarization transfers associated with background contributions. We do that studying the regions where signal is assumed not to be present. For instance, in a delta x, and y plot, you see that the pi of production are selected by y elliptic curves around the peak of wide angle complex scattering given candidates. And also here we have a spectrum of the coincidence times of the trigger times of the two detectors, and random events, accidental random events can enter this spectrum. And so we select the side region of this spectrum. And as for the fractional statistics, which must be taken into account into the final convolution, for instance, for EB gamma, what we do, we develop several techniques. Here, there is the spectrum of the incident energy. The highest peak is due to elastic electroproton scattering. The broader peak here is due to wide angle complex scattering overlaid by pi for production events. And here dashed is the EB gamma contribution that we want to extract. So we present here one of the methods developed to do that for EB gamma. We use calibration data without radiator. And we want to measure this quantity, n EB gamma, a fraction of EB gamma events divided by the EB events. On the left plot, you see this fraction as a function of the threshold cut used in the incident energy spectrum. We basically select events with a larger energy than this threshold. And if we do this, we see the different plot that we get for delta y. And the red plot here is with a tight cut on the incident energy, and you see that we can select EB gamma events with a final photon measure in delta y around 0, and EB events in the highest peak with deflected electrons. And so this n EB gamma enters this formula. This is the fraction of wide angle complex scattering event within a small peak shown before. The value of this fraction of events is 65%, and it's consistent with all other developed techniques and also the Monte Carlo prediction. So here the deconvolution. The first table is the measurement of all the polarization transfers associated with all the background contributions, and also with a narrow ellipse selection here. We want to measure the wide angle complex scattering within this tip, and the selection is these slides, the narrow slides. And so we have to take into account this deconvolution formula, and of course this is based on the values of the polarization measure for the truth of the plane parameters, as well as the fractional statistics that we determine for each selection here. And therefore, in the end, for the truth of the plane parameters, we are able to extract the values for the wide angle complex scattering events, both for KLT and JLab, TFS which polarization. And so this is the plot of KLab versus the central mass scattering angle of the reaction. This point, the red one, is the new point measured in this analysis. The black point is the previous measure. And there are several theoretical predictions plot here. The first one is Kaini-Shina for a point like proton. This is the red dash card. The solid red card is related to Postino core model with specific mass values for the quarks. Then we have the solid blue line for soft collinear effective theory. Then we have this gray band based on GPD calculations. And then we have Raggi predictions, the blue dash curve. And then we have two perturbative PCD-based calculations, where the negative one is in the asymptotic approach, which is very accurate since it is based on more than 300 Feynman diagrams. So without error, this must be negative. And our value seems to indicate that we are consistently leading quark mechanisms, but we exceed all the theoretical predictions. So about the wide-angle complex scattering research program, the real complex scattering research has a significant chance of discovering an actual reaction mechanism. And this motivated a new experimental proposal recently approved at 8 and 10 GeV of photon energy. And this is the space in S and T that will be explored at the 12 GeV upgrade. And okay, for the upgraded JLab 12, since we will have double the energy, we will reach also an outstanding luminosity up to 10 to 39 units per square centimeter per second. And so we have the so-called tracking challenge. We have to find a tracking algorithm able to operate in a high luminosity environment. And this is an issue regarding many experiments. And so as another part of my PhD activity, I also dealt with this problem. And so in this slide only, I want to mention that the method developed is a multi-step approach that is developed for a rather generic tracker based on 6 chambers and 2 silicon microsync detectors, so an hybrid tracker. And it is made of 3 steps. The first is to take advantage of the charge and time correlation for clustering. The second has been to design a neural network for rate association with the tracks. The third step is common filter of the associated hits into tracks for precise track reconstruction. And preliminary results based on a Tony model and shown in the SBS weekly meetings provide high reconstruction efficiency and accuracy and good computational time. The work is still in progress. We are studying multiple scattering effects. We are including cluster shape and charge information, and we are making comparison with other methods. So, the conclusions. The E07032 analysis of wide-angle complex scattering provided measurement of ALT and KLL at the new kinematic points. The value for ALT and KLL are shown here. ALT is compatible with mbed and perturbable QCD, but KLL is completely inconsistent with perturbable QCD. And surprisingly, KLL is larger than all the available theoretical predictions. A paper with the results has been already circulated in collaboration and almost ready for submission. And possible interpretation of the large value of KLL might be related to configurations of the proton with non-zero quark angular momentum, or maybe UD dipole correlation. And therefore, new high precision measurements are necessary to enlighten these emerging features. I really want to thank these people here and for their help and their valuable feedback during all the work, and I will not forget anyone, so thank you very much.
Can you show the slide again that shows your extraction of the analyzing power? Yes, here. Okay. May I ask what range of Z-close you considered, and did you include only single-track events in your analysis, or also multi-track events?
No, it was single track, and the values or the range in Z-close is reported in my thesis. To be precise, I don't remember exactly the values.
But there is some cut.
Yeah, there's
corresponding to the
yeah, I think the same cuts of Metzian thesis as well. Yeah,
oh, okay. Okay.
Yeah.
Yeah, it looks maybe a little bit lower than I would expect at that momentum. From, but okay. I'll read your thesis.
Any other questions? If not, let's thank the speaker and all the speakers from the Let's close today's